presenter will play or we will play on their behalf? Mr. Parag Patil.
Yes, I start the presentation, okay?
So just allow
Yes,
allow a minute,
okay,
please.
okay.
Mr. Parag Patil, is
Hi.
the presentation will be played by you
Okay.
or
Hello.
Mr. Parag Patil?
Yes. Hello. I'm
Yes, yes.
view my
Yeah.
presentation from here.
So, okay, you will
Okay.
run the
Yeah.
presentation, no? Okay. And next,
Okay.
virtual
Yes.
MNC, the next presentation is from Dr. Prajakta, and it is a video. We will play it automatically. And the next fourth is the Ravindra Bhate. Again, we have the video. We will run. And the fifth is not available. Then we'll switch to the sixth, Veer Raja. Again, we have the video presentation. I think everything is set. Now we can start with make a live.
Yes, ma'am. We can going to make live.
Hope all the presenters are ready. They are going live.
Okay.
Thank you.
All right. I start the presentation. Okay. Yes. Hi. Thank you for giving my opportunity to make a presentation now.
So
I would like.
just a second. Virtual MNC, it's live now.
Uh,
Can you please confirm when the chairman has to start? Virtual MNC. Can you hear me, virtual MNC?
I will the presentation myself. Thank you for giving an opportunity to make presentation now. I'd like to report from Master of Tokyo Electric Power Company Holdings Inc. on the subject of study computational fluid dynamics analysis with design on the spillway of hydraulic power plant. I'm not good at English, so please forgive me if it is difficult to hear. First, we are planning to install a new spillway as shown in the figure at our hydroelectric power plant. The flow of water during power generation is the light blue line. On the other hand, uh, when the power plant is shut down, water flows as shown by the light by blue line. At that time, the water is de-energized by colliding with the impact type energy dissipator and then further de-energized by the stair type energy dissipator. In this way, we are aiming for a facility that can safely discharge the water when the power plant is shut down. Here, in designing equipment with such a complicated flow, in order to confirm the water flow and the influence on the equipment that can't be grasped by the desk calculation on the conventional method. It is necessary to carry out a hydraulic model experiment. However, this time we decided to conduct a study aiming at the using CFD analysis as an alternative to the experiment. Specifically, first, a basic hydraulic model experiment is performed, and then a reproduction analysis by CFD is performed. Here, if the analysis accurately can be verified, it judged that CFD analysis can be used as a substitute for experiment in further design changes such as cost reduction studies, so the hydraulic model experiment can be reproduced with high accuracy. So we examined the analysis method to be used. The following are the specifications, plan view, and external photographs of the hydraulic model experimental facility. For the hydraulic model experiment, the target was composed of impact type energy disparator and state type energy disparator that connected the hydraulic iron pipe and the drainage ditch, and the scale was made as 1/10 according to the fluid similarity rule. Regarding the measurement, we measured the water level in various places in the hydraulic model and water pressure acting on the impact type energy disparator. Here for safety analysis, we decided to use Flow 3D, which is a general purpose safety code, and analyze by the both method by the finite difference method. Regarding the analysis conditions, the shape model was modeled it in the same range as the hydraulic model with the same dimensions, and the boundary conditions were also the same as the hydraulic model. In the reproduction analysis, some problem occurred, but as a result of solving these problems, the results shown below were obtained. First, regarding the flow conditions, the result of comparing safety analysis and hydraulic model experiments are shown. The flow conditions in the safety analysis result are in the same state as the hydraulic model experiments, and it is considered that the flow conditions in the hydraulic model experiments can be reproduced with high accuracy. Next, regarding the state-type energy disparator in the hydraulic model experiment, the water level was measured at the position shown in the figure. The result of comparing shift analysis and hydraulic model experiment is shown. The water level of the shift analysis result was compared with the result of the hydraulic model experiment, and the result was almost consistent. Uh, in the hydraulic model experiment of the impact type energy disparator, the water pressure was measured at the composition shown in the figure. Regarding the water pressure acting on the impact type energy disparator, the CFD analysis results showed the same tendency as the physical model experiment in terms of the maximum and average values, which are important in design. It is summary. The shift analysis result showed the same flow conditions as the hydraulic model experiment results, and overall the results were consistent with the hydraulic model experiments. This gives us the perspective of that safety analysis can be an alternative to hydraulic model experiments. In the future, we will take measures to utilize the safety analysis results for the further design changes such as cost reduction studies and water flow tests using actual machines after construction. Thank you for your attention. I'm sorry, I'm not very good at English, so I can't understand your question right away. Therefore, please send your question to my email address, please. Thank you.
Hello.
Hello.
Can I start my presentation? Hello.
Hello.
Yes, I am Bharat Patil. Can I start my presentation now?
Oh, presentation finished. Presentation
Ye-
finished.
Yeah, yeah. या तो झालं झालं की नाही? झालं सुरू झालं एकदम बारीक कर. इथं कर. Can I share? I am audible. Hello.
Audible?
Yeah, my presentation is shares. Hello. चल 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 सुरू. इकडं आलो.
Yes, we can see the presentation.
Yeah. Good morning. I'm Parag Patil, scientist, Central Water Power Research Station, Pune, Maharashtra. Here I am going to present on the topic is optimizing layout of the power intakes in the runoff river projects. As we know, in India, the vast power potential is available in the north and northeast region, Himalayan region, because these are the rivers in the perennial type and having the steep slope. Secondly, the main problem of all these rivers having the problem of the huge sediment carrying and deposit is the same in the reservoirs. So for efficient management of the sediment, we are normally practice low spillways and crests very near to the bed of the river, which gives the opportunity or give the arrangement that is periodic flushing. In the runoff river projects, intakes are normally provided near the intake that is generally aligned with the 90-degree to the dam axis. The basic function of these intakes to withdraw the water from the river or reservoir and generate the power, and again sediment free laden water will be discharged into the power rate tailways channels. The sediment deposition pattern in the reservoir is highly site specific. It depends upon the various factors like the reservoir capacity, reservoir geometry, then geological features of that area, flow characteristics of that river, then sediment characteristics, then how the reservoir will be operated. The present paper give the three case studies in the Himalayan run of the river schemes. That is the unique solutions given for their power intakes. First case study I am going to here present. Hello. First case study I am going to here present that is Subansari AG project, which is situated in Assam, Arunachal border, 2000 megawatt project capacity. This is the power. This is the powerhouse, or what do we say? The intake is a staggered intake. This is the dam axis. In this project, we reproduce 1:100 model. That is, this total reach of this river is 10 kilometer upstream and 0.5 kilometer downstream of the dam axis. Initially, we can see in the first side the intakes are in staggered conditions, and while studying for the discharge of 6,000 meter cube per second, the full reservoir level is 2,005 meter, and we are done carried out studies for 24 hours. In this, we can see in the next slide the staggered position intake condition. We can get the sediment slag zone. This slag zone will created due to the staggered position, and while this sediment deposition is occurred, will hamper the power generation in turbines and all these things. Then from the studies we can suggest them, if we place the intake in one line or in avoid to staggered condition, and the sediment laden zone will be clear. By these studies we will be conclude the same thing. Second study, that is Chamera HE project, which is situated in Himachal Pradesh. Here we can see the blue one, that is the intake position is 90-degree, and gray one, that is the initial position of the intake, that is 100-degree to the dam axis. This is the model layout. In this case, we construct the model in 1:70 GS model. The reach of this model is 3.5 kilometer upstream, 0.5 kilometer downstream. The original alignment of the power intake, as we seen in the previous slide, is 100-degree to the right bank. Like by the experiment of discharge of 500 meter cube per second of flushing discharge, we can see that the very low cushion is available in the spillway crest and the intake invert level of the Chimera project intake. So while the cushion is very low and the reverse flow is created in the front of the right way of the intake, the sediment laden water or suspended sediment will go enter into the conductor system. So to improve this condition, we will give the result or we will give the suggestions to the project authority to keep the intake at a 90-degree and avoid the what we say the you know, in front of the intake the small sediment will be deposited and it will close the sediment laden water into the conductor system. Third project is the Mangdechu project, which is situated in Bhutan. And here we can see the total model reach, that is 825 meter upstream, 200 meter downstream. And this is the dam layout. Here we can see the intake positions, that is AA, CC, and BB. These three positions will be given by the project authority itself. In these conditions, we construct the model for 1:100 J scale. The total reach is at 25 meter upstream, 200 meter downstream. Then these are the key conditions as we seen in the previous figure. But condition A, BB, and CC, condition AA and BB is more favorable for the sediment point of view. But due to the geological constraints, they are not able to construct the position at A and BB. So again, the construction, again, the third position, that is CC, is shown in figure, is studies are carried out on this condition. While studies, we will see that the condition at position at A and CC is more favorable. Means the sediment deposition level in front of the intake, that is more below, that is crest 8 to 10 meter normally. So we suggest them, we can suggest them that intake will be provided at the condition at the section at CC. And here we conclude that the present studies highlighted of the physical model studies in the finalizing intake position with respect to sediment deposition levels after flushing. Then present studies, it can be seen that experiments on the physical scale models can be used to optimize the alignment of the intake and flushing efficiency of thereby reducing deposition in front of the intake. Efficient solutions can be derived to suit site conditions and the project constraints with the help of the physical scale models. Thank you.
प्रेझेंटेशन मोड नव्हता तुझा.
Thank you.
Hello, virtual MNC. Yeah, I request you to please run this video presentation. Yeah.
Ensuring the stability of the dam. Periodic inspection. My today's topic is based on this saying. To maintain good health, like people, structures also needs regular checkup. Radial gates and spillways are used for safe passage of flood without endangering the stability of the dam. Periodic inspection can reveal trends of something serious is developing. Today's presentation will provide information regarding how a comprehensive condition assessment of spillway and radial gauge should be conducted, what are the common defects in these structures that we find out from this condition assessment, and what future action
Scientist C from CWPRS Pune. The topic of presentation is innovative research methodology in evolving design of spillways for Himalayan HE project. Most of the India's hydropower potential exists in north and northeastern Himalayan region. The perennial river with the large hydraulic head provide attractive possibility for large-scale power development. High mountain and steep slope fragile geology are some of the characteristics of the Himalayan terrain. These rivers carry the large amount of the sediment with it, and hence sedimentation of the reservoir is a serious problem, especially in the Himalayan terrain. These are some of the hazards of the sedimentation. Some of the projects affected due to the sedimentation are Salal, Parasul, Vaniri, Bali, Chila, and Nakpajagre. Flushing, it is an effective technique for removal of the sediment. Earlier, the overflow type of the spillway with the small sluices in the body of the dam were used for flushing purpose, but it was observed that this flushing is not effective due to the small sluices of size 3 meter by 4 meter. These were effective only locally, and there was a tendency of choking these sluices within the very short period of time. Hence, the innovative design has been developed in design of the spillway, where the crest of the spillway is kept as nearer to the riverbed, which fulfills the criteria of the flushing of the sediment. Nowadays, these orifice spillways are being more popular due to its dual advantages of passing the flood as well as flushing of the sediment from the reservoir, and are adopted on most of the hydropower project. This is the model view. Yellow color shows the pier. In between that, the breast wall is provided. This is the breast wall. This red color shows the radial gate. These are the divide wall, and this is the energy dissipation arrangement in the form of ski jump bucket. These are the advantage of spillway can be accommodated in a narrow value, reduction in the height of spillway gates, reduction in number of spillway span, ease of regulating flood and storage, reduction in cost of gates and operating mechanism. This can be used for diversion of flows during construction of the project and also used for flushing of the sediment. These are the general consideration, discharge characteristics of the spillway that we will discuss in subsequent slide. Waterway of the structure in relation to the width of the natural water course. Generally, this width is kept minimum from the economical consideration. Size and dimension that we'll discuss in the subsequent slide. Protection of the spillway surface to resist abrasion. Generally, these spillways are adopted for the high dam. When this high velocity flows passes over the spillway, there may be the possibility of causing the abrasion damage. Hence, it is required to protect the spillway surface to resist the abrasion damage. Proper care is taken. Also, the care should be taken in selecting the energy dissipation arrangement, as these spillways are used for flushing of the sediment. Generally, the ski jump bucket is the best option for energy dissipation for the orifice type of the spillway. The waterhead is of the order of the 30 to 60 meter over the spillway crest. Width of the span varies from 6 to 15 meter. Height of the opening is of the order of 10 to 21 meter. Height of the breast wall is worked out to be 20 to 40 meter. In order to support such high breast wall, thickness of the pier also increases substantially. Discharge capacity of the orifice spillway. This is one of the most important hydraulic aspect in design any type of the spillway. In orifice type of the spillway, two type of the flow occurs. One is the free flow when the water level is below the top level of this roof profile, and when the water level is above the top level of this orifice flow occurs. This discharge for this two type of the flow can be calculated by using this formula, where the coefficient of the discharge, that is the CD value, is influenced by many parameters, that is upstream, downstream, and the root profile, head over the crest, height of upstream depth, that is the height of the crest from the river bed, shape of the pier nose, aspect ratio of the orifice opening, that is width and the height of the orifice opening, and approach flow condition. Upstream quadrant of the crest is may conform to the ellipse similar to the OP profile of the spillway, and downstream profile is generally in the form of x square is equal to 4SCY. This is the roof profile. This is a closer view of the roof profile. It guides the flow smoothly. And design of this roof profile should be in such a way that maximum discharging capacity is achieved and the pressure on this profile should not be excessively negative. Till now, there were no guidelines provided for this design. The profile is provided in the form of the quarter of an ellipse suggested by the USBR. The main aim of this presentation is to discuss how this profile affects the performance of the orifice spillway, especially in terms of the discharging capacity, which is considered as an important hydraulic aspect. These are the hydraulic design aspect to be studied: discharging capacity, approach flow conditions, pressures on bottom and roof profile, water surface profile, and flow condition along the spillway bottom profile. Now I'll discuss here the contribution of the CWPRS in evolving the design of orifice spillway. CWPRS has contributed for more than 25 orifice spillway projects for evolving its design. I'll discuss here the two case studies. One is the Tala project, where the maximum discharge is 10,600 meter cube per second and the power generation is 1020 megawatt. Sluices of size 6.5 by 13.5 meter. Head is 43 meter and ski jump is the energy dissipation. Model studies was conducted on 1:40 scale 2D sectional model. This is a cross section of the spillway and this is view of the physical model. The studies indicated that discharging capacity of the spillway was adequate. The piezometric pressures observed on the bottom as well as the side of the spillway were also acceptable. However, the pressures on the roof profile was negative of order of minus 13.5 meter for the PMF discharge of 10,600 meter cube per second under free flow condition. Corresponding cavitation index was calculated as 0.016, which was less than the critical cavitation index of 0.2. Hence, design of this profile was modified. Originally, it was the elliptical profile recommended by the USBR. Now, the various alternative with the different entry and the exit angle was modified. This is the table shows the discharge values and the corresponding cavitation index for the original design as well as different alternative. For original design, the maximum negative pressure was 13.5 meter and corresponding cavitation index was 0.016. For alternative 3, the pressure was reduced from 13.5 to 3.56 and cavitation index was 0.2 to 0.27. This was observed for entire range of the discharges, and by comparing all these values, the alternative 3 profile was considered to be suitable and was recommended. This is the second study, Punasancho project, where total maximum discharge is 15,800 meter cube per second, 7 sluices of size 8 meter by 15 meter, and head over the crest is 36 meter. These studies were also carried out on 1:50 scale 2D sectional model. This is the original elliptical profile. For this profile, it was observed that this flow was not touching this profile, and hence there was a reduction in the discharging capacity. Again, the various alternatives were carried out with the different entry and the exit angle. For alternative 2, we observed that this flow was touching this roof profile of the orifice spillway. This is the table showing the discharge value for various alternative. This is for the original design. The discharge of 13,426 meter cube per second was passed for the original design, whereas for alternative 3, the discharge of 15,736 meter cube per second, that is 2,000 meter cube per second more than the original design was passed over the spillway, and hence by comparing in all this data, the alternative 2 was recommended. In addition to these two case studies, CWPRS has also contributed in different for various orifice spillway project, and from that we found that how this roof profile plays a very important role in assessing the discharging capacity of the orifice spillway, which is one of the important hydraulic aspect. Hence, basic research studies was carried out using the physical and numerical model. Total 250 number of the experiment and simulations were carried out. For this, the height of the orifice opening was selected as 0.2 to 0.4, that is 10 meter to 20 meter in the prototype, considering 1:50 scale model. Design head is 0.6 to 1.4, that is 30 meter to 70 meter. Operating head is less than design head, equal to design head, and greater than design head. For this research, width of the span was kept constant, that is 0.2 meter, and height of the spillway crest is kept constant, that is 0.2 meter, means 10 meter in the prototype. In the first setup, there was no solid bottom as well as the roof profile. Experiment were carried out for the different design head as well as the height of orifice opening, and by measuring the lower nappy profile, we finalized the spillway bottom profile in the form of equation x square is equal to 4hty. This profile we then fixed at the downstream of the orifice in the second setup, and again the experiment were carried out for this setup for various design head and the height of orifice opening, and by comparing all the data, we finalized the equation for the roof profile in the form x1 is equal to a y1 by b to the power m, where x1, y1 are the x and the y coordinate. A is the length of the breast wall, which can be calculated using this formula, considering the height of orifice opening and the design head are important parameter. This equation is valid for the head design head ranging from 30 to 70 meter, height of orifice 10 to 20 meter. But for when the spillway bottom profile is in the form of x square is equal to 4hty. This equation would be useful to engineers at initial design stage of an orifice spillway to make the structure economical and hydraulically efficient. Then we compared this roof profile of the proposed equation with the existing case study. 3 case studies were selected. This black shows the original profile, blue color shows the profile finalized from the physical model studies, red color shows the profile from the proposed equation. These two profiles were far away from the original profile in all the 3 cases, whereas the profile proposed from the present research was very close to the profile finalized from the physical model study. Hence, it can be this comparison shows that large number of the trial and error could have been avoided if the proposed equation was available earlier at the design stage. Now we change the height of the crest from the bed of the upstream reservoir and found its effect on the discharge and the pressures on the roof profile, because these two were the important parameter in our basic research. The P, when we vary the P, that is 0.2 to 0.8, that is 10 meter to 40 meter in the prototype, there was no much change in the discharge value, as well as there was no change in the pressures on the roof profile. Hence, insignificant effect of the P was observed on Q and pressures on the roof profile. Then we changed the K value from 4 to 3, which made the profile steep. For this steep profile, there was increase in the discharge value. Discharge was increased from 0.182 to 0.188, but there was a sudden drop in the pressure value in the initial region, and the corresponding cavitation index was calculated below the 0.2, that is less than the critical cavitation index. Hence, the performance with the K is equal to 4 was found satisfactory, and it may be recommended to use the K value as 4 for design purpose. For BPD is 0.3 when we design this with respect to D. Two aspects Two considerations were taken, that is BD is equal to 0.3 and 0.4. When we increase 0.4 times of the D, there is a increase in the discharge value, and there was no change. There was not much change in the pressure value. Hence, from this, we concluded that D by D make the profiles deep and longer, and there is increase in the discharge value. Hence, this may be adopted for the design purpose. From this, we conclude that orifice spillway is a common challenge, especially in the Himalayan region. The advantages of the flood, of the sedimentary reservoir. The things derived from these studies would be applicable for all the practical design made at orifice opening and useful for the design engineer while designing the structure at the initial design stage. Verification and calibration studies prove the applicability of this information with respect of the discharging capacity and the pressure distribution of the spillway. However, the one point I will mention here that as the design of this project is unique in this respect, the performance of the spillway with developed equation should be checked by conducting the hydraulic model studies. Thank you.
Mr. Ravinder Bhate, are you ready? Can I play your video?
Yeah, please.
Thank you.
Warm wishes to dear participants. I am Ravindra Bhate, Scientist C from Central Water and Power Research Station, Pune, presenting paper on future challenges in design of spillway and energy dissipators. As on today, there are approximately 57,000 large dams in the world, and India is ranked third after China and USA. In India, there are about 5,350 large dams and about 410 under construction. For any kind of dam, spillway is the paramount importance part of any dam project because it confirms or it governs the safety of the dam. And for optimizing the design of spillway, hydraulic performance of spillway, the hydraulic modeling is the most important tool. As the dam building activities are going on for many years, almost all easy sites have already been tapped, and we have been left with the difficult sites, narrow valleys, increase in the globe, upward revision in the flood and coastal reservoirs. And these different types of, this poses different types of challenges in front of designers and to design the spillway for these scenarios. When we consider the Himalaya as the power hub of India, and there are the identified capacity is about 85% of total capacity of India, there are three major basins, Indus, Brahmaputra, and Ganga. And all these basins poses the challenges of the Himalayan rivers, and the challenges of the Himalayan rivers are the narrow and steep valleys, the river slope between 1 in 30 to 1 in 100, causing flash floods. The sediment rate is very high. They will carry high amount of silt and boulders with it. High seismic zone is there. Problems of heavy sediment load due to fragile geology and landslides. Sudden breach of glacial lakes are there. Recently, on 7th February, we have experienced an accident in Himalayan region. Difficult to construct the storage reservoirs due to siltations. There are certain experiences from the previous storage reservoirs that it got silted up within few years. And the viable solution is the run-of-the-river schemes and spillway structures for these kind of rivers where they carry very high amount of sediment with it, or there are the chances of blocking the river due to the landslide, and when the overflow takes place, it will carry a high amount of silt with it into the dam. The possible option can be the breastwall spillway, where the spillway crest is kept as low to the as near to the riverbed as possible. This is one of the typical breastwall spillway where the head is generated using the breastwall spanning between tiers, and the is at the bottom of the dam.
बाटे का चल रहा है सर अभी
In the
इसमें भी हम लोग भी कनेक्टेड है हम सर
when the high sediment flooded or the high sediment concentrated flood comes, that can be passed over the spillway by lifting the gates. The special arrangement for the enhancement is considered for this kind of spillways. Ski jump buckets, due to its self-cleansing, supernatural flow and not formation of any kind of hydraulic jump, etc. The ski jump bucket is preferred, but in every scenario, it is not possible when the topography does not, or the
सर हम
terrain.
लोग करने के टाइम में क्या करने का सर उसको प्रेजेंटेशन को इसको ड्रैग करने का कैसे
Filling basin in such scenario is its own challenges. Normal
उसमें जाके
are deep seated, and the fraud number is very low. The dissipation
ये हाँ
stage is also very low, and due to the deep seated basin, there are chances of
you are listening as a delegate.
हाँ वही है
You have to log in
मतलब
as a speaker.
and that has to be taken
Log in as a speaker आप कर सकता है.
by provision of cylindrical end seal, which will facilitate to flush the sediment during the flood operation. When we have to think, when we have to think of tapping the water in Brahmaputra and its tributaries, there are challenges in the narrow valleys to pass the very high amount of flood with the sediments. So in that scenario where the spillway sections are high due to the it is not possible to accommodate the powerhouse due to the geological to accommodate the powerhouse in the dam body. One can go for multi-level spillways or multi-tier spillways. In these spillways, the bottom tier or the bottom opening will take care of sediment as well as the flood, and the upper openings will take care of additional floods. If these spillways are provided with the area dissipation system like ski jump bucket, then its hydraulic is relatively easy. But if the hydrology does not permit or tail water level is high, then the spillway hydraulics become more intricate when these multi-level spillways share the common area dissipator. The glove impact on the design of spillways is one of the very important factor in the design of spillway in the Himalayan region. Recently, on Nanda Devi Glacier failed, and the Rishi Ganga project has damaged totally due to the glove had sudden entry of water or debris flood into the river. What happens here at the base of the glaciers, moraine dams are formed, and these lake when overtops the moraine dams or due to internal degradation, the dam overflows. The water or the debris flood gushes into the downstream river, and on the downstream river, if there is a hydropower project or a dam is there, then that spillway must be able to pass this very high sediment laden flow and a high amount of flood, sudden flood. The spillway must be capable to discharge through it. In Himalaya, there are about 15,000 glaciers and 10,000 lakes are formed below these glaciers. In Sikkim only, there are about 700 such lakes, and due to the glove revision of the flood for many hydropower projects which have already been constructed in Sikkim are going on, it is therefore difficult to estimate the flood from this lake as the scanty data is available, and many a times the breach is unpredictable. At CIDO Paris, during conducting the hydropower studies, we have conducted hydraulic model studies on many projects, and I have tabulated a few projects here where the component of glove is very high. So while conducting the design, while conducting the model studies on such projects, or designing spillways for such projects, we have to take care of GLOF very seriously. The spillway must be able to pass that GLOF, and the deposition of debris in the reservoir must be avoided. In India, dam building activities are going on for many years, and as on date, more than 1,000 dams are more than 50 years old, and about 300 dams which are more than 100 years old. And for these dams, the flood was assessed based on the techniques of that era, like empirical formulas or envelope curves, etc. So as on date, there is a large improvement in flood assessment techniques. More hydrometeorological data is available. So there is one under a drip review, a thorough review of the design flood is taken under this program, and from this it was found that there is upward revision of 50% flood for about 58% dam, and about for 38% dams the upward revision of flood is more than 100%. For example, Kharai Dam in MP, the upward revision is of the order of 929%, and in the Share Tank, it is about 500%. For the major dam like Hirakud, it is about 50%. The dam flood has been revised to 69,600 meter cube per second from 42,000. For these things, this necessitates the need of redesigning the spillway to cater the revised flood. This flood can be catered by some non-structural measures also, that is optimizing the reservoir water level and operational before monsoon, provision of parapet wall for increasing the freeboard over the fire, implementation of early warning system, controlling the reservoir water levels before monsoon. And in structural mitigation or structural measures, the enhancing the capacity of existing dam spillway is major component, and or the provision of additional spillway on the ream or the saddle of the reservoir, on the ream of the reservoir in the saddle, the provision of emergency spillways in the form of fuse plugs or breaching sections, or provision of the spillways where the effective length is increased by using their platforms, repeated platforms like labyrinth spillway, PKVRs, or duckbill spillways are used, or in the narrow valleys, the terrain spillways, etc., can be the option where the divergent tunnel can be effectively used as a spillway. Here you can see the labyrinth PKVR can increase the effective length, and due to this increased effective length, with a low increase in the reservoir height, more discharge can be passed, and this can be utilized. The next component or the next improvement in the spillway design is required for the coastal reservoirs. The coastal reservoirs have the potential to become the major source of fresh water for the countries where the coastline is very, countries like India, where the coastline is very big. World is using only 1/6 of total surface runoff, and other 5/6 of part of runoff is directly discharging into the sea. India has got about 7,500 kilometers of coastline, and about 78% of surface runoff is directly delivering into the sea. Here you can see the very big amount of surface runoff is directly pouring into the sea, that is wasted, and that can be accumulated or that can be stored in the coastal reservoirs. Some researchers in India have came up with the concept like Sarovar Mala across the coastline of India, and that sarovars of which will be constructed across the coastline will be connected with each other, and that is called as Sarovar Mala. A coastal reservoir is a freshwater storage located in coastal waters. It may be river mouth, lagoon, gulf, and that will be fed by the sustainable freshwater flow. For that, an impermeable barrier isolating the freshwater storage and the brackish seawater is constructed. And the highlight means here you can see the quantity of water which is running into the water highlights the fact that enough water is available, but we are lacking in the storage of fresh water. In the world, coastal reservoirs have been effectively used in the countries like China, South Korea, Singapore, and Hong Kong. In India also, we have proposed one project, that is the Kalpsar project, which will be after formation, which will be the one of the biggest reservoir of fresh water in the sea. In this, a 30-kilometer dam is proposed in the Gulf of Cambay, and this reservoir will be fed by 7 major rivers of the Kutch and the Gujarat. Narmada is also diverted through the Barbud Barrage, and it will also fed uh, to the Kalsar project before joining the sea. But constructing a coastal dam has its own challenges, and for coastal spillways, the challenges become more complicated because on the one side it is reservoir and on the downstream it is a sea where the water level is fluctuating on daily basis. So design considerations for coastal spillway involve estimation of design flood, sizing of spillway capacity, tidal variation, storm surge, and wave data, dam safety aspects with tide and wave effects, and proposed spillway, reservoir operation considering inflow, RWS, and tidal variation and storm surges, prevention of intrusion of saline water into the freshwater lake, and energy dissipation arrangement to avoid the entry of high velocity jet into the sea. The reservoir operation, considering the inflow, RWN, and tidal variation and storm surges are very important. You can see here, this is the spillway or the dam. And on the one side, there is a sea. On the other side, there is a lake. When high tide is there, you cannot open the spillway gates, and you can open the spillway gates only when there is low tide or the sea level which will be lower than the reservoir water level. Then only you can open the spillway gates. In monsoon, there are chances that the flood is pouring into the reservoir, and on the other side, the high tide will be there and storm surges will be there. In that case, you will not be able to open the gates. The spillway capacity should be such that it will be able to pass all the flood during the small window of say 5 to 6 hours when low tide will be there. So in this case, unlike the valley storage reservoirs, the inflow will be less and the outflow will be more, because we have very less time to operate the spillway in 24 hours. So normally in coastal reservoirs, the design inflow will be high and design inflow will be less than the design outflow. Coming to the conclusions, as the dam building activity is going on for years together, almost all easy type sites have already been tapped. Major hydropower potential lies in Himalaya. Designing the spillway requires consideration for high seed load, flash floods, growth, narrow valleys, etc. Upward revision of flood for existing dams, designers have to think for enhancing spillway capacity of existing projects. Designing spillways for coastal reservoir poses its own challenges, and for all these scenarios, scanty guidelines are available. So hydraulic model studies play a very important role in optimizing the design and layout of spillways and associated appurtenant structures. Thank you.
Next presenter, please. Again, it's Matthew. Are you here? Next participant, please. Mr. Dan Estimative. Viranjana Malayala. Viraja Malayala. Are you available?
Yes, this is we are available.
Viraja.
Yes, sir.
Viraja, which name, sir? So, Mr. Viraja, you want to play PPT or video, sir? Mr. Viraja, are you hear me?
Yes, I can hear you.
So, I play your video, okay?
Yes, please.
Just a minute, just wait.
If it moves, it breaks. My today's topic is based on this saying. To maintain good health, like people, structures also needs regular checkup. Radial gates and spillways are used for if it moves, it breaks. My today's topic is based on this saying. To maintain good health, like people, structures also needs regular checkup. Radial gates and spillways are used for safe passage of flood without endangering the stability of the dam. Periodic inspection can reveal trends of something serious is developing. Today's presentation will provide information regarding how a comprehensive condition assessment of spillway and radial gates should be conducted. What are the common defects in these structures that we find out from this condition assessment? And what future actions can be taken based on the information we collect from this condition assessment? Spillways are experiencing different kinds of loads during their life cycle, flood, seismic, something else. Factors such as foundation conditions, drainage, joint detail, reinforcement, temperature variation can affect the stability and structural integrity of the spillway. Based on the loads and these factors, potential failure modes are determined, which can be stagnation pressure, cavitation, flotation, settlement, delaminations, faults, cracks, uh, blocked drainage. These potential failure modes then can cause some or in some cases failure of the spillway. In 2017, such failure occurred in one of the spillways, and forensic investigation revealed that there were design inadequacies, but also thorough condition assessment of the spillway was not conducted. In order to conduct thorough condition assessment, we need to do a comprehensive data review. which entails review of the geologic survey, design drawings, design parameters that were used for this spillway, what were the load combinations that were used for the design, was the load combinations and the design criteria in line with the code, review of the construction drawings, uh, size of the rebar, spacing of the joints, uh, thickness of the slab, if there are any dowels between the walls and the slabs. Construction photos can also provide vital information regarding construction. Hydrology and hydraulics reports provides information such as what were the design floods, what is the peak maximum flood, how it was determined, are there any previous inspections conducted on this spillway, if there are any defects found in previous inspections, are steps taken to mitigate those defects. Once the data review is conducted, the inspector should go on field and perform a visual inspection. This can provide us information of the defects that are found on surface, such as negative offset, which is where the uh, downstream slab is higher than the upstream slab, which can be because of um, uplift, cracking, spalling of the joints, condition of the surface drains, if there is any subsidence or misalignments, undercutting of subsurface material. Boroscope inspection can be conducted to see the health of subdrains. Are they clogged? Are they flowing freely? Visual inspection can provide vital information regarding the defects, but only on the surface. What's happening underneath the slab surface or behind the walls or within wall thickness? To understand that, another useful tool that can be used is non-destructive testing. Non-destructive testing is based on two different methods. One is sound-based, one is electromagnetic pulse-based. The sound-based technique is called slab impulse resonance, slab IR, which uses sound waves to detect any voids behind the walls in the subsurface conditions. And ground penetrating radar, which uses electromagnetic waves uh, to find out if there is any voids within the slab or wall surface. Also, if there are any cracks that are found during visual inspection, then how deep the cracks are can also be determined using slab impulse or GPR techniques. If there is any water saturation in the joints, these techniques will let us know. So in order to conduct a thorough condition assessment, we need to do first a thorough desktop study of the data available on the spillway, be it design drawings, construction drawings, hydraulics, hydrology reports, previous inspection reports, geologic survey. Once those are conducted, we should go and do a thorough visual inspection and to understand the severity of the defects that are found during visual inspection, we should conduct a non-destructive testing. With all these different methods, a comprehensive condition assessment of spillway can be conducted. Now, let me provide you some information regarding condition assessment of radial gates. Radial gates are steel structures that are also used for flood release uh, for the stability of the dam. The components of radial gates are skin plate assembly, vertical ribs, horizontal girders, girder and skin plate bracing, strut arm, Tunian assembly. During any of these components, if they are not regularly maintained or periodic inspection is not conducted, as you can see on my slide, failure of this dam gates can occur. In United States, Federal Energy Regulation Commission provides guidelines for conducting a condition assessment of radial gates. For category 1 gates, this type of condition assessments needs to be conducted every 10 years. Category 1 means failure or inability to open or close a gate endangers life, property, or stability of the dam. In order to conduct this kind of inspections, there are 3 components to it: structural inspection, full open test, and electrical mechanical inspection. Structural visual inspection is inspection of all the components of the gate at arm's length. This includes all the steel members, riveted or bolted joints or connections, sides and bottom seals, skin plate, lifting attachments, and when this visual inspection is conducted, defects that are not visible from distance can be found out. These defects can be deflection of the members, missing components, uplift of components, cracks in the steel members, deformations, leakage, and which cannot be found out by doing a visual inspection from the deck. One of the ways to conduct this kind of visual inspections is using rope access techniques. Rope access provides qualified engineer a valuable resource to inspect the upstream and downstream components of the radial gate safely. Deflection, deformation, corrosion are not apparent from a distance. In United States, the rope access techniques are regulated by Society of Professional Rope Access Technicians organization called SPRAT, and internationally it is governed by International Rope Access Trade Association, IRATA. In order to, once the structural inspection is conducted, the second part of structural evaluation of radial gates is full open test, in which the gate is opened to its full extent and closed to see if any kinds of, of, of noise is occurring while opening and closing of the gates, or any kind of raking is happening while the gates are open and closed, are the side rollers moving as they are supposed to, are the gate guides or the guide pads are working properly, what is the condition of the guide pads are, what is the condition of the hoist, if the hoist is made up of chain links, what kind of condition the chain links are. These all things can be found out during full travel test or full open test. When the full travel test is conducted, electrical and mechanical inspection of the gate hoist machinery is also conducted. Mechanical inspection entails inspection of all the gate machinery, hoist chain, gears, reducers. Electrical inspection entails all the electrical components, hoist motor, what kind of readings are readings of current and voltage readings that are taken during the opening and closing of the gates, and are those readings similar to what is provided in the record drawings? Are the voltage on the nameplate are same that uh, are similar to what was recorded during the open and close of the gates? All this information during full travel test and the visual structural inspection gives us a comprehensive understanding of the condition of the steel structure in this case. So to summarize the inspection of the radial gates, and we shouldn't forget that we need to provide uh, or conduct data review in case of radial gate inspections also. And we should definitely find out what is the operational history of these gates. How are there any defects that happened during the prior inspection? So to summarize, we need to have visual inspection, full travel test, and inspections of the electrical and mechanical components of the gates. Once we have all this information available, recommendations can be made in the gate inspection report regarding the health of the gates. The recommendations usually are provided in three different categories: critical dam safety, potential dam safety, and for items of general maintenance. Sometimes an analysis needs to be conducted to find out if the uh, what was found in the field can have any adverse effect of operation of the gates. USACE Engineering Manual 584 and ASCE provides criteria for this kind of structural analysis. So spillways and radial gates are considered as vital appurtenant structures of a dam. Their health and safety is very important for operation of the dam. Today, through my presentation, I hope you were able to get some understanding of what entails a comprehensive condition assessment, how it should be conducted, and what are the typical defects that are found during condition assessment of a radial gate and spillway. Thank you for providing me this opportunity to present in front of this esteemed audience. Thank you.
Mr. Dan Estimatio is available here for present. Dan Estimatio. I think he is not available.
Hello, this is Adit Joshi. I had the last presentation for condition assessment of riddle gates in spillways. If any member here have any questions, I will be happy to answer based on my presentation.
Mr. Joshi, what's your time to present? Mr. Joshi,
Hello, the last presentation that we just had uh, in introduction to structural condition evaluation of dam aquatic
okay.
structures.
Viraja Malayala. Huh?
Yes, that was uploaded by my colleague
Yes,
Veeraja
yes.
Malayala.
So you
Yes,
want to run PPT?
no, uh, I observed the presentation. I just wanted to see if any of the participants in today's session had any questions on my presentation. I will be happy to answer.
Okay. If any question, please.
Hello.
I see there is one question coming up. How do one increase the spillway capacity of the existing dam that were built 50 years ago? Um, there is one example in here in California where we have Folsom Dam, and where we have an existing spillway with radial gates, and a study was conducted based on the current PMF, uh, and was found out that the discharge capacity of the dam is not adequate. In that case, uh, a separate spillway was constructed on the uh, on a different side of the dam with its controlled structure, and to increase the capacity of the spillway and the discharge capacity of the dam. So that is one way of doing it. If there is that opportunity available, then a new spillway can be constructed and designed to increase the discharge capacity.
Hello. I would like to add something here. If the existing spillway is ungated one, then we can use labyrinth weirs or PK weirs to increase the effective length of spillway, which will increase the discharging capacity of spillway. If the valley is narrow and we have scope to provide the tunnel spillways, then additional tunnel spillways can be provided. In case of concrete gravity dam, some overtopping can be allowed, of course, taking due precautions on the down.
പാച്ചമോളെ പാച്ചമോളെ കുറച്ചൊന്ന് വീഡിയോ എടുക്കണേ എൻ്റെ ഒരു 10 മിനിറ്റ് വീഡിയോ എടുക്കണേ.
Yes, no, we can start.
Yeah, I'm Amitabh Tripathi. Can I start now?
Yes, sir. Please.
Yeah, good morning to all the distinguished panelists and the delegates who have joined virtually. I am Amitabh Tripathi, Senior Executive Director from WAPCOS, and on behalf of my director, Mr. for this technical session on rehabilitation technologies to enhance the safety. And perhaps this is the most um, opportune time. Of course, last 1 year we could not hold this conference, but now it is really heartening to know that we are holding this very important conference through hybrid virtual media to invite suggestions and case studies and experiences to very important aspects of the sustainable development of dams and river basins. And today there are six papers lined up and slated. And looking at those papers, you can very well see that it covers a variety of aspects related to safety. And they will definitely bring a lot of new perspective and insight based on the respective experiences while handling these issues as described in these papers, and will definitely throw some light into developing a robust mechanism in the area of the dam safety in various geographical regions. And one more thing before I invite the speaker is that there are number of almost 47 to 50,000 dams over 8 countries, where India ranked third on that. And in Indian context, almost 20 years. So there is a pressing need, and it in fact is imperative that we have a robust mechanism and framework with inputs from all over the world to develop guidelines and the experiences for the dam owners to mitigate the adverse impact of the aging dams, and as well as chalk out a roadmap based on the inputs and experiences for the future generations, because more and more dams will age as we proceed. And at this juncture, in fact, we are at the inflection point right now. And with these type of conferences and the technical sessions, definitely it will pave way to formulate a very good and wide-ranging guidelines and strategies for the dam owners to address these issues holistically. So with this, I would request the first speaker to present, and then we can go through all the papers, and then towards the end, if there are any questions from delegates or anything, so the respective speakers can always respond to that. And I am pretty sure that the kind of papers we have, we would be in for a very informative and very meaningful session today. And now I invite the first speaker, I think from Uganda, to present the paper and enlighten us with his experiences in the dam safety. Over to the speaker and virtual medium to take forward. Thank you.
Distinguished guests, ladies and gentlemen, greetings to you all from Uganda. I'm called Darren Edson Mukwanason, a civil engineer working with Uganda Electricity Generation Company Limited, and it's really my pleasure and honor to be presenting the risk-based stability evaluation of the upper spillway middle pier for Isimba hydropower plant in Uganda. The presentation layout, we shall have a brief introduction on Isimba hydropower plant, and thereafter I'll walk you through the risk-based evaluation, where we shall have an appreciation on how risk can be used in the analysis of the pre and post-construction defects. For this paper, the vibrating pier was used as a case study, and I believe we as dam operators and dam professionals will be in position to learn a thing or two from the recommendations before we go into the conclusions. Isimba hydropower plant was commissioned on 21st March in 2019 and is located on the White Nile in southern Uganda. It has a total installed capacity of 183 megawatts, that is from 4 generating units, and it was designed for a 10,000-year flood of 4,500 cumecs. It is currently operated by Uganda Electricity Generation Company Limited, and it's in its defects liability period. Inset down here, we have downstream view of the hydropower plant, and up here in the photograph, we have the aerial view showing the components of the dam structure. The power plant adopts a spillway as the main flood release structure, whereby we have the lower spillway and the upper spillway. The lower spillway is sometimes called the submerged spillway, and it's mainly used for sediment flushing. And during excessive flood conditions, it supplements the upper radio gates or the surface spillway in flood control. The surface spillway or the upper spillway is used in the day-to-day regulation of the reservoir water level. And in the photograph here, you can see the gates were partially open. And in between here, we have the concrete pier understudy. This is a cross-section of the middle pier of the upper spillway. And as you can see, we have a stilling basin, the spillway pier, we have a radio gate for flow control, and then also strain gauge 8 as one of the instruments in the concrete weir. Strain gauge 8 is mainly used for the vertical strains or response in this concrete weir. This side we have the reservoir or the upstream. So flows go through the radio gates, then into the stilling basin. The main purpose of the stilling basin is for energy dissipation, and that is to break the water velocity to avoid erosion of the downstream riverbed. During the initial impounding, here we are seeing the action in the stilling basin. There's a lot of turbulence and overturning of water. This creates a hydraulic shock onto the middle pier. Here, both openings were releasing water, and that's what led to the spillway-induced vibrations. During these inspections, we realized that the pier was moving or oscillating abnormally. To further investigate the situation, instrumentation data results were compared for the strain gauge installed in the concrete weir. And as you can see from the graph here, the plot in red shows the response for strain gauge 8. And as you can see here, we are having a rapid response to impounding, as compared to strain gauge 7, which is also installed in around the same location, but for it, it's having very minimal response to impounding. These two observations prompted further investigations in order to assess the risks. So for the risk-based evaluation, we've looked at the visual inspections where we had the inception of this problem. We further went ahead to do an instrumentation check where we found erratic vertical displacement in strain gauge 8. So in order to kind of assess the hazards or risks the dam operator was facing, we constituted a dam safety risk workshop. Now what happens here is we have a dam or project risk register where we identify risks, quantify them qualitatively or quantitatively, and thereafter try to grade them. So from in here, we realized two potential failure modes. There was a possibility of pier flexure failure that would be directly linked to the vibrations, and then there is also possible uplift of the stilling basin. And this was in a way related to the erratic vertical displacement of strain gauge 8. As a step forward, a preliminary analysis was done by the consultant in order to verify the stability of the top weir, assuming a horizontal crack, and then also to determine the perennity of the pier under the vibrations. For the perennity, we are talking about how long the pier can stand if at all it was subjected to these vibrations continuously. And therefore, a 3D model was used, which is here. And this is mainly to replicate the actual structure. So here we are having a digital representation of the spillway. We have two vertical walls of 2.5 meter width. And then also here we are seeing the elevations from the foundation up to the spillway crest. A number of simulations were run by the model, and the results were that the pier could stand for 42 years under continuous spillway operations. So we are talking about 42 years under these adverse conditions. The only setback or risk was that this analysis was based on an adopted hypothesis. That means we are missing out on the actual build situation. And as we all know, there are so many defects that are always attached to poor workmanship, poor installation procedures, and sometimes omissions, which prompted a vibration test. This vibration test was meant to facilitate a more informed or in-depth stability analysis using actual site data. This is the layout of the vibration test, and it was aimed to collect vibration characteristics. Here we're talking about the vibration acceleration, the vibration displacement, and pressure pulsation. And as you can see up here from the model that was used, this is the layout of the 34 sensors that were used by the contractor during the execution of the test. Thereafter, numerical simulations would be undertaken in order to evaluate the vibrations, and thereafter have vibration reduction measures proposed. That's if the evaluation, in the evaluation, it was found that these vibrations are out of range or they're in the alarming zones. But from the test study, realized during the execution of this test, would have to release flows of up to 2,200 cumecs. And that corresponds to the 20-year flood of the Simba. And with this came a 2-meter rise in the tailwater level, which posed serious risks to the downstream communities, the upstream communities, and then also the dam owner. For the risk management, Uganda Electricity Generation Company Limited, which has safety at the heart of its core values, used a risk-informed approach in order to identify, assess, analyze, evaluate, and mitigate these risks. And part of the mitigation measures included reservoir bank surveillance, public sensitization, stakeholder engagement, and then also vibration monitoring. After thorough mitigation of the possible risks, the test was carried out under strict coordination, and the table on the left shows the procedure that was used in the execution of the test. Like I showed you in the previous slides, the upper spillway has two main openings, one on the left and the other on the right. So we started at an opening percentage of 15% and went all the way 30, 45, 60 to 75 with 3.5-minute intervals. During this time, we're still recording the parameters of vibration acceleration, displacement, and pressure pulsation. And as you can see from the graph here, we have the hydrograph extracted from our SCADA system. The first hydrograph peak depicts the flows during simultaneous opening of both gates. Then the medium peaks here are the flows during the partial opening or individual opening of the left and right gates. I picked out two graphs here, representative graphs, to kind of explain what transpired during the test. So here we are having the displacement curves and acceleration curves. And as you can see, these graphs or plots are for different locations and different parameters. We are having the displacement in micrometers, then also acceleration on this other end. From the preliminary test results, we realized the maximum displacement was observed at elevation 1,044 meters above sea level at about the topmost part of the middle section of the pier. The recommendations: in the interim, the upper radio gates could be operated at less than 70% opening. Reason being that the actual stability analysis was not yet ready, and it was only at the 70% opening that we were sure that the vibrations were still within range. Then also during flood conditions, we advise simultaneous operation of both gates in order to have balanced hydraulic conditions in the steering basin. Regular visual inspections need to be carried out for the spillway, and this is meant to capture or arrest any defects or faults that may not be captured by the instrumentation. And for the case of the pier, we recommend additional instrumentation to be installed, such as the 3D accelerometers for these intense vibrations. Given the fact that the upper spillways are always in operation for the day-to-day regulation of the reservoir water levels, this would be very good analysis data. Then a stability analysis should be carried out by the contractor using as-built data. The as-built data combined with the vibration test parameters that were collected would help the contractor carry out an in-depth stability analysis. Thereafter, it would go through a series of expert reviews. But what this means to the operator is that it would help us institute a dam safety risk workshop where we would have to review the risks and try to reduce them to as low as reasonably possible. Then dam operators should adopt a risk-based evaluation of post-construction defects and snags. Thank you very much for your kind attention. I wish to hear more from you during the discussions session.
Thank you, Mr. Mukan Wasan, for this very informative case study from Uganda. I feel that the highlights of his presentation was the monitoring and surveillance to early detect the potential risk involved, and the robust instrumentation can really go a long way to effectively devise a mitigation plan, and also some framework in the transfer of asset from during the construction stage to the eventual owner of the asset. I think, in my opinion, these are the three key highlights, besides using a very good software to numerically analyze the problems faced by them. And thank you so much for this very informative presentation. And now we may request the next presenter to go ahead with his presentation. I think the voice is not no, clear. Mr. Santosh Kumar, can you unmute?
Sir, am I audible now?
Yeah, you are audible, sir. And just before you start, we have a total 90-minute session. So I would request that maybe around 10-12 minutes would be the best so that we can cover and then we can have discussions towards the end. Thank you.
Obviously, sir, obviously. So my name is Dr. P.T. Santosh Kumar, Deputy Director, Construction Materials Division, Kerala Engineering Research Institute of Irrigation Department, Government of Kerala, India. So my paper for presentation is Innovative Methodology to Control Seepage of Pathalakundu Earthen Dam in Kerala, India. So the contents for my presentation is salient features of the dam, problem statement, stage-wise solution to the problem, conclusions and references. So in the salient features of the dam, it may be noted that the height of the dam is 17 meters, that means water height. Then length of reservoir 143. Then gross storage capacity is 1.5 million meter cube. And reservoir bottom width is 84 meters. As well as this is an earthen dam and barrel is provided at the bottom for irrigation purpose. And a sluice well is also located at 37 meters from toe to the upstream side. Location is in Kerala in Thrissur district, India. So the problem statement is as follows. The dam was commissioned in 1978 and is not functional effectively due to excessive seepage. That means if the water is filled up to the FRL level, we can see incessant flow through the canal leading from the barrel. So this seepage was not able to arrest from 1978 to till 5 years back. And an effort made to control the seepage, and that is being described in this paper. So when the reservoir is getting full, whirlpools are also observed. And at that point of time, that means around 6 years back, we have proposed two solutions to the problem. Number one, extension of upstream blankets, curtain wall, scarification of upstream earthen portion, and refilling with necessary compaction with ripraps, obviously. That is stage number one. And stage number two, to focus on the barrel and well. That means barrel and well. And first part was completed and observed that still that incessant leaking was observed and dam is able to fill the water completely. So the second stage work started. The details of second stage is as follows. We can see that is 84 meters long and having a width of 0.6 meters with varying depth from 1.5 meters in the water side and 1.2 meters in the toe. And it is not possible to enter through the barrel. And this sluice is provided 37 meters from the toe end. And the diameter of the well is 1.6 at the top and 1.2 meter at the bottom. So it is not possible to repair the well as well as the sluice or as well as the barrel opening because it is always wet and the mixes blended with epoxy and such quick fixes are not possible due to this effect. So a new technology was thought. It was similar to a push technology. That means a composite barrel, that means another material fabricated from outside and pushed through this already existing masonry barrel so that the possibility of leakage arresting is possible. And the space between the barrel and the is proposed new composite barrel is to be filled with mortar, quick setting mortar and quick setting grout. That was the objective. And with that objective, we have the work. And the space between the already existing barrel and the new barrel, that is composite barrel, provide a PVC of 7.5 centimeters to inject the mortar as well as grout, and a free flow grout was used in between the stainless steel composite barrel and existing RR barrel. It may be noted that the top of the barrel is covered with precast concrete slabs. So, how the method worked? Each 6 meters long, the barrel was placed inside, and then second 6-meter barrel was welded to the tail end of 6 meter and then pushed inside. And after pushing completely, then the third one was welded, and the pushing goes on till a meter length. That means up to the downstream end is reached. And for easy movement, rails were fixed on the bottom of the proposed barrel, and using cranes, push was done. Video of this push and details will be shown at the end of this PPT. And after this motor was placed in between the barrel steel and the existing masonry barrel using pressure and using pressure of 2 atmospheres. And after that, bentonite earth grouting was done from the top to see that the tributary area around the barrel is fully grouted and leak proof to arrest the lateral seepage of water out the barrel. And the barrel, that means proposed composite barrel, need to be checked the structural as well as hydraulic parameters. And the structural part is done using Stat Pro, latest version. Model, these were the forces considered. That means it was assumed that the load from a angle of 60 degrees with the horizontal will be passed on to the top of the barrel. Considering that the precast slab does not take any load on the conservative reasons. And the sides of the barrel were applied with a lateral earth pressure found from soil analysis, and the modulus of subgrade reaction of 18,000 kilonewton per meter applied at the bottom of the barrel as per soil tests. And a 1 meter length of the barrel was considered for analysis, and it was found that the barrel is safe in resisting stresses. This is the well, this is the Patadakondu Dam, and we can see the view of the model in Stat Pro analysis is as following. And the stress contour from the Stat Pro for the composite model is as follows. From this, it is clear that the stress within its, so you can obviously see that the stresses are a maximum of 60 Newton per millimeter square, whereas the permissible one is 250 Newton per millimeter square minimum. And for the hydraulic reason, piping was checked using Bleek's creep coefficient, considering the type of soil and assuming a Bleek's creep coefficient of soil as 5. And L is the creep length, H is the head loss. So for the head loss of 0.6 meters considered at the level of the bottom of the barrel, the creep length required is 72.8 meters. This is less than 8 meters. that is without curtain itself, this is safe. And this assumes that the size of the particle of the soil is not more than 2 millimeters and the velocity of water is 5 millimeter per second through the porous medium. And the limitations of that exist here also. And we need to check for the discharge through the barrel and corresponding eye cut. As per the Department of Irrigation of Kerala, a duty of 60 acres per cubic is considered, and as the eye cut for the dam is 150.7 hectares, the required discharge shall be 150.7 divided by 857.2, that is 0.18 meter per second. And as per CWC norms for in the permissible velocity is found from Manning's formula, and it is obtained as 1.08 meter per second. And from this, the discharge was obtained as 1.8 meter cube per second, which is more than 0.18, and hence it is deemed to satisfy the discharge requirements also. So in the conclusions, for the first time since 1980, the dam has been opened on 21st August 2019 at 1254 meters water level, FRL, and leakage was seen to be within various limits, almost negligible. So this method has replicability scope in similar dams. Aurora KR, CWC guidelines for safety inspection of dams, IS 383-1121, 1905, and Kerala Engineering Research Institute, KREPG, which is opened in 1960 by the then Prime Minister Jawaharlal Nehru. So this is a reputed firm of Kerala State Government of India, and is now open with full functional with full reputation. And this is IS 17894-1975, and this is the presentation part. You can see photos of the grouting from the top. So this is the downstream side. You can see the upstream side. There is in the upstream side. You can see this is the composite stainless steel with MS plate put inside. This is the pipes which is being placed up. So the video of driving the cable inside the existing masonry barrel is coming now. So this is the upstream side of the dam. The temporary bund was provided to limit the ingress of the barrel is being pushed inside. So with this, I am concluding my presentation on innovative methodology to control seepage in Pathanakuntu Dam in Kerala State. Thank you, one and all.
Thank you, Mr. Santosh Kumar, for this very nice presentation. What we could understand from your paper, what it indicates that the importance of the regular O&M beforehand to first minimize the problems, and secondly, not only the identification of the source of the seepage correctly, and then also weighing various alternatives possible specific to the case, like in this case, the push technology by placing stainless steel barrel owing to the smaller size of the RR barrel. That was also quite clearly explained by you. Besides the two component structural part in StatPro and hydro part in this. So all in all, it was a very insightful paper, and it can be definitely replicated in similar situations elsewhere. Thank you so much for your presentation, as giving us the details. And now we may proceed to the third presenter for making his presentation.
Thank you.
മ്യൂട്ടാണ് കുഴപ്പമില്ല. മ്യൂട്ട് ചെയ്ത് മ്യൂട്ടാണ് കുഴപ്പമില്ല. അൺമ്യൂട്ട് വരും.
അപ്പോൾ വീഡിയോ on തുടങ്ങി.
कोई भी पोस्ट करते हैं.
इसको बोलना है
हम लोग तो इसमें ये अभी चल रहा है.
ये अभी चल रहा है सर.
ये अभी चल रहा है.
Good afternoon to all. Sir, I am audible?
Yes, sir.
Yes, sir, I am continuing then. Good afternoon to all. Myself, Vigneshwaran. I'm working as scientist in Central Water and Power Station in Pune, in India. So today my topic of presentation is seepage control in masonry gravity dams through dam body grouting, and along with that a case study is also be presented. So coming to the presentation, so first we want to know what is seepage and leakage. So the masonry dams especially exhibit leakage and seepage due to poor quality construction, leaching of cementitious material, cracking, design deficiency, and aging effect. Due to the age of the dam also there may be leaching may be there, and due to some other problem also there may be leakage and seepage is there. So the leakage and seepage affects structural stability of the dam due to development of high pore pressure, because the leaching material block the porous drain, and because of the leaching there will be a reduction of mass density, and because of all this there will be a reduction in the strength. To overcome this, to restore the structural integrity of the dam and to make the distressed structure serviceable again, various methods are adopted, and either in one or in a combination. It may be facial, it may be of rehabilitation measures, it may be repair. So the objective of rehabilitation is to reinstate the structural integrity, improve durability, prevent leaching of materials, and mainly the restore water tightness. That is what seepage and leakage does, and to improve the appearance of the structure. So coming to the grouting, what is grouting? So grouting is basically the process of filling up voids, the material that leached. So the process of filling up voids or cavities in any part of the system in order to consolidate mass into one integral unit. Because of the leaching material or because of the seepage and leakage, the structure is disintegrated. In the process of grouting, it is integrated into one mass. So integral unit by means of injection, cementitious or epoxy material in fluid state under pressure with sufficient viscosity to penetrate into the unit to a uniform distance around the point of grouting. This is the general point of grouting. So what are the properties of grout? So the grout should be fluid enough to reach the interior part, and it should have a minimum bleeding and segregation. It should have low shrinkage, so that after grouting it doesn't detach from the parent material. It should have adequate strength after hardening, and it should have no harmful compounds like acidic in nature, something, etc. And at last it should be durable. The grouting we have done, it should be durable for minimum of 20 to 50 years. So coming to the next slide. So why dam body grouting is required? So grouting of dam body is one of the most effective cures for most of the masonry dams, and has been successfully implemented for reducing seepage in so many dams all over the world. And the one of the major part is presently there is no specific BIS code for how the grout mix has to be designed. So in our CWPRS, we have designed a grout mix based on the parameters collected from the lab and from the site, and we have designed the grout mix and we have implemented it. So the grout mix design is dependent on numerous parameters like pattern, size, continuity of the cavity fissures, quantity of seepage water flow, desirable enhancement, and what is the desirable enhancement of mass density towards improvement in strength requirement of dam body. So there are number of dams grouted in India. Some of the dams are Varasgaon Dam, Temgar Dam, Vatsa Dam, Damini Dam in Maharashtra, and Pagara Dam, Satyashagar Dam in Madhya Pradesh, and Hemavati Dam and Takale Dam in Karnataka. So how the material for the grout mix design has to be selected. So the grout material depends upon the workability, the dimension, stability, adhesion bond with the base material, chemical resistant and strength properties. And one of the major parameters is it should be able to negotiate with the existing aggressive condition without dissolving seepage water, because already the dam has some seepage and leakage. If the grouting is not done properly, without setting, the grout materials wash out from the dam, and it should attain the initial setting reasonably fast without dissolving in the seeping water. And it should have a strength. It should have must have strength in compression. It should have strength in tension, shear, and flexural. And it should be thermally compatible with the old concrete or old masonry. And the grout mix can be selected on basis of evaluation of properties in the laboratory. That I will explain in the detail. And there are various type of grout. Like we can use like fly ash, pozzolana, sand, cement. It can be cement-based conventional method. It can be cement-based quick set for if the seepage and leakage is very high. And it can be chemical grout for sealing of particular condition. And in extreme cases, we go for epoxy resins for underwater grouting also. So these grout mix designs has been selected based on the laboratory experiments. In our lab we have done some very elaborate laboratory tests like flowability test by Marsh cone apparatus. So this is the Marsh cone apparatus to find out the fluidity, how fluid is the grout material, and settlement and segregation test to understand how much the grout settle after a particular time, and what is the percentage of settling time, and what is the jellification test is to know that what is the initial setting of the grout, and pH value to know whether it is acidic or alkaline in nature, and the compressive strength. So this is the jellification test to know what is the initial setting time, whether it is settles after 1.5 hours or 2 hours or 1 hour. And based on the condition, if you want the grout to settle within quick setting for about 30 minutes or 45 minutes. And this, you can see this is the grout we have put for compressive strength evaluation. It is very fluid in nature. So after a 1 or 1.5 hours, the grout becomes a gel. It becomes jellified and becomes attain its initial strength. So these are the laboratory tests. After this laboratory test has been confirmed, we conduct trial application of grouting in masonry blocks. For this, we have constructed about 1 cubic meters in 1 meter into 1 meter into 1 meter of masonry cubes. These masonry blocks has been constructed using a density of around 2000 to 2100 kg per meter cube to simulate the site condition. So from the laboratory test, the ideal cementitious grout mix has been selected after numerous combinations, and the grout has been carried out. You can see from the picture that this is the blocks, and we have grouting using the grout mixer pump, and this is from free flow grouting. So in this year, pressure has been also been applied up to 2 kg per centimeter square, and we have grouted the blocks. And after these blocks has been grouted, we have given sufficient strength, and non-destructive test has been constructed on these masonry blocks. The non-destructive test has been constructed using the pulse velocity method, and this technique gives mechanical ways. So the basic idea behind this non-destructive test is the pulse velocity method is established that the velocity of pulse of compression waves through a medium depends upon the elastic properties and density of the medium. This is using the Pandit equipment, and these tests are carried out before and after grouting. So before grouting, we have conducted the test throughout the block, and after grouting also we have tested, and we have found that after grouting the masonry has improved. The strength of the masonry is improved because of the pulse vessel velocity is more than 3000 meter per second. And we have also conducted water loss test before and after grouting. So before grouting, you can see that the known quantity of water we have let into the masonry blocks is free flowing, and after the grouting after a sufficient curing time we has given, and the water loss is very minimum. That is, no, we can say this, it's very negligible. So in this we can see that the significant reduction in leakage of water takes after the grouting. So these are the two non-destructive tests, and after this, to evaluate the efficacy of grouting, we have extracted cores. So these are the cores of 30 centimeter dia cores have been extracted, 30 centimeter into 60 centimeter length dia cores using our core drilling machine. You can see here the two cores that we have separated, and these cores have been capped, so that because the bottom portion is uneven. After this, it has been tested in our 210 compression testing machine. So coming to the next part, what is the case study? So here we have taken the case study of Domihira Dam. It is a dam in Maharashtra, in Palghar district in Maharashtra, India. So it's a composite gravity dam with earthquake motion of about 700 meters and masonry non-gated oogie spillway of length 58 meters. So the problem here is, after the first importment of reservoir in 2010, heavy seepage has been observed at the reservoir level. The seepage was there in the spillway portion, construction joints, lift joints, and the right and left trunk walls. So this is the photo showing the leakage of the dam. You can see in the spillway there is a enormous leakage is there, and in the flank walls, right and left flank walls also, there is a enormous leakage is there. So this case was referred to CWPRS to control the seepage. So we have done the grout mix design for this based on the materials such as the OPC cement, 43 grade OPC cement, and we have added fly ash for improving the durability of the durability of the grouting, and silica fume to increase the strength, and admixtures. We have added 3 admixtures, like admixture for binding of grout mix to the surrounding masonry we have added, and accelerated for enabling the setting of grout mix, and additive for improving workability of the grout mix. So this combination we have tried about more than 100 combination, like varying the cement content, fly ash content, and this admixture content, and this has been mixed in our lab using the grout mixer. So this grout mixer is used because we have to mix these ingredients in at least in a speed of about 1500 rpm, so that this mix become a colloidal nature and the grout sustains. So the final design of cementitious grout mix has been taken by CWPRS during December 2018, and numerous trials of using various proportion of cement, fly ash, silica fume, and 3 type of admixture from various manufacturer has been tested. So based on the selected mix, some sample masonry blocks what we have showed has been grouted and tested. So from this grouted from all this grouted mix, we have selected one mix based on the which is optimum for the present site condition, and we have given that mix to the Domihira Dam Authority so that they can grout and the seepage can be reduced. So this is the grout methodology we have suggested for the dam. We have suggested to drill inclined horizontal holes. You can see this; these are the inclined horizontal holes with in a spacing of about 5 meter, and in horizontal spacing of 3 meter, and a vertical spacing of about 1.5 meter in a staggered manner. So in this grout methodology, we have given the what should be the pressure and what should be the duration when it should be. We have given a detailed methodology so that there is no other adverse effect. So the grout is carried out from the inward to the outward pattern. So you can see this is the diagram of the Domihira Dam. In this, you can see that from the upstream portion, about from the 1.5 meter, you can see this. The grouting has been, the grout holes has been done, and the grouting has been done. In addition to this, there is a hole has been drilled from the top of the dam, and a grouting has also been carried out. So this is the picture showing the grouting carried out. So we can see this in the left hand side, the grouting from the top of the dam has been carried out, and from in the right hand side, you can see this the grouting from the upstream face of the dam. In the downstream face of the dam, you can see this, and the holes has been drilled. And here also we have we ascertained that the grout mix is proper, so that we have taken the samples from the grout mixer whether the grout mixer is rotating at a proper speed that around minimum of 1500 rpm. We have taken the cubes for the compressive strength measurement, and we in the site also we are checking about the what is the marsh cone value, whether the grout mix is fluid, and whatever we have designed in the lab is actually we are achieving in the site conditions. So based on these parameters, the dam authority has grouted the whole dam from the upstream, from the downstream portion, and from the top of the dam. So you can see this. This is the picture showing after the picture of the dam after grouting. So coming to the conclusion, the grouting of the spillway portion has been completed in 3 stages, and the total consumption of cement bag has been observed to be about 20,000 bags, and with a grout intake of about 1,532 metric ton. The total cement intake per cubic meter of dam masonry worked out around 1.92 bags per cubic meter. This is almost equal to what we have find out in our laboratory condition using the trial blocks. And the dry grout intake is about 146 kg per meter cube. The mass density of the dam masonry has enhanced by more than 5%, resulting in the improvement of structural safety of the dam. And due to the grouting, the seepage/leakage through the spillway portion has been observed to be completely stopped. Even after the 2 monsoon season, now the seepage and leakage has been very minimal. The overall seepage rate has reduced from 300 liter per second to about 60 liter per second after successful grouting of the spillway portion. So this is the photos we have taken about after the initial grouting. The flank wall grouting is in progress at that time, so there you can see some leakage is there, but in the spillway portion, the leakage has been completely stopped. So coming to the conclusion, dam body grouting using proper mix design is very important and effective tool to control seepage and improve structural safety and of the distressed masonry dam. In most of the cases, the dam body grouting fails because the grout has not been designed as per the actual site condition. In this case, we have designed actually based on the site condition, and we have conducted a numerous trials so that it has been effective and it has solved our purpose. And design of cementitious grout mix is important and necessary be done by conducting laboratory tests on different materials. Here also we have conducted both laboratory tests and using the field trial box. After conducting the suitability test in laboratory also, many mix proportion, a suitable design mix is arrived for carrying out grouting in the field, and that has been carried out. And due to grouting in masonry spillway portion of Domihira Dam in Maharashtra, the seepage leakage through the spillway portion has been observed to be completely stopped. So our scope has been, our motive has been done so that the grouting has, the leakage is reduced to a bare minimum. Thank you.
Thank you, Mr. Vigneshwaram, for this wonderful presentation. And what we understand, it clearly establishes the importance of very extensive laboratory testing, as you rightly mentioned, regarding the proper design of the design mix of the cementitious grout mix, specific to the site condition, and also extensive laboratory studies as carried out in this case for assessing the suitability of the grout system by varying the ratio of ingredients such as cement, fly ash, silica, and so on. And I think this was very informative, and all of us, listening and going through this paper would clearly understand the importance of the correct design of the design mix, and as well as a very extensive laboratory testing and other requirements to arrive at the design mix. So thank you so much for this paper. And now we may request the next presenter for his presentation. And the time limit, I think we have another 35 minutes to go. So I would request the presenters to adhere to the allotted timeline accordingly, maybe 10-12 minutes each. Thank you so much.
Hello, everyone. My name is Nagesh Malyala. I am a technical leader with AECOM. I work in the Sacramento office of AECOM. So the topic I want to present is on Argonaut Dam. The title of this presentation is Innovative Remedial Design of Barrel Arch Dam. A brief history of the dam. The dam was constructed by a guy named John Eastwood in 1916. John was involved in similar dams, around 10 of them in California during the same time frame. The purpose of this dam is mainly to store the mine tailings. The dam is around 400 to 450 feet long and 46 to 50 feet tall at the highest point. There are 13 contiguous arches, and the buttress walls of these arches are braced by tie beams, and 6 of these arches are basically braced with these tie beams. The location of the dam, you can see in the map. It is in Amador County in California. It's 1 mile north of the city of Jackson. And the city is basically on the downstream side of the dam. Historical activity. Argonaut mine, which used to be in operation between 1850s and 1942, is the center for gold mining. They used to process the ore there. The tailings were then hydraulically transported and impounded in large ponds, which are basically filled in the natural depression. So the concrete arch dam was constructed to prevent the tailings from entering the Jackson Creek, which flows through the city of Jackson. There used to be a spillway as a part of the dam at the left abutment, which has been removed or demolished since then. That particular area is currently occupied by a highway, as can be seen in the picture here. So over the past century, the dam has been neglected in terms of inspections and maintenance. The Army Corps and the Environmental Protection Agency performed the structural integrity evaluations of the dam. The results showed that the dam failed to meet the minimum engineering requirements for seismic stability. So AECOM was brought into the picture by California Department of Toxic Substance Control to do retrofitting design project. These are some of the pictures of the pre-remediation condition of the dam. You can see the arches. The pipes are basically acting as spillway, the front view of the dam and the side view of the dam. So AECOM scope of work involved completing site geotechnical assessment, completing alternative studies, and a design of preferred alternative, and then providing construction support. So on the site geotechnical assessment, the upstream tailings have been investigated by Department of Toxic Substance Control in 2014, prior to the arrival of AECOM on this project. The downstream side has been investigated by AECOM. As a part of that, 10 borings and 5 test pits were completed in 2016. 6 of these borings were performed within 5 to 15 feet from the base of the buttress. And the depth of those borings varied between 15 feet to 36 feet. 2 piezometers were also installed in the borings to measure the groundwater fluctuations. Again, 3 test pits were excavated near the base of the arches. All the test pits were advanced to the bedrock. So the results of the investigation identified that the upstream tailings are very loose. They had low shear strength and are potentially liquefiable. The tailings do contain arsenic, cyanide, and other heavy metals. The SPT blow counts were in the range of 1 to 5 blows per feet. The downstream identified that the hard rock is at very shallow depth. The soil overburden was measuring around 1 to 5 feet in thickness, predominantly silt and clay, and there is some toxic contamination in the downstream end tube. So the second step of the AECOM scope of work is to develop alternatives. So multiple alternatives were developed, mainly to address the couple of major deficiencies of the dam. So the first one is the stability, to address the seismic stability. And the second one is for stormwater management. And subsequent to that, after all the alternatives were developed, the preferred alternative was selected, and then the design was completed, and then construction. So as a part of the alternative study, we looked at 4 different alternatives. The first alternative was titled as a reinforced concrete buttress wall with gravity arches. As you can see in the top left-hand picture, the existing dam is there, and then the reinforced concrete buttress with the gravity arches was installed to the downstream face of the existing dam to provide the buttressing effect. And this construction was proposed to be completed using vertical mass gravity arches. The preliminary construction cost is estimated at around 10.2 million. So the second alternative is a mass concrete gravity dam, wherein we fill in the arches with mass concrete, as can be seen on the top left-hand picture. The construction cost was estimated around 11.8 million. So the alternative 3 is a roller compacted concrete gravity dam. This is very similar to our alternative 2, but the only difference is here, instead of using a complete mass concrete to fill the arches, here you are using roller compacted concrete, which is constructed in lifts, as can be seen in the hand-drawn picture on the top, to provide like a 1:1 slope, approximately 1:1 slope. And then the annular space between the embankment, the roller compacted concrete embankment, and the arch of the dam is filled with mass concrete. So this alternative was costed at $9.4 million. So the fourth alternative that was evaluated is earthen embankment. So downstream, we proposed a earthen embankment, which is shown in the green color. So you build it up in stages, and the annular space between the arch of the existing dam and the earthen embankment is basically filled with cellular concrete. So this is a composite combination of the earthen embankment. And this estimate, the estimate came out around $6 million. You can see that as doing that, we are also taking care of the drainage system. We installed the geodrain fabric, which basically went along the downstream face of the wall and underneath the embankment, underneath the proposed embankment on the bedrock, on the top of the bedrock, which basically connected to the subdrain pipe system. And from there, it connected to an exit drain to get it out of the site. So the recommended alternative was further developed based on, was basically selected. It is based on the costs. So the earthen embankment, which was costed at around 6 million, came out to be the lowest cost, and that was selected as a preferred and recommended remedial alternative. So the construction of this one was completed in 2 phases in the summer of 2018. The scope included removing the foundation soils and the weathered rock within the footprint of the earthen embankment, and then laying the under-drain system installation, and then constructing the composite earth and cellular concrete embankment. And the upstream was basically enhanced to drain the storm water, and through a stormwater conveyance system, which was also part of this construction. So for the stormwater management, the upstream end of the arches right here has been graded to make sure the water flows in a particular direction. And then it enters through a graded weir structure, which was constructed at the left end of the dam, into a drop structure. And the drop structure is mainly needed to reduce the flow. And from there, it basically goes into a manhole, out of which it gets off the site into the city stormwater drainage system. So the construction, as I indicated, was completed in the summer of 2018 in 2 phases. The phase 1 included clearing and grubbing and removal of all the contaminated soils. As indicated earlier, the contaminated soils had arsenic and heavy metals. So those soils, along with any soft soils that are encountered, have been removed. Any instrumentation that was required, like seismographs and tiltmeters, were installed during the phase 1. These contaminated materials which were removed were basically transported and stockpiled at a location at the north end of the property. In the phase 2, which included the construction of the composite embankment and the stormwater drainage system, the rock excavation was performed to prepare the stormwater drainage chute and standpipe formation and the foundation for the standpipes. The cellular concrete within the existing dam arches and the butters were filled in lifts of 2 to 3 feet. Approved embankment fill was placed on the top of the horizontal drain and filter materials, and then stabilizing the composite is built in lifts. So summary of the overall work, the 4 alternatives have been evaluated, and based on the advantages, constraints, and the conceptual costs, a preferred alternative was selected. That preferred alternative is a composite earthen embankment, which included cellular costs to make the costs effective, and the option a viable and feasible option. The composite soil embankment is proposed to bear directly on bedrock with an underlying drainage system. Due to the contaminated soils on the site, the work has been divided into 2 phases, which I explained before. The phase 1 is removal of the contaminated soils, and second phase is the construction. Construction began in summer 2018 and was completed in December of 2018. So these are some of the construction photographs. This is prior to initiation of the construction. And as you're going through the construction phases, where drain rock was being placed in the picture, first picture, and the under drain pipe system was being installed, and then the filter fabric was placed over the gravel drain. You can see the cellular concrete being filled in between the earthen embankment and the arches of the dam. You can see that the drop structure from the grated weir is being the pipe. You can see the stormwater drain pipe. And basically you can also see in the lower right-hand picture, the outlet structure from where the stormwater basically enters underneath the highway into the city stormwater system. So you can see this picture has the cellular concrete in the bottom left, and you can see also on the top. And you can see on the upstream side of the dam, the turf force mats are being placed on the graded surface, so to make the water move in one particular direction. This is a completed construction photograph of the composite earthen embankment along with stormwater drainage system. Thank you very much, and appreciate your attention. I would like to thank my co-authors and the Department of Toxic Substance Control for giving us the opportunity to participate on the project. Thank you very much.
Thank you so much, sir, for your very interesting, a very unique presentation regarding the 100-year-old tailing Argonaut Dam near Jackson, California. Very interesting. First of all, the objective of the correct structural deficiency and address appropriate flood water management, where it was explained that a combination of cellular concrete and earthen embankment buttress on the downstream face was used, primarily because of the cost economics, also the suitability, and also the stormwater deficiency was clearly addressed by constructing a spill system that has the capacity to handle the required flood, design flood. So all in all, it was a very, very interesting and very important paper, and thank you so much for this. And now we are left with another 20 minutes, so I would now request the next presenter to to go ahead with his presentation within the stipulated time frame, keeping that in mind. Thank you.
So the topic is evolving repair methodologies for spillway, sling basin, and sling basin in Himalayan region. So written by Mr. Balraj Joshi, Mr. Keshav Deshmukh, Mr. Shirish Dubey, and myself, Ajay Mittal. We are from NHPC Limited, Faridabad. So the issue is why the Himalayan rivers are different from other rivers. Himalayas are basically young mountains with fragile geologies. These rivers carry large amount of sediments. Landslides, flash floods, cloudbursts, and seismic events also generate sediment loads. During monsoon, these rivers carry large quantity of sediments at high velocities, which accelerates the damages on spillway and its component, requiring frequent repair due to erosion. Provision of low-level spillway crust to maintain the live storage capacity have further stressed the system due to high velocities at the crust. Now we will discuss mechanism of erosion in spillway. Erosion takes place due to progressive disintegration of the soil by abrasion and cavitation and impact forces generated due to high velocities of water carrying sediments. Cavitation occurs due to generation of extremely high pressures or implosion of water vapor bubbles at surface in a small area causing pitting. Abrasion results from abrasive effects of waterborne silt, sand, gravel. Rate of abrasion is dependent on size, shape, quantity, and hardness of sediments. Impact, this is basically a new thing, impact that we have noticed, and it is very important for Himalayan region. This impact is caused by large size boulders traveling in high gradient rivers, causing crushing of concrete. So this crushing of concrete is very important phenomena, which is basically seen in these Himalayan rivers due to high gradient boulders traveling with the water. Once above forces substantially alter the spillway profile, high water velocities striking the irregular surfaces accelerates the damages. So this is the mechanism of erosion in the spillway. So to understand the erosion conditions and required repair materials for them, we tried to divide the erosion conditions in three parts, three types. Mild, second is moderate, and severe. So these categorization was done on the major characteristics. These major characteristics are hydraulic head over component, annual sediment load, and maximum size of sediment. The most important characteristic here is the maximum size of sediment. Generally, in the mild erosion condition, there is no boulder rolling, only silt and sand is there. In the moderate conditions, no boulder rolling, only silt, sand, and gravel. So gravel is added here. And then in the severe condition, the boulder rolling along with silt, sand, and gravel. So the major thing is basically in Himalayan rivers with high gradients, this boulder rolling creates the major problems for the spillway material. In the mild, the second category, which is important, is hydraulic head. Hydraulic head for the mild erosion condition is generally 0 to 15 meter, moderate conditions 10 to 30 meter, and for severe conditions it is 10 to 60 meter. You can note that even for a 15 meter spillway, 15 meter head over the spillway, if the boulder is rolling, this can create severe conditions. One of the other major characteristics is basically annual sediment load. There is not much variance in the sediment load, but this decides the frequency of repair which will be required. So for mild erosion conditions, the standard concrete is okay for as a repair material. For moderate conditions, we need HPC. For the glacis bucket sling basin and cementitious mortar R4. And for severe condition, steel liners appears to be the only solution for upper glacis and the crust. However, HPC can be used for the lower glacis and the bucket sling basin. Steel liners can be used at the piers or the cementitious mortar. So these are basically the categorization. And the Himalayan river, we face these severe conditions at NHPC at many projects and were successful using these steel liners. We will discuss these repair materials in the further slides. So this is the categorization of the erosion conditions. Mild condition observed in the low head spillway. So we see this condition in the barrages located in the alluvial reaches and the spillway of high dams with large reservoir. Due to large reservoir, the sediment is not there, and due to crest spillway, the head is also low. So mild erosion conditions exist like Bhakra Dam and many other concrete dams with high dams and crest spillway. The moderate conditions, due to increase in velocity, the cavitation and abrasion forces are prominently visible. However, impact forces are absent. So the impact forces are not here in moderate condition. In the severe erosion condition, the conditions are observed high head spillway or even low head spillway with high sediment yield. But the most important part is that the boulder rolling is observed. Damages due to all forms of cavitation, abrasion, impact are prominent at such location. Impact load causes crushing of the concrete. So these impact loads due to boulders causes crushing of the concrete. So now we will discuss the HPC, various repair material. One of them is HPC, high performance concrete, has high strength and high durability compared to conventional concrete. HPC provides high erosion resistance in moderate erosion conditions. For severe conditions also, HPC is preferred for the lower glacis, bucket, sling basin, because these can be repaired with high frequency, and the steel plating is not an alternative here. Design mix for HPC is basically cementitious material, silica fume plus cement, varying from 450 to 500 kg per cubic meter, and water cement ratio of 0.3 with a compatible PC based superplasticizer. The other important thing is the aggregate, because aggregate is a large part of the concrete. So the Los Angeles value, crushing value, and the impact value of the aggregate should be less than 25%. And how to bond the new HPC with the old concrete? So we use mechanical bonding, can be provided with the epoxy grouted 25 mm dia steel anchors. So other repair material is cementitious mortar. This cementitious mortar also evolved at NHPC because we were facing a lot of problem in repairing the piers with thin layers of the material. So this cementitious mortar is as per EN 1504. This is a structural grade repair mortar. The most important property of this mortar is its adhesive bond strength is more than 2 MPa. So if you repair with this mortar, it becomes a integrated part of the original concrete, and it becomes basically a structural member. So the bonding is very good, and the abrasion resistance of this mortar was, as per STM C1138, was seen that the abrasion is similar to M65 to M80 grade. So this mortar was found very suitable for the repair of the piers. The layer thickness may be 12.5 mm to 50 mm, or the cavities up to 100 mm was filled, and the performance was found satisfactory. Erosion forces are relatively less at the piers and in comparison to glacis. However, we have seen that in the mild case or moderate case, we can use this at the glacis also. The performance of this product was found satisfactory at low level spillway in the Dhauliganga Dam, which is located in the Uttarakhand, and Tista 5 Dam, which is located in the Sikkim. Both of these dams are basically low level spillways and severe in condition. So other repair material is basically steel liners. Steel liners, resistance of steel plates against cavitation, abrasion, impact is well established. Thick plates can resist impact loads generated by big boulders. Anchoring of new plates. This was a big issue, how to anchor the new plates. So we at Dhauliganga used Hilti bolts to anchor the 32 mm thick steel liner with countersunk bolts at the spacing of 250 mm center to center. So countersunk bolts was placed 10 mm below the finished surface and the flushed with compatible welding material after installation. We provided a steel cutoff also at the end. The performance was found satisfactory in spite of heavy boulder rolling at at the high velocities. So here you can see two photographs. This of the Dhauliganga spillway. It's a very high gradient river, so carry lot of boulders during monsoon. You can see that before installation of the this steel liner, before installation of the steel liner, even after 1 year of operation, you can see that 1 meter to 2 meter deep channels were formed at various locations in the spillway. After these steel liners, we installed these when we installed these steel liners, then even after 3 years of operation, there is no sign of abrasion, cavitation, or impact damages. So these were highly successful at Dhauliganga. Other repair materials, steel liner. So steel liners have resistance against cavitation, abrasion, and impact forces. So one more repair material, epoxies. We are discussing the last repair materials, which is epoxy. Epoxy is ASTM C881. Epoxy compounds have excellent adhesion, high compressive strength, and rapid hardening and abrasion resistance. ASTM C881 provides standard specifications for epoxy. So the main important thing is that the ASTM, we should follow ASTM C881. These type 4 epoxies have been recommended for structural repairs. The limitation regarding application is that thickness is 5 mm to 15 mm. The cementitious mortar possesses similar engine properties as the parent material. However, here we had the advantage of that higher thickness can be used. Epoxies, due to its excellent adhesive properties to steel as well as concrete, may be found suitable at some of the locations. So finally, the recommendations and conclusion. The frequency of repair can be optimized by study of erosion and suitable repair methodologies as follows. The categorization of the various components of spillway as mild, moderate, or severe based on the three major characteristics, that is hydraulic head, annual sediment load, and maximum size of sediment and boulder. HPC is the repair material for spillway. However, steel will be more suitable in severe condition for the crust of the spillways along with nearby spillway area. Structural repair of piers of spillway and other structures may be carried out with cementitious mortar R4 complying with EN 1504 Part 3. The mortar has abrasion resistance of M80 to M65 grade. Epoxy materials complying with ASTM C881 have excellent bonding strength with concrete as well as steel. However, it has some limitations regarding thickness. So there is a need to standardize the repair guidelines, including technical specification, repair materials, and methodologies for execution of repair spillways. At NSPC, we have standardized these specifications and have been using for the last 4-5 years and found them very suitable. For the upcoming projects, major characteristics mentioned in the paper may be studied for suitable erosion classification of the spillway components to adopt appropriate material during construction stage to minimize damages during O&M stage. So the conclusion is that the use of appropriate material with standardized performance characteristics can optimize the cost and frequency of repair and enhance the safety aspects of the dam. Thank you.
First of all, Mr. Mittal, I would like to thank you for bringing up such an important aspect, especially in the context of Himalayan structures to the fore this session. And perhaps what we have seen, and all of us agree, that this spillway aspect, especially in high reaches where you have already mentioned the causes in sequence, that the high boulder with high velocity leads to cavitation, and then the whole problems you have already described. First of all, it's very, very important, and most of the time dictating area in terms of the dam safety, especially in Himalayan region. And secondly, you have also very clearly, very beautifully brought out the need for overarching need for the categorization of the understanding of the whole erosion and the sediment issue before deciding upon the alternative for which we have to what we have to adopt. So overall, a very insightful and very important aspect of dam safety, and I thank you, Mr. Mittal, for this. And I am sure that the issues described here would go a long way for all of us, all the dam owners and the designers, and help them in evolving the right strategy. Now we are left with hardly 5 minutes, so I would request the last presenter to go ahead with his presentation.
Thank you very much. My name is Cemal Can Maslak from Bauer Special Foundations from Germany. In 2017 and 2018, we have constructed the cutoff wall up to 100 meters with plastic concrete at Polavaram Dam, and I was in charge for developing a suitable plastic concrete material, the trial mixes, and also I was in charge of quality during the production. So let's start. My first slide. So we had a plastic concrete cutoff wall with an area of 67,000 square meter. The thickness of the wall was 1.5 meters, and the length of the wall was almost 1.5 kilometers. In some portions, the depth was up to 9,500 meters. So for the operation, we have used 2 times grabs, which we perform the upper 20 to 30 meters, the removal of the soil material. And then subsequently, we had cutters in operation for the deeper parts after 20 or 30 meters. It was mandatory to have a rock embedment of 2 meters in a very hard rock in this area. Yes, one challenge for us, since we are traveling from Germany, so it is a very long way for us. So from Munich, we have to fly a long way to Hyderabad, to Rajahmundry. This is the city where we have an airport in nearby, and then a ride to Polavaram. It usually takes more than 24 hours to get to the project location from Germany. So it is already a challenge for us to access the locations. Next challenge is the river water levels. As you can see, we have dry and wet season. In the dry season, it is not possible to, it is possible only to work. And in the wet season, you can see all this area, it is already flood, and it is not possible to work in wet season in this area to make the machines operational. Yeah. So here is a sketch. You can see the March 2017 was the authorization for the project start, and we could work only 3.5 months in the first season. And then we have to wait due to very high water levels in the river. And then in end of 2017 and until June 2018, we have worked in the second season for 6.5 months. So we have worked in total 10 months. And we have to, as I mentioned before, we have to consider that working is only possible in the dry season. Another challenge is the panel design and the rock embedment. We have to understand that we had 2 different type of panels. So we have triple bight panels, which consist of 3 bight panels and with a length of 7 meters, and a secondary panel, which overcuts the existing primary panels to provide a completely impermeable wall integrity. Yeah. And in the first season, we have conducted triple pipe panels and the secondary panels. And in the second season, where we have higher depths, we have changed to only single bite panels to reduce any risk of integrity problem. But we have to also, there is another challenge for a 7-meter triple bite panel. We have to consider that a concrete volume of 600 cubic in one batch has to be supplied. So this is a big challenge. So considering that we can concrete around 60 cubic per hour, then we require a workability time of around 11 to 12 hours to complete this concreting process. Therefore, the task was to develop a mixed design that is workable for 11 and 12 hours and flowable. So the challenge was also a logistics of the raw materials. This is a very rural area, so we had to use the locally available materials. So basically the sand was chosen from the riverbed. Gravel material was provided from the client, so this was basically locally crushed material. Water, as a mixing water, we have used river water, and delivered concrete ingredients were cement and bentonite. So to understand what is a plastic concrete, according to EN 1538, plastic concrete is a concrete with low strength, with low A modulus, and high deformability. So therefore, the expected strengths are much lower than normal concretes. And we add also bentonite to introduce some stability to this concrete, since we are working with very high water contents. And also bentonite is known to increase the deformability of the concrete. So as I mentioned before, my task was to develop a suitable and highly deformable concrete with locally available products. We had some other issues. You can see here we had to work with local standards, and here is a comparison of two different standards. So you can see this is filling materials for watertight cutoff walls, Icold Bulletin 1985, and this is IS 14344. So the content is basically the same, a modulus of 4 to 5 times, elastoplastic method, which are also included in the IS standard, but we have realized that there was a misunderstanding here in the standard, since the Canadian standard Icold was saying that the concrete water cement water ratio shall be less than 0.5, which amounts to water cement ratio of 2. And in the IS 14344, we have realized that it is written the water cement ratio shall not be greater than 0.5. So this was clearly misunderstanding, but this took us time, for example, to introduce this information and to say that this is probably a typing error. Yeah. So another difficulty was for me, at least, to work to understand and totally new standards. So this had to be implemented. How we develop a plastic concrete? Briefly, I will try to explain. As a main constituent, we have bentonite in this concrete. And the addition of bentonite is done by means of bentonite slurry. So we mix the bentonite with water, then we have to be careful if this bentonite slurry is pumpable or not. So we cannot increase the bentonite infinitely. There should be an upper limit, and this is actually the pumpability. It should be pumpable. The second, we try to find out a proper consistency for the concrete. So with this dosage of bentonite, which slurry volume has to be implemented, which gives a sufficient consistency of the concrete. And after all, we have conducted a performance test with different cement ratios from 160 to 200 to see which cement content gives us the expected or the required material properties. Yes, here you can see the plastic concrete, the workability is of very high importance. We need a concrete workability of 12 hours. Yeah, and here you see the slump itself is not easy to understand if this flow is, if the concrete is flowable. So therefore, we additionally measure the slump flow. Yes. So therefore, you can see that slump flow gives a much better indication. Yeah, and here you can see initially we had a concrete cake diameter of around 520 to 550, and still after 12 hours we had a slump flow of around 400 millimeters and still workable. And after that, around 15-16 hours, we have seen that the concrete has just set. Yeah. So we require a concrete that is still workable until we complete the concreting process. As next, you can see here our performance test, different cement contents. We have tested triaxial test, confined compressive strength with a confined pressure of 0.4 megapascal. We have checked the strain at failure at triaxial test, unconfined compressive strength, and the coefficient of permeability. And among all of those cement contents, we have realized the mix 2 gives us sufficient performance in regard of all different aspects, all different properties. That's why this mix 2 was chosen for the project execution. Exactly. During this, we have done many tests, and we have 3 times we have repeated all these performance tests to understand the repeatability of this production. And we have to understand that in achieving a higher strength actually opposes with the requirement of other properties, which means if we go up with the strength, then it means the deformability of the concrete will get worse. Therefore, this should be optimized. Here is our specification. What is important for us, or very challenging, let's say, is the quality control. So the number of tests that were specified in our contract. So in order not to deviate from the contract, we have fulfilled our requirements, but understanding that 3 cylinders per 60 cubic amounts to 30 to 50 samples per day, because we concrete normally, we open 2 trenches every day, and we have to concrete them directly afterwards. This means 2 panels around 900 or 1,200 cubic amounts to 30 to 50 samples more or less in average per day. And this is also valid for triaxial testing, which means we had to buy 2 compression testing machine, 2 triaxial testing machine, and run the laboratory 24 hours long so that we can fulfill the requirement of quality control. And additionally, we have tested permeability every 200 cubic, but considering the amount of concrete, this is a big number. Every day, 3 to 5 samples of permeability test was tested. After that, we also test the materials, so bentonite, cement testing, aggregate testing at site laboratory, some chemical testing in external laboratories we have conducted. At site during production, we have done slump flow, temperature, air content, and hardened concrete tests such as unconfined compressive strength, confined compressive strength, Young's modulus, and permeability was done during the production. So here you can see most of the numbers are within the range. So we have done this, for example, panel-wise. Every single result is shown in blue. The red points are the average values, and the green line is our limits. And we have given our client a line, a strain curve. And the same is also for the triaxial test. We have done a monthly, we have given a monthly report, and all the test results we have also shared in this monthly report. And here you can see our plastic concrete, how deformable it is, even after failure, it is still able to take some loads. And this is the special case of the plastic concrete. So imagine the cutoff wall in the line when the reservoir is filled or water is removed, all this load acting on the from the reservoir acts on the wall. And this changing loading system, it is important that that we have a very deformable concrete that they can take these loads during the use time of the dam. Yeah. Here is our testing of permeability testing. We have even conducted up to 6 tests simultaneously. All the tests were witnessed during the production. And there is another point that I want to discuss. So a statistical analysis I try to make considering all these numbers, high numbers that we have tested. So basically, you can see that during the project, we have tested over 6,000 UCS samples. The same for the triaxial samples, 6,071 triaxial samples. More than 700 permeability samples were tested. Yeah, and you can see here as a very low coefficient of variation is visible. It is less than 0.2, and this shows that it's very consistent, the test results. Yeah. So a proposal, was it really necessary to conduct so many tests to understand the quality control is successful? So maybe for such big projects, considering that very high numbers of testing should be done, maybe it is more suitable to reduce the test, let's say keep it in a higher frequency in the first 600 cubic, for example, or say initial 10 panels, and then reduce the testing frequency. This would help quality control a lot. So, basically, as I've mentioned, it is very difficult to find personnel to run the test and all the machinery to run the test day and night with 2-3 different machines. It is very challenging. Yeah. And here I also checked what would have been if we reduce the testing frequency to 300 cubic, every 300 cubic instead of every 60 cubic, for example. 300 cubic comes from EN standard. So I have calculated from the existing numbers, the average will not change almost. The minimum value was changing in that case, but standard deviation and the coefficient of variation would remain almost the same. So it was also possible to develop an effective quality control with with reduced number of testing. Yeah. So I want to show a couple of pictures from our site. So this is from the dry season, in the season 1. You can see that river portion is gone. There is no water anymore, so our machinery can work. And here our cutter cannot work in clay, so we should implement the grab in that upper 20-30 meters. If the clay area has to be made with cutter, this is problematic. As next, you can see our working platform, our guide wall preparation before start of work. So we are starting with the second season, so all our machinery are going to the working platform again over the service road. Here you can see different machinery working at the same time simultaneously. A grab is working, a crane is there, and cutters are working. So we are approaching to the deeper portion of the river, as you can see. So here you can see our bentonite plants, all the machinery. At the back side here, we already started to fill the deeper portion, the river portion, with available material up to the hill. And we have to divert the water so that the service road can still be used. This was done by our client. My last picture, you can see here the field area, and we are almost to reach to the hill. This is the end of the cutoff wall, and here you can see this is the horizon. So we reach until this part. Yeah. So this was all. Want to thank you for everybody for listening and joining. Thank you.
Thank you, Mr. Maslak, for a very wonderful presentation. It was clearly reflective about the specialized nature of your this work of deep cut-off wall and study on QC testing. And you also very clearly covered the associated challenges in terms of the raw material and then choosing the right way of doing it, the sequencing and the timing of each activity. So all in all, it was a very informative in terms of explaining us as to how to achieve this very specialized a very important activity of deep cut-off walls. So thank you very much for your presentation, sir. And we have already overshot by almost 15 minutes. So there is a paucity of time. We were supposed to end it by 1 IST. So I once again thank you everyone, all the distinguished panelists for such a wide spectrum of issues associated with the dam safety and long-term structural integrity and various other issues to the fore. And I am sure that the conclusions, the outcomes, and the issues raised here would find suitable place in the final recommendations at the end of the conference. So I once again, on behalf of WAPCOS, thank everyone for this wonderful technical session. And I'm sure that all the participants and all associated stakeholders will take a lot of positive things out of the case studies and the issues presented today. So once again, thank you so much for your time and patience and giving us so much of information in such a short time. Thank you so much. And I over to virtual host. Yeah, can we conclude now? Is there anybody from admin?
Yes, sir. I am host. So can
Yeah,
we
I think, yeah, you can now, because we
end
already.
this session?
Hello?
Can we end this session, sir?
Yeah, sure. So once again, we thank all the distinguished panelists for their time and presenting the paper. Now we can conclude the session. Thank you.
Thank you, sir.
Yes, sir. Now you can start, please.
Okay. So good afternoon, everybody. I am Sanjay Sibbal, Chief Engineer, Central Water Commission. So I am chairing this session. So this session is on rehabilitation technologies to enhance dam safety. And as we all know, the time allotted to this session is around 90 minutes. So there are 6 presentations in this session. 3 are national presentations that are from India. And the remaining 3 are international presentations, one each from Iran, UK, and Russia. Further, I am told that 3 presentations are PowerPoint presentations where the authors will be presenting, themselves presenting, and 3 are recorded presentations. So we will take up the presentation in the order that has been listed in the program. So the duration of each presentation will be around 10 to 12 minutes, and 3 to 5 minutes, remaining 3 to 5 minutes will be for question and answer session. So each presentation has been given a time slot of 15 minutes. So if anybody having questions, so they can ask the questions or they can write in the chat box. So then I will ask the question. So the first presentation is a numerical simulation of a stage constructed rock-filled dam and plastic clay foundation. So this is with reference to the Polavaram Dam project. So this dam is being constructed in Tamil Nadu and Andhra Pradesh and Telangana boundary on River Godavari. So Mr. I think Ashwini Kumar Verma, from Deputy Director in Central Water Commission, he will be making the presentation. So over to Mr. Ashwini.
Thank you, sir. I'll be sharing my screen now. Good afternoon, everyone. Today we'll be discussing a study on the numerical simulation of a stage-constructed rockfill dam on plastic clay foundation. And this study has been conducted by Mr. Anil Jain, Director, Central Water Commission, along with Ashwini Kumar Verma, Deputy Director, that's me, and my colleague Randhir Kumar Chaudhary, Deputy Director from Central Water Commission, India. Now, as you all know that plastic clays tend to have high compressibility and they settle on application of large loads. And dams built on such foundations can undergo excessive deformations and lateral displacements, which can be detrimental. So such dams are usually built using the design as you construct approach, wherein we control the rate of fill placements and utilize the instrumented response data collected during the construction. And for stage constructed dams built on soft clay, the most important aspect is the pore water pressures, and a realistic prediction of these pore water pressures can be done using the coupled stress strain consolidation analysis, which can be very useful in planning a safe construction sequence. Now, this study is about Polavaram Dam, which is under construction across Godavari River, which is located in Andhra Pradesh state of southern India. On the right, you can see the longitudinal geological section of the dam, wherein the main rockfill dam is to be placed. About 2/3 of it has a foundation which is poorly graded sand, while a third of it is highly plastic clay. Now, for the subsoil exploration, we had conducted SPT test, CPT test, cone penetration test, and cross-hole test, which was supplemented by lab test as well. Cross-hole test, and it was found that the clay percentages by weight were up to 50%, with an average of 30%, and the plasticity index ranged was about 35%, and liquidity index ranged from 40% to 75%. And the clay was found to be normally consolidated clay. And during the preliminary estimates about the consolidation settlement, it was those were found to be in the order of 3 to 4 meters. We're looking at the grain size distribution, where we can see the clay percentages to be up to 50%, and the Atterberg limits, where the liquid limits are pretty high. Next is the plasticity chart. We can see that the samples are can be categorized as CI, that is intermediate plasticity plastic clays, high plastic clays, and very high plastic clays. Those are the SBT charts from ECPT. We'll take them later. During the several CPTs were conducted in a grid size of 50 by 50. Those were confirmatory, and we got a stratigraphy of the complete foundation. The tip resistance of the CPT can be seen on the right, wherein the sands and clays have been differentiated. Now, this is a typical geometry of the dam. The upstream slope is about 2:1, while this downstream slope is 1.75:1. It has a central clay core, and we have used a diaphragm wall, a plastic concrete diaphragm wall, for the under seepage control measure. As for the ground improvement, we have placed the stone columns, and just below the core, you can see that there is a composite material of deep soil mix material. The top layer we can see is mostly sand, underlain by 10 to 15 meters of clay, then another 20 meters of clay, and then we have weathered rock. Now, based on the investigations, we had estimated the properties of each material used in the simulation, and majorly two constitutive models were used. First is the elastic perfectly plastic with the Mohr-Coulomb yield criteria, and the second was modified camp clay model used specifically for the clays. These are the properties of the material used. Most for elastic perfectly plastic, most important parameters are the elasticity modulus, the Poisson ratio. As for the failure criteria, we are using the cohesion and phi and dilation. Next, modified can clay, as our focus is on clays, and we want to predict realistic pore water pressures and deformation behavior. A modified camp clay proposed by Roscoe and Berlin in 1968. This model was used. Major soil parameters here are over consolidation ratio, the Poisson ratio, initial void ratio, the phi, which is used for this calculating the slope of critical state line, the lambda, which is the slope of the normally consolidation line, and kappa being the slope of over consolidation line. Now, as for the ground improvement, we have proposed stone columns, vibro replacement method, which seem to be suitable for these plastic clays. These are some of the geometric parameters and the material characteristics. The depth of the stone columns is about 15 meters from the ground level. The diameter being 900 mm placed in square pattern with a spacing of 2.5 meters. And the area replacement ratio can be termed as 10 to 16%. The vibro stone columns are being placed using the wet top feed method. These are the average strength and the stiffness parameters of the plastic concrete being used in the diaphragm wall. Major parameters are the elasticity modulus obtained from the confined compression test and the actual strains at failure. Now, this is the typical geometry used for the simulation. At the outset, here we can see that we have used an interface element along the diaphragm wall. The ground improvement, basically the objective of ground improvement is to accelerate the consolidation and to reduce the post-construction settlement. And after the ground improvement, the dam shall be constructed in stages so as to ensure its safety. And the basic objective of the study is to optimize the rate of construction of ECRF, that is the Earth Core Rockfill Dam, for different consolidation periods, ensuring the stability of the dam at all times. So a tab is kept on the factor of safety at all times during construction. Numerical simulation using the coupled stress strain for water pressure analysis is carried out. These are all the analyses which have been carried out. First is this. Through this, we are able to analyze the system of core and the plastic concrete diaphragm wall and the stresses generated, the strains generated in the cutoff wall. And we are also looking at the effectiveness of the ground improvement using the stone columns. And basically, the study is done using a 2D plane strain nonlinear time-dependent behavior using the finite element analysis code of Geoslope International, which has a module named Sigma W. The ECRF dam is simulated to be built in about 25 lifts, each being 1.5 meters high. And the number of days of fill placement is varied from an imaginary single stage loading to 2 days, 3 days, 6 days, and 9 days for each lift to study time. In one case, we have also added a dissipation phase of 3 days, wherein where the constant loading is assumed with time for dissipation of pore water pressure. And to capture realistic stresses on the diaphragm wall, we have used interface element. As I've told, the stiffness property of the interface element is assumed to be equal to that of surrounding soil, but we have given separate C and phi values to the element. Modulus of elasticity is provided as a function of effective stress for the foundation soil, and hydraulic conductivity of soil of soft soil, which reduces on soil as the soil compresses, is inputted as a K modifier as a function of effective vertical stresses. The hydraulic boundary condition for stone columns is a constant head equal to that of the elevation of natural ground. And as for the granular blanket placed on top of the stone columns and below the dam is kept as zero pressure head. Now, to ensure the efficacy of the cutoff walls, the governing criteria is its imperviousness and the deformation compatibility with those of surrounding soils. And the factors influencing the stress strain behavior of the wall is basically the ground improvement in the surrounding soil, the interface element properties, and the modulus of elasticity of plastic concrete. And as for ensuring the stability of slopes, the stress states from the coupled analysis has been used, and these have been used in a limit equilibrium framework to analyze the factor of safety. Basically, these are stability factors, and these are the ratio of summation of the available resisting shear forces along a slip surface to the summation of mobilized shear forces along a slip surface. These are the results we obtained. These are the 6 cases we have analyzed to optimize the rate of construction, along with the factor of safety shown. Now, the first row shows the single stage construction. This is an imaginary condition. The row 2, 3, 4, 5 are wherein we have 25 lifts, each of which are constructed in 2 days, 3 days, 6 days, and 9 days with no dissipation phase. And the 6th one is 25 lifts, each lift of 3 days and dissipation phase of 3 days. And if you look at the rightmost column, after 5 lifts, the factor of safety achieved is the maximum, while it goes on reducing and is the lowest at the end of the construction. Now, as you can see in this case number 3, this is the most critical one which we found, and further discussion pertains to this case. So case 3, having a lift construction time of 3 days with no dissipation phase seemed to be quite critical. And we look at the graphs of the deformations in this case. This I've discussed. Yeah, these are the ground surface deformation, the settlement and the heave at different stages of construction. Initially, there is no settlement. At the end of the construction, we have about 3 meters of settlements at the center of the dam, while a heave of 1 meters at the toes of the dam. These are the lateral deflections at the upstream dam toe. At the end of the construction, we have about 1.9 meters of lateral deflection at the toes. This is a result of how the regions of the material deform. This is the deep soil mixed soil. These are the stone columns, and here we're talking about the lateral deflection at the toes here. So this is about 3 meters of settlement. And you can also see that the diaphragm wall and the specific plastic clay placed on top of it, the plastic clay cushion, is also come down with it. Relative vertical displacement between the clay core and the top of the diaphragm wall is about 2 meters. So it is proposed that we have a 3 to 4 meters thick plastic clay cushion on top of the diaphragm wall. The strains in the diaphragm wall were found to be in permissible limits. So that is why it was considered to be safe. And based on this analysis, we were able to say that the stage construction of ECR dam can be safely carried out within the time period we propose. And practically the lift height are at field are about 600 mm for rockfill after compaction, and which usually take about 1 to 2 days to place. And the time of each lift will go on reducing at higher elevations due to reduced earthwork. So with the availability of good instrumentation data, the construction time can be minimized. We recommend instrumentation and extensive field instrumentation installation scheme to monitor and control the rate of construction, as the scheme of as the objective is to design as we construct the dam. So a good instrumentation is key to this. Instrumentation next to the diaphragm wall will also be effective in understanding its behavior during the construction. Next, we moving on to the conclusions. With proper instrumentation and careful monitoring of the collected data, field construction rates can be adjusted. The extent of embedment of the diaphragm wall into the core can be decided based on this analysis. And a plastic clay cover core having plasticity with the liquid limit of more than 50% is proposed to be placed on top of the diaphragm wall. This will act as a deformable cushion and will reduce stress concentration. And there's always a possibility of differential settlement between the cutoff wall and the foundation, resulting in friction between the cutoff wall and the surrounding soil. So with suitable ground modification, such differential settlements and the consequential friction forces can be drastically reduced. And the range of settlements expected in the improved ground conditions warrant defensive measures like providing thicker clay core and increasing the height of the dam and the core to ensure that the freeboard is not encroached upon after settlement. Thank you so much.
So, thank you, Mr. Ashwani. Any questions? So, I have a couple of questions for Mr. Ashwani. So, you have modeled in the properties of clay core that you have adopted, a Poisson ratio of 0.49 has been taken.
Yes, sir.
So, this is nearly equal to that of a fluid, which when we take a fluid, then we take this high Poisson ratio. So, can you have any comments on this? Because it will behave like a fluid.
Yes, for unsaturated soils, the Poisson ratio usually range from 0.49 to 0.5. Due to numerical simulations, we usually use 0.49, 0.495. But for undrained conditions, the Poisson ratios are in this range. For a drained condition, it can reduce to say about 0.3, 0.35.
So why you have not adopted this cam clay model for the dam core, and why more column model has been adopted for that?
So basically, whatever the core and the rockfill itself, these are just creating loads onto the foundation. What we are trying to study is the foundation, the consolidation of the foundation. We were actually not very interested in the deformation of the core, although it could have been used.
So another question is, for the dam clay core, you have adopted total stress parameters.
Yes, sir.
Whereas, and you have used GeoStudio software.
Yes, sir.
So in this, the Moore column constitutive model is based on effective stress parameters.
Pardon me, sir?
The Moore column constitutive model in GeoStudio is based on effective stress parameters, but you have used total stress parameters.
So in this elastic perfectly plastic, we can use both the kinds of analysis, the total and the effective both. Wherein when we are using the total analysis, we input C phi in terms of the total condition, in terms of total C and total phi. And when we're using the effective material model, we use the effective C and phi.
See, normally if we use the total, then we use CU undrained, then you can use the total stress. But if you use the effective, then C phi, then we have to use C phi material properties.
True, sir. Although it is undrained, but the issue was to give certain values for Moore column yield criteria, and that is why total parameters from CU bar test were adopted.
So, okay, thank you.
Welcome, sir.
So there is another question from Mr. Louis Hatting. So he says, what is the maximum long-term deformation and how long does it relate to the end of construction deformation?
So we have tried to keep the permissible residual settlements to about 300 mm. That is the limit we are trying to restrict this total settlements, and that is how we are trying to that is why we are trying to get the maximum settlements during the construction phase itself. Although this study was to find out the least amount of time that we can take to construct the dam. The dam shall be constructed in about 9 to 10 months of time. So we are probably looking at about 80% of the settlements to be about 90%, sorry, about 90% of the settlements to be complete during the construction itself.
So you have given different in the table, different stages, different scenarios of construction that you have modeled. Six case numbers that you have modeled. But the actual construction stage, I think you have not modeled.
So that was not known at that time. Actually, the plan was, can we build the dam in about 4 to 5 months? So the simulation was taken up to predict that whether it'll be safe in that condition or not.
Okay, thank you. Any other question? So, okay, thank you.
Welcome, sir.
So the next presentation is on significance of stress sensitivity analysis and monitoring of structural behavior of concrete double curvature arch dams using finite element modeling for the safety evaluation of existing dams. So this is by Mr. G.G. Panikar. So I think this is a recorded presentation. So I will request the host to play the presentation.
Respected guests, dignitaries, and ladies and gentlemen, I'm delighted to present a paper on this session of Icold and the APG Symposium on Sustainable Development of Dams and River Basins. My paper is on significance of stress sensitivity analysis and monitoring of structural behavior of concrete double coverage arch dams using finite element modeling for the safety evaluation of existing dams. In this paper, I have structured my presentation into 9 sessions. It have a brief introduction, apart from some aspects of arch dams, its types, structure analysis, and the need of a review on analysis of existing arch dams. What are the potential failure situations? And finally, moving to the sensitivity analysis, why it is conducted and how it is conducted, before move on to some of the inferences. So regarding arch dams, there are various classifications of arch dams. These classifications use various criteria, but some accepted or general classifications are based on the centers, whether it is constant centered, variable center, single centered. If it is variable centered, two centered, three centered, polycentered, like that, or based on thickness, if it is thin, medium thick, or thick, and if it is based on the curvature, whether it is constant angle, constant radius, variable center, or double curvature. So this is somewhat the general classification, but there are some other classification like high arch dam or super high arch dam, something like that. And these are some of the terminologies where we meet with while dealing with the arch dams. This is upstream phase is often known as the extradose, whereas the downstream phase, which you see from the downstream, is the intradose. And this is a central ankle. And here we see the thickness, varying thickness, the top thickness being very small compared to the bottom thickness, base thickness. And we will be having drainage galleries or inspection galleries at various heights, some of them having multiple drainage galleries. This is the line of arches. Regarding the number of arch dams existing in the world, we have to rely upon the general synthesis of Icold. As per the statistics of April 2020, the total number of dams, large dams in the world is 58,713, of which 2,358 is arch dams. It's an interesting fact that there's an increase of 6 arch dams with respect to the previous update of Icold of April 2019. It was 2,352 when it was updated in 2019, whereas now it is 2,358. So we see that there is an increase of 6 arch dams. Okay, this is an interesting statistics on the number of dams, large dams. Coming to the behavior of arch dams, strengthened behavior are often affected by the material of construction and the method adopted for construction. So we can see that arch dams can be of masonry and concrete being RCC, roller compacted concrete, or the conventional concrete, and the methods adopted for construction. So for arch dam construction, is being in cantilever monolith, they have to be temperature controlled. So depends upon the method of construction, the strength and behavior will vary. The behavior affected by the foundation or the abutment, that is the rock, its characteristics, loads acting, etc., are dependent on the behavior of these dams. There could be differential movements if the abutments are not strong. These differential movements, if caused, will be disastrous and potential cause for failure. So it is very important to see the movements or the behavior of the arch dams at the salient points such as abutments or foundation. So phenomenon such as alkali aggregate reaction and its effects, delayed ettringite, fracture pattern, etc., are factors affecting behavior. Often the stress pattern on the body of the structure, the body of the dam, at the abutments, at the foundation, etc., are factors affecting the behavior of arch dams. Structural analysis of arch dams and doubly curved arch dams are often done in many ways. Previously, it was by conventional methods such as trial load method, which utilizes assumptions such as homogeneity, elastic nature, etc., etc. But things have changed after the introduction of computers and advanced computation technologies using 3D fine-tuning methods, etc. But these conventional methods, in this analysis, they take care of ideal conditions, but not the various real situations. That is the presence of joints, crack opening, nonlinearity. This nonlinearity can be in geometry as well as deformation, displacement or deflection, variation of thermal stresses, etc. And the advancements in the mathematical modeling and the FEM tools, faster digital computers, interventions had made a simulation of all these situations in a more realistic way. There are some acclaimed softwares such as ANSYS, Abacus, Athena that can model the real scenario, and these analysis, 3D analysis of various loading scenario will give reasonably good results matching with instrumentation data. So advanced softwares are capable of simulating any geometry, analyzing any load cases, that is a dynamic load or non-linear analysis or variation of thermal loads, etc. And it can simulate reservoir dam foundation interactions, the fluid structure interaction, and also can analyze the various potential failure modes that can cause risk. So why analysis of existing dams is required? Normally we go for analysis when the new dams have to be constructed, but nowadays the rate of construction of arch dams, especially double curvature arch dams, are not at par with the conventional gravity dams. But still, we have seen that there was an increase of 6 over 1 year. Even then, these analyses are having a good bearing in the sense that the performance and behavior evaluation is the design performance or the envisaged behavior is important. Whether it's behaving in the designed way or the envisaged way is to be analyzed in the case of the existing dams. That's very important. And review whether the structure is safe with respect to relevant design consideration as per the relevant guidelines or codes. The codes existing in the time of construction might have changed during the present times. So we have to evaluate whether these codes or guidelines holds good in the present scenario, in the present time. So hence the review is required. The effects of aging of the structure with respect to structural parameters and any possible changes in the hydrological, geological, climatological, and technological parameters are to be investigated. Whether the aging has some bearing on the structural performance of the existing dam or the behavior of the existing dam needs to be ascertained. So the structure analysis becomes inevitable in this case. Also, the instrumentation data or the structural health monitoring can be incorporated in the analysis when it is done in the case of an existing dam. So in all the cases, the ultimate aim is elimination of the potential risk. So at the time of construction of the dam, there was no such advanced techniques to simulate the real scenario, but now we have all the technologies and methodologies to do the analysis and assess whether there is any potential causes of risk. So this is a visualization in 3D FEM model of a doubly curved arch dam integrated with the abutment of the foundation rock mass. It's a model view. So some of the potential failure causes of concern in respect of arch dams or the doubly curved arch dams that may require studies are listed here. Many literatures about arch dams emphasizes that one of the potential causes of failure of arch dams or double coverage arch dams is the failure of the abutment due to various factors. There can be faults or joints vulnerable to cause failure in shear. Joints and fissures parallel to the direction to the thrust are detrimental to the stability of the abutment. Safety of the arch dam prominently lies in the strengths of the abutments and foundation rock. And as such, the analysis to find out these stresses and the behavior is very important. Development of unusual stresses and movement, the abutments, development of unusual stresses and movements at foundation interface, development of unusual pattern of tensile stresses in dam body or other salient points, if any, an unusual movement vis-a-vis the expected or envisaged pattern, and the development of cracks and crack propagation, anything if it is in the various salient points of the dam. These are some of the causes, some of the concerns to be investigated in the case of an existing arch dam or the double curvature dams. Now coming on to the sensitivity analysis, what is sensitivity analysis and why it is to be done and how? I will go in small sentences. Sensitivity analysis is a study of how the uncertainty of the output of a mathematical model or system, that is numerical or otherwise, can be divided and allocated to different sources of uncertainty in the inputs. So we will be interested in certain output parameter, output results. How these outputs are affected by the uncertainty of the input parameters are determined in a sensitivity analysis. How sensitive it is, the output, how sensitive it is with respect to the various parameters is analyzed, and the sensitive parameters are found out. Sensitivity analysis helps to identify how sensitive the model results are with respect to the input parameters. You can have ample number of inputs in the sensitivity analysis. And finally, you can find out which are the sensitive ones. There is a sensitivity analysis in which the magnitudes of certain parameters are varied can indicate the confidence with which the model can be used. Sensitivity analysis enables the analyzer to refine the model. You can refine the model based on the parameter selected and its sensitivity. A sensitive parameter produces a relatively large change in the output for a change in the input parameter within the range of uncertainty. You can see that if it's a sensitive parameter, a relatively large change can be seen in the output variables. There can be hundreds of parameters sampled from their probability distributions. The parameter sensitivity analysis finds those parameters that make the largest contribution to the chosen outcome or its variability. So it's very important you can have apprehension on certain particular parameter that can affect the output. So you choose that many number of parameters and find the most sensitive ones. There are various traditional techniques based on parameters.
Excuse me, I think we have to accelerate a bit.
Methods or non-statistical methods, random sampling of the parameters and hypothesis testing of responses. There can be single regression models or multiple linear regression, etc. There can be non-statistic methods as fast. Advanced special case sensitivity techniques. So there are numerous methods by which the sensitivity analysis can be done. So this is a particular case of a representative indicator system for sensitivity analysis done by a researcher for operational tunnel problem. So how sensitivity analysis can be exercised on a variety of problems has been explained in this one. In this particular case of the tunnel analysis, the output parameters were maximum bending moment, maximum axial force, and maximum bolt strength. So there were three output parameters, S1, S2, and S3. So you can see that the input variables based on the structural risk, environmental effects, soil factors. So these three main divisions, based on those main divisions, there are other parameters listed. And these input parameters, variables, were analyzed in the sensitivity analysis and how it is affecting the outputs legitimate. So this is an example. So in case of Arch Dam, there were many instances where the sensitivity analysis done.
We should straight away come to the conclusions.
Optimization problems where shapes are economized for performances. Sensitivity analysis gives advanced
और तुम्हारी क्लोरोफिल का पिगमेंट का जो वो प्रोसेस हो गई वो हो गया
structural evaluation and sensitivity calculation for critical parameters such as stresses and displacement can be done. It was proved by Michalska in 2019 analysis. And in 2019, there was another analysis, the seismic stability, sensitivity, and uncertainty analysis of high arch dam foundation systems qualified. It quantified the variation in seismic stability beside the parameter uncertainties. So this is 2 or 3 research paper which I have chosen to highlight what studies they have done using sensitivity in the optimization or the stability analysis. So in India, there has been sensitivity studies on arch dams. Incidentally, it is the only one arch dam, that is at Idukki Arch Dam. Sensitivity studies were conducted on India's only one arch dam, Idukki. And Central Water Commission has done that analysis and have seen that this 40 years of aging has not done any impact on this particular mighty structure. And they have done the 3D FEM thermostatic analysis of this dam using a backer software. The FEM analysis were in full agreement with the instrumentation data, which validated the FEM modeling and analysis. And according to the studies, this doubly curved thin mighty arch dam is in full agreement with instrumentation data. And I will quickly draw some of the conclusions based on the research on reviews done on this sensitivity analysis and the behavior arch dams. The doubly curved dams are exhibiting complex behavior and needs rigorous analysis. If there is some doubts or apprehension on the behavior. Identification of potential failure modes and risk, the safety evaluation of existing dams, etc., are very important and requires careful analysis. So a sensitivity analysis can list all these parameters, input parameters, and study the effect on the output. There are many parameters associated with the design as well as safety evaluations. Various uncertainties get incorporated in the models. The sensitivity of these parameters on the targeted outputs, that is the stresses, deformation or displacement or deflection, various salient points for careful review is required to alleviate any potential risk that is associated with the high or mighty structures. So we see that a sensitivity analysis is very important in case of these complex structures. The 3D FEM softwares are of much help, and this can be made use of in the analysis. Thank you.
So any questions on this presentation? So I think we can then go to the next presentation. It is by Mr. Fardeen. It is on using earth pressure instrument data to examine the safety of earth dams against arching and shear failure.
Hello, Mr. Siebel. My name is Amir Akbari.
Okay.
I will go to present on behalf of Dr. Jafarzadeh.
Okay.
Can you share my slides? Excuse me, sir. Can you share my slides? Thank you. And because due to some connection problems, I use my mobile phone. I would be so thankful if you can kindly proceed my slides. Okay. This is our presentation about using earth pressure instrument data to examine the safety of earth dams against arching and shear failure.
Excuse me.
Study. I think this is the old version of our slides.
Excuse me, I am Dr. Fardin. Can I share my file for Dr. Akbari to present that? I have the latest version. This morning I sent the latest version. Unfortunately, they have not substituted that. If possible, remove this one and I will share from my window this.
You share your screen.
Okay, I will do. And Dr. Akbari will present it. Okay, can you see my?
Yes, it's visible.
Okay, Dr. Akbari, go ahead, please.
Okay, thank you. Okay. This presentation is about using air pressure instrument data to examine the safety of earth dams against arching and shear failure. Next slide, please. Stress state in air dam is one of the most important parameters to evaluate dam safety, especially at the first impounding of the dam reservoir for selecting the optimum speed of filling and during the operational time to evaluate the long-term stability of the dam and its foundation. In zone earth dams, arching control is very important because the stress inside the core materials and adjacent to the core filter interface is commonly reduced and fragile deformations may not occur. Also, in this condition, the possibility of hydraulic fracturing and cracking and consequently the core failure is of concern. In addition to arching control, ensuring the stress levels inside the dam body and its foundation to be in a safe mode is essential in critical conditions such as earthquake or flood occurrence. Next one, please. One way for measuring and monitoring the stress values in air dams is using the pressure cells at different parts of the dam. Due to various events such as stress concentration and installation issues, it is necessary to modify the recorded values of the stresses by soil pressure meters.
I think Dr. Akbari is disconnected. Do you have my voice?
Yes, please proceed.
Okay, I believe Dr. Akbari is disconnected, so I will continue the paper. Anyway, in this paper, an earth dam in Iran, namely Silve Dam, and its recorded and instrumented data are considered, and by provided solution, the raw instrumented data are modified, and the arching phenomena is studied from the for the total stress and recorded data. This is a general picture, I mean, of Silve Dam located in northwest of Iran. Before first impounding on March 2017, You can see the dam body and also reservoir. The specification of the dam was the maximum height was 89 meter from foundation, crest length 731 meter, and slopes upstream downstream. Reservoir volume is about 84 MCM, and dam body volume is about 4.4 MCM non-homogeneous earth material. As you can see here, the maximum height cross section of the dam. It's clear that the foundation is has clay blanket and some clay core shells and other details that is usually in dam type. And we had a growth curtain and also about 40 meters in the foundation. So here you can see the yes.
Unfortunately, I lost my connection. Can you hear me?
Yes, yeah, please. So go ahead, Dr. Akbari.
Okay. I'm sorry.
Okay,
I'm
go
sorry.
ahead from this slide number 6.
Okay, in this slide, the plan of Silva Dam and location of the earth pressure instrumentations at section 2 is shown. Section 2 is the highest section of the dam. And as you see, in height of the dam, some kinds of pressure cells are installed to monitor the stress levels inside the dam body. Next slide, please. To measure the stress levels through the dam body, a set of cell pressures has been installed at some points for different sections and levels of the Silva Dam. By applying the solid mechanics relationships, two-dimensional vertical and shear stresses can be derived. As you see in this picture, we in form of a triangular arrangement of cell pressures, we can obtain and record the stress in any point. Next, please. Here you can see the results of monitoring on the vertical and inclined pressure at dam body on level of 1515 MASL in section 2, and the data are reported against time in different dates. As you see, from the construction, beginning of the construction of the dam body, the stress levels has been raised up to a level at which the construction has been completed, and after that the impounding was started. Next one, please. Arching is usually created due to the lack of complete transfer of the earth pressure between the embankment layers, which reduces the effective stress in the soil and increasing the probability of hydraulic fracture in the dam as a hazardous phenomenon. Arching phenomena mainly occurs in the core of inhomogeneous earth dams, such as zone dams, that is mainly originated from the consolidation of the core after the construction phase. As you know, the clay core of high-rise dams may face two enormous settlements, but as you know, the filter and drain materials are no consolidation materials, as well as the shell of the dam. Accordingly, there is an inhomogeneous deformation inside the dam body, and some part of the dam body, such as filter, drain, and shell, do not have the consolidation and acts as side restraints to core settlements. Accordingly, weight of the core materials tends to transfer on the side filters, and the effective stress in the core becomes less than the overburden pressure. Next one, please. Arching usually occurs more intensively in low thickness cores. In addition to the core filter interaction inside the dam body, the foundation settlement below the core can cause arching. The arching coefficient A is commonly defined as the ratio of the measured vertical pressure to the overburden pressure, as you see in this slide, as A equals to PV by gamma H, in which PV is the actual vertical pressure, which commonly recorded by the air pressure instruments. Gamma is the soil unit weight, and H is the height of the overburden soil of the recording instrument. Next, please. The smaller arching coefficient A indicates that the stress from the dam body is not transferred to the lower layers, and values close to 1 mean the appropriate pressure transfer of the upper layers to the lower parts. The arching coefficient higher than 1 indicates no transfer from other parts of the body to the stress measurement point. The high ratio of arching can cause longitudinal cracks in the dam core, which increases the probability of piping. Another adverse effect is the effective stress reduction that can cause hydraulic fracture and a scoring of the dam body after impounding and raising the pore water pressure inside the core. Actually, the value of A must be close to unity, ensuring the safe condition of the dam. However, the values above 1 is less critical than the lower values near 0. Next one, please. The notable point about the low coefficient at some level is the arching coefficient decreases when the embankment height relative to the earth pressure instrument level is only a few meters, less than 10 meters. The arching occurs usually when the stress of the dam body is not transferred to the lower layers and imposed to the stiff layers around the core. The phenomenon found in many instruments installed in their dams is the local arching that is due to the inadequate transfer of vertical stress to the soil layers. As a result, the instrument values become much lower than the corresponding real values. I want to say that cell pressures are commonly recording data with significant errors due to local issues that have been occurred during the construction procedure of the dam. So the recorded data about the cell pressures must be modified, and this is the most important factor that has been considered in this study. Next one, please. Based on experiences in the design of air dams, it can be assumed that the arching is negligible when the embankment height is up to a specific height of filling, namely Z0, above the earth pressure instrument. And the predicted earth pressure is equal to gamma H. For the heights more than Z0, Mir Qasemi and Elmi in 2013 defined a stress reduction ratio K in earth pressure instrument as shown by this equation in this slide as K equals to gamma Z0 minus ST by gamma Z0. ST is the recorded stress values. Next one, please. Since K is considered constant for any installed instrument, it is determined at the embankment heights up to the height of Z0 above the instrument level. Then the earth pressure is modified according to the following equation that has been depicted in this slide as S equals to K gamma Z plus ST, in which ST is the actual stress at the instrument location. It means that the correct value of the stress level that the instrument must be recorded in the dam body, and Z is the height of the embankment above the level of the instrument. In this research, by considering the specific characteristics of the Silva dam and taking into account the engineering judgment, the Z0 height was considered as 15 meters. Next one, please. So after modification of the arching coefficient, you can see this picture in which the results are depicted as at the left one, you can see the arching coefficient against the time before modification. At the right one shows the modified corresponding values. Next one, please. By representing the stress points on the critical plane at 4 height levels of section 2 and comparing them with the Moore-Coulomb failure criteria, the possibility of giving the failure condition was assessed in this study. The critical stress plane has an angle of 45 plus phi by 2. Phi is the internal friction angle of the soil. A normal shear stress on the critical plane of stress can be obtained as 3 equations that have been presented here. There are the common formula regarding the Moore failure criteria. Next one, please. And here you can see the condition of shear stress inside the core body at 4 points and the comparison of the stress against the corresponding Moore-Coulomb criteria. As you see that almost all points are below the Moore-Coulomb criteria, and we can say that the dam is almost safe in comparison with the shear failure criteria. Next one, please. Next one, please. Yes. And as conclusion, the stress values inside the Silva dam were studied in this study by considering the pressure data. Silva is one of the highest dam sections as selected in this research, and the values of the stresses at 4 elevations in this dam were studied. Since the value of the instrument differs mainly from the actual stress values due to some issues, such as effects of construction works, local arching, and stress concentration, a method to modify the stress values was presented in this study. And by using the modified stress values, the arching ratio was evaluated, and the main stress values on the critical planes were compared with the Moore-Coulomb criteria. The results show that the proposed relationship is in agreement with the analytical predictions. Also, the studied section of Silva dam was shown to be in a safe condition against arching and shear failure. Thank you. And I want to appreciate your attention to this presentation. Any question you have, I try to answer.
So any questions on this presentation? So I have 1 or 2 questions. You have defined a parameter Z0, which is a specific height of, can you hear me?
Yes, yes.
You have defined a parameter Z0, which is a specific height of embankment above the earth pressure instrument. So how this parameter is determined?
Actually, this parameter must be considered using engineering judgment, and we have considered many dams, and this height is about 5 to 15 meters with the average of 10 meters. Actually, we can say that at this level, there is no practical arching phenomena is expected. So the instrument, which is located beneath the 10 meters of the, for example, geomaterials, must show the value of the vertical stress very close to gamma h. Accordingly, this height can be considered as an index for justifying the recording values by the instrument.
So there is one question by Mr. Louis Hetting. So he says that he's not sure about the definition of the arching factor. Does it take into account core pressure? And he says one needs to consider effective stress when determining the principal stresses. Also, 3D analysis would be more justifiable, not just 2D. So can you comment on that?
Yeah, the arching coefficient A is the ratio of the recorded data with the vertical theoretical value of the stress. And you can find it in many literatures. Of course, I think that there are some other similar relationships that most of them are equal to this one. And about the 3D analysis, I think, yes, the 3D analysis can help. However, we are going to find a practical relationship for the engineers. As you know, that this work is not just a research, and we want to help the engineers in practical works.
So any more question? So thank you, Mr. Fardeen and Mr. Akbari. So now we move on to the next presentation. It is the Todd Brook Reservoir Spillway Incident and Emergency Response. So I think it is a recorded presentation and it will be played.
Thank you.
Hello, I'm Alan Warren. I'm a technical director with Mott MacDonald in the UK, and I'm also the chair of the British Dam Society. And today I'm going to tell you about a major incident that occurred in the UK in 2019 at Todd Brook Reservoir. The paper that was written on the incident and the emergency response was co-authored with Natalie Bennett of the Canal and River Trust, the owner of the reservoir. So first of all, some details of the reservoir. It's an old reservoir constructed in 1831. It has a central clay core of puddle clay, dam length 310 meters, maximum height 24 meters. There's a primary spillway at the left abutment. You can't quite see it in this photo. Primary spillway was 41 meters long. And then in the 1970s, about 50 years ago, a secondary spillway was created to improve flood safety. And so an overflow weir was constructed approximately 200 millimeters above full supply level, that overflow being 76 meters long. And as I say, it was constructed on the embankment itself. The reservoir retains 1.24 million cubic meters of water and lies immediately upstream of the community of Whaley Bridge. This is a plan of the reservoir, and a little bit unusual is that we have retained here the bywash channel. So the original channel that would have been created for the construction of the reservoir was retained and provides a diversion channel around the reservoir, and that proved to be very important in terms of the emergency response. So at the upstream end, you have an inlet weir where flow can either be directed directly into the reservoir or directed into this bywash channel. In this area here, we have the primary spillway at the left abutment, a simple overflow spillway. We have outlets through the embankment, and then we have this concrete overflow spillway, auxiliary spillway on the embankment itself. So you can see the bywash channel sort of becomes the spillway channel at the downstream toe of the dam. So in July 2019, there was a pair of moderately severe flood events or storm events on the catchment. Catchment area was 17.3 square kilometers. We had a 40-year storm event, followed 4 days later by a 90-year storm event. and that caused the auxiliary spillway to operate. And this had only operated a few times in its history over the last 50 years. And so it was quite a sight for the local residents, many of whom would never have seen it operate before. You can see these, the flow disruption here is caused by stone inclusions. They were not there primarily for energy dissipation, just simply to break up the visual look of the spillway. They didn't really serve any practical purpose, but they were important in terms of why the incident occurred, which I'll come on to. So early on the morning of 1st of August 2019, muddy water was seen coming from the spillway, and so the alarm was raised. And here you can see that the voiding got larger and larger through the morning. And the subsequent investigation found that the most likely mechanism was water injection through cracks associated with the stone inclusions on the spillway. The concrete itself is quite poorly constructed, designed and constructed, just 150 millimeter thick concrete. Water stops not in all of the joints, and dowels not in all of the joints. Quality of the construction was not great. So here, as I said, you can see the voiding got larger through the morning, and eventually this is the scene that was greeted by those arriving on site. The voiding was quite substantial, and there was not a great deal of fill left between the void and the back of the puddle clay core. However, there was no water coming through the core itself. This was not an internal erosion event. Water had accessed the downstream shoulder through the lining itself. So obviously an emergency response was called for by the operational staff. The outlet valves, of course, were opened as the first action to try and get the water level down. And the supervising engineer called the inspecting engineer, an inspecting engineer from Mott MacDonald that attended site. In fact, I was the second inspecting engineer. And instruction was given to evacuate the 1,500 residents in the estimated breach area. This was the largest civilian evacuation in the UK since the end of World War II. Emergency services took control of the incident and a command centre established at the site. And so the engineers on site then developed an emergency stabilisation plan. So the first action taken at the site was to put sandbags on the overflow spillway to reduce the risk of further water accessing this void and causing further erosion. There were weather reports of further rainfall in the forecast, so this was a concern. The military were on site and were asking what they could do, and it was appreciated that we would not be able to safely access this void to stabilise the dam using mobile cranes just by the nature of the site. And so it was decided to use helicopters to bring in bags of aggregate and to drop them into the void to build up this void slowly and over the coming days to stabilise the rear of the core. The sandbags here, or the aggregate bags, were subsequently grouted with cementitious grout, and at the top and sides of the void where we couldn't use sandbags, a polyurethane foam injection method was used to seal the void. But the most important thing was to stop water getting into the reservoir. As I said, we had diversion facilities available, and to pump water out to reduce the pressure on the dam and to reduce the risk associated with dam breach should it occur. So the inlet weir was raised and strengthened, and improvement works were carried out to the bywash channel to improve its conveyance. a huge number of pumps were brought to the site. So about 29 large pumps were in use. We had almost 3.5 kilometers of this steel piping that you can see, and an enormous amount of water, 1.1 million cubic meters of water were pumped over 4 days. So throughout all of those activities, the engineers on site monitored the condition of the dam and updated the emergency services continuously with regard to the risks and the actions that had to be taken. So here we see infrared monitoring of the dam, checking for any signs of seepage. We did have piezometers, so we were able to check that there was no deterioration in the performance of the core, and obviously topographic monitoring of the spillway itself to make sure that nothing was moving. So 12 meters depth of water was gained in six days. So a drawdown of 12 meters. Hydrological assessments were carried out. We had to work out at what point it would be safe to allow the residents to return. And in the end, it was decided that the reservoir had to be almost emptied and all of the stabilization works completed in order to allow the residents back in their home, and that happened on day 6. So here I've just put up a list of the very large number of organizations that were involved. It was a fantastic joint effort by all those involved. The emergency plan actually worked very well. So with such a major incident, of course, there are repairs to be done. So the interim measures involved the construction of a new auxiliary weir, properly keyed into the core, and some protective liner to the downstream face. And of course, we have to learn from the incident. The Canal and River Trust carried out their own investigation, but there was an independent investigation carried out by the UK government, and you can find that if you go on gov.uk and type in Toddbrook, you will find the independent review, all of the details of why this incident occurred. The British Dam Society carried out a seminar back in July 2020, and of course the future permanent repairs and replacement of the auxiliary spillway is ongoing. So that's it. Thank you very much. If you have any questions, please let me know.
So can we ask questions? So Mr. Alan Warren is present, so I think he can reply to the questions. So Mr. Warren, can you hear me?
I can hear you. Good afternoon.
Good afternoon. So my first question is whether spillway construction over an embankment dam is safe or is allowed in UK, because in India we don't have a practice of constructing a spillway over the embankment dam.
It's a great question, and it's never a preferred option. It was an option carried out 50 years ago, and I think we would not do that in the UK today. There are a small number of reservoirs in the UK with a similar arrangement, and those have been subject to urgent reviews to make sure that they are adequately safe. It's never a preferred option.
So this was an emergency option that was adopted.
I beg your pardon?
This was an emergency option that was adopted.
Yeah, you have to remember we have some very old dams in the UK. This was 1840, and our understanding of flood hydrology and tolerability of risk have much improved since 1840. And so, the dam, if it was built today, would never have been built with such a small spillway. So where we are now is we are trying to develop a new design, and it is likely that the final spillway will not be on the embankment.
Okay. So what was the probable cause of spillway failure?
So the government review has found that it's most likely crack injection. The high velocity flows stagnation pressures being created at the stone inclusions on the face of the concrete spillway, forcing water through cracks and basically turning the underlying material into a type of slurry, which then caused uplift of the slabs and release of this water over a number of hours. And then obviously once the void had created, then the slabs basically fell into that void. And then of course the overtopping water had immediate access to that underlying material and created the washing out that you saw.
In India also we have a number of old dams, so where because of upward revision of hydrology we have to provide some auxiliary spillways like this. So if after say 30 or 40 years of dam operation, I think it has consolidated, fully consolidated. So can we think of providing such type of auxiliary spillways for emergency use over such dams?
I think you have to be very careful with the design of the concrete elements to make sure that they are of good quality, that all the joints are sealed, and that there is no risk of any water getting in underneath the slabs. And this was the problem here, that the design and construction was not good, and some of those construction records had been misplaced. So the spillway had been effectively unsafe for 50 years, and it was only quite recently that the records, the construction records came to light, and there was an inspection of the dam in 2018, and it identified that there could be a problem here. But unfortunately, the storm event occurred before those investigations could happen. So we were very unlucky, because if the storm event had happened 1 year later, the chances are that this spillway would already have been under review and remediation. So it was very unfortunate.
Actually, I have read another paper of on this subject, so where it has been written that in the past also several floods have passed over this spillway, and it has performed satisfactorily.
Yeah, that's right. So it is possible that some form of deterioration had occurred over time, but we don't know very much information about those earlier events. So it could be that this was the greatest flood event that had to be passed on this structure. So there's still quite a lot of uncertainty. And of course, when the structure has been so damaged, it's very difficult to go back in and do forensic evaluation of the underlying condition, because it's already been destroyed. So this is a real challenge.
In another paper, I have seen some photographs. So I have seen some vegetation growth over the spillway. So I think there was some connection with the dam, and there was some cracks that have been developed.
Yes.
So I think water could have flown over through those cracks.
Yes,
and
that's
the
right.
dam material can also be then flown away or this washed away along with that.
This is correct, and there is a government review which will try to improve maintenance at UK dams going forward. So that we have lots of lessons to learn from this.
Okay, thank you.
Thank you.
Okay. So the next presentation is on assessment of concrete properties of Bhakra Dam in India. So I think this will be presented by Mr. Ojha.
Yes, please. So let me share the slides.
Okay.
So the assessment of concrete properties of Bhakra Dam in India. So we have conducted an study at Bhakra Dam, and we are presenting that case studies. The 50 years old Bhakra Dam, it was required to determine the in situ properties of concrete, and the basic aim was for the condition assessment and determination of engineering properties. And it was envisaged that those properties will be used for determining the modeling through finite element method to get reliable model output about the realistic deformations, stresses, inclinations, etc. to study unusual deflection of dam. And this engineering properties had been determined by our Institute, National Council for Cement and Building Materials, and it has been provided to the Bhakra Dam Authority. And probably they are going to present another one paper on finite element modeling, how those property has been used. So those paper, perhaps it is being presented in the same conference on 27th. So, so field studies, we carried out visual observations, then we carried out ultrasonic pulse velocity test, then we also carried out carbonation test, then half cell potential, resistivity test, in situ moisture content by humidity meter. We also conducted air permeability test and temperature measurements. In situ properties were determined. So these are the in situ properties: density, compressive strength, then modulus of elasticity as per IS 516, Poisson's ratio as per ASTM C469, split tensile strength as per IS 5816, drying shrinkage and moisture movement as per IS 1199, thermal coefficient as per CRD method. And we also carried out the microstructural studies of concrete covering alkali silica reaction and sulfate attack. So sometimes it is confusing whether the alkali silica reaction has happened or sulfate attack has happened. So we also carried out the microstructural studies of concrete. So these are some pictures of UPB test: in situ moisture content by humidity meter, resistivity test, concrete coarse extractions, half cell potential, and ambient temperature measurement at site. So findings of field studies are that it indicates no carbonation and no corrosion. So from the studies, we found that carbonation and corrosion has not occurred. The ultrasonic pulse velocity by surface probing, it was not possible to do the cross probing. So by surface probing, and the result varies from 3.56 to 4.03 kilometer per second. And based on this, overall quality of concrete was assessed to be good in general. And moisture content on upstream side varied from 4.95 to 5.2%. And on downstream side, it was around 4.64%. So on interpretation, it was found that results indicated that moisture content in the upstream side is marginally higher than the downstream side. And based on temperature study done, it is seen that there exists temperature gradient across the dam. So coefficient of air permeability for upstream site, upstream right and left bank, and galleries at 107 and upstream at EL 1608, downstream varies from 0.016 to 0.046 kT 10 to the power minus 6. And what it indicates? It indicates quality of near surface concrete in good category. So coefficient of air permeability for downstream right, left bank and galleries varied from 0.269 to 0.590, indicating quality of near surface concrete in normal category. Results of electrical resistivity ranges from 77 to upstream 95.37 downstream side in terms of kilo ohm centimeter. The test result indicate that moisture content in upstream side is marginally higher than downstream side, and same is confirmed by humidity meter test also. So concrete type, the concrete type A, 3 feet thick concrete on surroundings of galleries, and the concrete type B, the mass concrete portion, and the concrete type C, 6 feet thick concrete on upstream face. So field concrete strength are 17.25, 15.85, and 20.7. But concrete strength, equivalent compressive strength of concrete core, when it was taken, it was varied. And for the first case, it was varied in the range of 16.29 to 24.72, and average is 22. In the second case, B, 18.32 to 35.98. So this is a quite large variation, and this is because of the higher size of the aggregates in the case of mass concrete. And the average is 27. Of course, it is not the indicative of a good result as far as standard deviation is concerned. And in third case, again, it's a narrow range, 23.62 to 29.89, and average is 26.31. So Poisson's ratio in all the three, it is in the same range, 0.21, 0.2, 0.2. Modulus of elasticity, so 25265 for concrete type A, concrete type B 25955 Newton per mm square, and in second case 27691 Newton per mm square. Split tensile strength, in the first case it is 2.04, in the second case 3.39, and in the third case 2.52. Coefficient of thermal expansion, again 9.01 into 10 to the power minus 6 to 14.71 into 10 to the power minus 6 in the first case for concrete A, and in the similar range almost for concrete B also, and we can say in the similar range from 9.21 to 13.92 for concrete C also. And permeability, the permeability is in comparison to concrete A and concrete B, it is higher in case of concrete C. So in first case, it is ranging 3.07 into 10 to the power minus 11 to 3.10 into 10 to the power minus 11, and the third one 4.54. So these are the studies on aggregates. The aggregates were extracted from the taken course, and it was analyzed, and it was analyzed under optical microscope, and model composition analysis were carried out, and these are the percentages in terms of the model analysis. The different type of rocks were present. So we carried out ASR and intrinsic study. So one of the test, color test on were carried out. So when color test on downstream and upstream galleries were carried out, so we found we found
low ASR.
So low ASR in case of concrete, we can see from the color. And when the microstructural studies were carried out, the growth of complex intrinsic crystals were found. We can see the needle shape of the intrinsic cluster in the micropores. So in the micropores, a little bit growth of intrinsic crystals were found. But those intrinsic crystals were not detrimental in nature, because whatever the intrinsic crystals were forming, those were being accommodated in the micropores only. So it was not. It is not creating the pressure to the extent that any cracks formations is taking place. But this study also indicates that in future also this type of study should be carried out regularly, so that to ascertain that what is the extent of this type of crystal formation is progressing, so that future cracks, developments, or if anything detrimental effect is envisaged, that can be monitored exactly. So time to time this type of study can be carried out. So we carried out also the accelerated mortar bar test on extracted aggregate. Extracted aggregate were coarse aggregate and fine aggregate, and net expansion as per ASTM-C 1260. In case of coarse aggregate, it was 0.080, and in fine aggregate, it was 0.087. Residual expansion of concrete course in similar procedure as per ASTM-C 1260, it was in upstream, it was 0.040, and in gallery 0.049. So in case of aggregate, as the expansion is less than 0.1% in all the cases, then aggregates indicates the innocuous in nature. So alkali aggregate reactivity problem was not there. So residual expansion of concrete course as per ASTM-C 129. So average residual expansion of course in similar to procedure of ASTM-C 1293 varied from 0.0231 to 0.0271%. This average residual expansion after more than the 50 years is not at all significant, keeping in view that limit is 0.04%. and that too at the age of 1 year. And with this result, it indicates that alkali silica reaction is not taking place. So 2-3 results is clearly indicating that alkali silica reaction is not taking place. Only a delayed intricate formation in the micropores are taking place, and that has to be monitored regularly at a regular interval. So test results of rock samples. So we also extracted some rock samples, and those analyses were carried out. So modulus of elasticity was determined of the rock samples. Poisson's ratio as it is indicated in the table. So compressive strength, as we can see, rock samples compressive strengths are quite high. The weight density is in the range of 2643, almost in the same range, 2659, 2660, 2669, like that. Dry density, it is 2622 to 2642 in the last samples. And UPV results is quite low. So it was surprising, but it is clearly indicating that some cracks and fissures are present in the rock samples. Because of those cracks and fissures, the UPV results are quite low in comparison to the concrete. So what is the conclusion from our study is that field study indicates no carbonation and no corrosion. Quality of concrete as per UPV test in general is very good in rather. The test results of resistivity test, humidity meter and concrete cores tested in lab for drying shrinkage and moisture movement shows that moisture content in upstream part of the dam is higher as compared to the downstream part, and there exists differential shrinkage from downstream to upstream and along the height in the dam structure. And the most important conclusion is no silica reaction rims were observed between coarse aggregate and mortar in concrete cores. From the color test, sulfate in the form of pyrite. So if we see the nature of aggregate, so some aggregates are pyrite in nature. And what is pyrite? Pyrite contains sulfate in it, and that pyrite makes available in form of the gypsum, and because of the availability of gypsum from pyrites, ACM and petrography analysis indicates that some formation of delayed intricate in the micropores are taking place. So intricate found in a small magnitude in large void and will not cause any expansion rather, but it should be monitored regularly. In case of aggregates, as the expansion is less than 0.1%, so aggregate indicates innocuous in nature. Results of petrography studies, scanning electron microscopy studies, accelerated mortar bar test, and color test also, we have concluded that alkali silica reaction is not taking place. And whatever our recommendation is, we are recommending to conduct periodic inspection, as it is being emphasized by me again and again, on selected concrete samples after 5 years at least, to understand the growth rate of intricate formation in future. So this was our presentation. So thank you very much, and thank you very much for the organizations of Icold and accepting our papers. So thank you very much. Thank you to all. So if any questions, we are happy to reply. Sir, you are on mute mode. We are not.
Sorry. I will repeat it. So whether you also obtain the stress strain data of the concrete, including the plastic one, because you told that the data is to be subsequently used for FEM analysis of the Bhakra Dam.
So I don't know how they have carried out further, but we have not gone through stress strain behavior.
So you have not provided any stress strain data to them.
We were not asked by the Bhakra Dam Authority to do that.
Okay. So you have told that there are two factors that affect the durability of the concrete. One is the ASR formation, other is ettringite formation.
Yes, yes.
So,
Most of the dam.
Acha. For ASR, now we do regularly for new dams, ASR test we do at the start of the project. For astringite also, is there any test or anything we have to miss?
Actually, for intrigite, there is two things. The gypsum availability, because why intrigite forms, it's because of the cement which is being used in, what is the nature of the cement. And if the SO3 optimization, it's a cement technology rather, but I am explaining it. So SO3 optimization in the cement, if SO3 has not been optimized properly in the cement itself, then the whole C3A content will not be exhausted in the initial hydration process, and the C3A will remain available in their product, let's suppose monosulfate and intrigite. So if it is a monosulfate, then with the additional availability of gypsum from the aggregates like pyrite, and it will react and the delayed intrigite formation will take place. So that is also because of the cement, what is the nature of cement and how it has been optimized. And
my question is, can we undertake any measures at the construction stage or before the construction stage of the project so that this do not occur during the operational phase of the project?
If we are using the cement of moderate content of C3A, and it is aggregates are not containing pyrites, then there is no issue, because delayed intrigite formations will be there, but that will not be that much, which can create stresses in the pores which can result into cracks. So in those cases there is no problem.
So you mean to say that we have to take some measures before the design and the construction?
Definitely.
So another question is, once the astringite formation or ettringite formation starts, so is there any chemical or is there any procedure with which we can halt the formation of this?
No, sir. It's because of in microstructure of concrete, in every micro or macro pores, the intrigite formation will take place. So there is no measures when the concrete has been cast and it is existing. There is no measures to stop them.
Because you have said that we have to again check the health of the concrete after 5 years.
It has to be monitored. Actually, what will happen if intrigite formations is to the limit to the detrimental effect of dam?
So any preventive measures exist for this?
In new concrete construction, new dam construction, we have already discussed. In old dams which is existing in nature, so what will be the effect of intrigite formation? Like alkali silica reactions, we have to see there is any inclination because of the intrigite formations or because of alkali silica reaction. So whatever the measures we used to take for with respect to alkali silica reactions in terms of overall behavior of dam structure, that precautions will have to be taken if the intrigite formations has come to the limit, to the extent that it can affect the overall behavior of dam. But once it is not to the extent, then we can investigate and interpret that whatever the overall changes in overall behavior is not because of either intrigite or because of alkali silica reaction, it is because of any other reasons. So to find out the regions of abnormality in the behavior of overall behavior of the concrete dam, we need to monitor it. So this was my intent to conclude.
Okay. So there is one question from Mr. Prashant Rai. So he is asking whether the concrete strength that you have indicated, it is under saturated state or in a dry state?
It's a dry state.
So if we carry out
actually we have taken the course from the dam. We have taken those course at at our laboratory, and it had been tested as per 516. The procedure laid down in IS 516.
Okay, so if we undertake the test during the saturated state, what the results would be different?
A little bit higher by 1-2 MPa, because in that case, so in normal cases also, what is the effect on saturated concrete when it is tested, and when it is dry concrete is tested, that effect will come in this case also. A little bit 1-2 MPa it can be higher.
हाँ join करिए ना उसको.
So I think there is no other question. So thank you, Mr. Ojha.
Thank you very much. Thank you very much.
So now we move on to the next presentation. It is on evaluation of permitted risk level for age dams during survey and expertise. So I think this will be a recorded presentation and it will be played out.
Hello, my name is Venturov Mikhail. I'm from Moscow, Russia, from National Research University School of Economics. And the goal for the paper is Evgeny Venturov from University of Cambridge. And the topic of the paper is evaluation of the permitted risk level for aged dams during survey and expertise. The study is viewed as a part of a more general risk management process. The main goal of this study is to prevent the most dangerous accident accompanied by a breakthrough of the pressure front, the formation of the breakthrough wave, and destructions in the downstream. Risk management stages. Two main stages of risk management can be highlighted. Stage 1 is performed during the survey, planned or extraordinary, caused by any serious damage. And stage 2 is performed in the process of declaring safety and fulfilling the requirements of declaration. In Russia, the federal law on the safety of hydraulic structures regulates the need to draw up a declaration of dam safety. The results of a survey of an opening dam serve as the basis for the development of a safety declaration. Risk management stages are risk analysis, condition monitoring and assessment, risk assessment, and risk regulations options. They conclude survey results, conclusions, and offers. Separate components of the risk management can be repeated of each of its stages. Methods presented in the report. The following methods are presented. Digitization of initial ordinal estimates of the dam condition, formalized assessment of the condition for all dams, assessment of the acceptable risk level. The presented methods use risk factors, dam condition indices I, varying in accordance with the ordinal scale from 0 to 6. The presented methods uses risk indices, dam condition index I. The proposed methodology is focused on an operational application at all stages of risk management. Methods are single, complex, and locally linked. Three main conditions of hydraulic structures in operation are identified: normal, potentially dangerous, and pre-emergency. The transition of a structure into potentially dangerous state requires scheduled, as a rule, repair work. The transition to the pre-emergency state entails the introduction of the emergency response plan. Particular restrictions are imposed on the operating mode of a hydraulic structure, up to the reduction of existing loads and the evacuation of the population from the zone of possible flooding. Experience with our database shows that 9 levels of damage can be reasonably identified during the examination. Levels 7 and 8 are of particular practical interest because of at these levels, accident prevention measures can still be taken. Emergency condition, example. The achievement, the level equals 5 corresponds to an emergency condition. The process of transitioning to the structure from the pre-emergency to emergency condition clearly demonstrated, for example, by recent, which took place in 217-year accident and the 235-meter Oroville Dam. This accident developed from the 7th to 4th of February. The argument measures taken connecting an emergency spillway, dumping rocks into the crumbling zone, made it possible to stabilize the situation and prevent the formation of the breakthrough wave. Database and the scale of damages. Risk assessment can be performed in a deterministic or a probabilistic setting. Damage database and the scale was developed based on the results of surveys and damage assessment of more than 180 dams and tailing dams. The three database sections correspond to the three main processes that can lead to the dam failure. Filtration S, destruction and buckling D, crest overflow and breakthrough wave formation F. Each section contains damage levels, types of structures and corresponding lists of objects. Separate database tables are presented for a descriptive damage scale as well as for a detailed description of each object. Most of surveyed dams, 75%, have been in operation for over 50 years. The procedures for monitoring, inspection, and examination of projects for the reconstruction of old dams actively used qualitative baseline information when assessing and diagnosing their condition. Therefore, a formalized assessment of the results of visual observation is important, which in the study is performed using the I index. Expert assessment of the condition index I is based on a descriptive scale. Part of the scale, 8 damage level, is presented on this slide. Analysis of the practice of examining dams made it possible to designate an optimal range of initial expert assessments of index I. The boundaries of assessment corresponding to adjacent damage level are not clear-cut. This circumstance is typical for expert assessment. The quantification, digitization of the initial ordinal estimates of the index I is necessary, as is known, for performing mathematical operations. In this paper, the authors use a method of Shakhnov and his proposed formula, which you can see on the slide. The obtained dependence has two inflection points with a sharp, almost linear increase in the index IQ between them. Similar dependencies are widely used to formalize subjective expert assessments in psychology, medicine, sociology. This confirms the appropriateness of the applied digitization. The initial information is combined for condition indicators corresponding to the most dangerous of the entered stages of the structure. Within the same range for calculating the index I, the formula which is presented on the slide can be used. Formula is based on the application of some provisions of the theory of fuzzy sets. IE is condition index for indicators of structure or its components. Imax and Imin are condition indexes which corresponds to the borders of each band. Q, expert base parameter. P, multiplication sign. Detailed descriptions of the damages of each dam and the individual conditions, indexes IE, are presented in the database. The initial values of these indices, assigned by expert based on the results of the dam survey, were refined by the method of pair comparisons. A more detailed classification for the indicated 9 levels of damage is presented in a separate section of the database. The same sections provides a list of keywords used to identify dams analogs for the dam under study. Two options are possible for estimating index IE for a specific dam. Option A, damage of the surveyed dams are compared with descriptions of dam damages from the selected group, and an analog dam is selected and the IE index of the analog dam is assigned to the dam under investigation. If it is not possible to select a suitable analog, then option B is applied. A direct comparison of the dam condition with the aforementioned verbal description of the damages presented in the base. Assessment of index I on the scale of damages. You can see possible dam condition, normal, potentially dangerous, pre-emergency, failure mode, filtration, violation of strength and stability, as well as overflow over the crest. Damage level from 2 to 9, group of structures, concrete, reinforced concrete, earth, tailing dam structures, etc. Group of dam analogs, and specification of index IE for surveyed dams. If the index I is more than 3, it's necessary to analyze not only the dam condition, but also the consequences of a possible failure, G. In this report, assessments of the acceptable risk are carried out on the basis of the IG diagram. When creating the chart, the results of surveys of 14 dams were used. Estimates of damage from a possible hydrodynamic failure were made mainly by Shkolnikov. The cost estimates of possible accidents are presented in the 215-year prices. High estimates of damage level I more than 4 obtained taking into account all repairs during the period of operation, and not only according to the results of the last survey. Sorry. On the diagram IG, the experts identified the risk zones: unacceptable A, elevated B, conditionally acceptable C, acceptable D, acceptable for unique structure E. The boundary of the unacceptable risk zone is drawn from the dangerous zone, which presents data on I for the most damaged structures. Thus, when concretizing the position of the border of the zone of permissible risk, the premise was adopted: serious damage and the dangerous condition of the structure have already been achieved, but no destruction has occurred. Therefore, continued operation is possible subject to urgent repair work. The assignment of structures to the dangerous zone and fixing the position of its border was carried out on an expert basis, taking into account the definition of acceptable risk. Practical application of the developed methodology is carried out in the course of the following types of work. The first one, commission inspection, monitoring the operating condition. The dam condition is assessed based on the application of the proposed condition index IE.
Can we come straight away to the conclusions?
Scale. The second one, expertise of project options and economic justification for the effectiveness of the major repairs or reconstruction of the old structure. For structures in potentially dangerous and pre-emergency state, that is when index IE is more than 3, risk assessment should be performed based on the diagram IG. Preliminary reconstruction or repair options should be offered. The IG diagram is used to justify the best option based on varying combinations of index IE, the possibility of the failure, and failure-related damage. The method applies risk indices, dam condition index I, as well as physiologic methods to combine the initial quantitative and qualitative expert information on the condition of the operated dams. Database summarizes the experience of surveys and expertise for safety declaration of 180 hydraulic structures in Russian Federation. The diagram IG is similar to well-known diagram FN. The combined use of these diagrams defines the safety criteria for structures and can be used to quickly assess the risk of operating all dams. These were the main conclusions of our paper. The authors, me and my co-author, are grateful to Radkevich and Ivashenko for providing initial information of the results of dam surveys. Thank you for your attention. If you are interested in our paper, you can see more detailed information in the proceedings of the conference. Thank you. Bye.
So thank you, Mr. Gonkarov. So any questions? So, okay, I think the next session has to start. So I will just conclude this session. So I will just briefly summarize what has happened in this session. So in this session, we had 6 presentations and a variety of subjects were discussed, such as numerical simulation of a rock-filled dam, behavior founded on a clay foundation, then stress sensitivity analysis and monitoring of arc dams, importance of instrumentation in studying and analyzing dam behavior during its operational phase, assessment of a concrete dam material properties for studying its health and performance, and then finally categorization of dam health using indexes. So in the paper on emergency response during a spillway failure of the Toddbrook Dam, we came across a new technical measure, that is provision of a emergency spillway over an embankment dam. So this needs to be studied further, particularly for embankments that are more than 25 to 30 years old and have fully consolidated. This provision can be particularly useful where a dam after a few years of operation requires an emergency spillway due to upward revision of the design flood. However, it warrants sound design. The Toddbrook Dam spillway failure occurred due to inadequate spillway design. The paper on numerical simulation of the Rockfield Dam founded on a clay foundation provided details of the numerical procedure, constitutive model, and values of the model parameters, the importance of time duration of construction stages, and the positive impact of the time interval between different stages on dam stability. Then the paper on embankment dam instrumentation provides details of interpreting instrument data for analyzing dam behavior during its operational phase. A careful interpretation and correlation of instrument data with the design data is warranted to interpret dam behavior. The paper on arch dam sensitivity analysis lists out the conditions and factors that have to be kept in view while undertaking its FEM analysis and monitoring during the operational phase. The paper on Bhakra Dam lists out the details of the tests that were undertaken for assessing the material properties of the dam concrete. So only elastic material properties of the concrete were determined. Bhakra is currently the highest concrete gravity dam in India with a height of 225 meters. It is now 50 years old. Then finally we came across how to index-based scale can be used to assess the risk level of any dam. So overall, this session has been technically enriching. I thank all the presenters and all those who participated in the discussions. With this, I conclude the session. Thank you. So there is now one question by Dr. TV Thareja. So he is asking regarding Bhakra Dam. So is Mr. Ojha is present? I think Mr. Ojha has gone.
I can answer for him. So I'm a co-author on this paper. Right. So essentially, what we do is we compare with the ideal state, which is in the documentation. So what we do is we give a method for initial risk analysis, and of course it can be used even 50 years from now, or it can be used with the initial data. And I also want to emphasize that this is just for the initial risk, and it can be used at any stage of the analysis, and it's just one of the methods that we propose should be used.
Okay, thank you. So I think Mr. Oja has left. So Dr. Theja's question will be emailed to him. So thank you. Now I close the session. Thank you.
Chief Engineer Sibal.
Yes.
I will be chairing the next session.
So I am closing. I am closing.
That's fine. Thank you very much. And on behalf of the International Committee on Large Dams, and especially the Indonesia Committee, we'd like to continue to welcome you on this occasion. Since it's already 9:30 in Australia time and some part of Indonesia here, and in Far East, 7:30 p.m. So let me take the freedom of continuing this instrumentation in rehabilitation and upgrading of existing dams. Our session on the rehabilitation technologies to enhance the dam safety. Everybody, welcome. And I know that for some of you are continuing from the previous sessions. Please have your tea, coffee, whatever, and then let us continue to gear up technically. I just want to commence with today's session that will provide important opportunity to introduce some good practices of the rehabilitation technologies to enhance the dam safety for existing dams and their sustainable operation and maintenance. This particular session is one of the continuous sessions we had today on the rehabilitation technologies of the dam safety, which has been discussed since the morning in this hall number 2. So far, we have covered the 12 papers on innovation and adaptation in intakes, spillways, and gates, and 6 papers on cause of the damage and structural performance evaluation of dams. And we will continue to discuss the various aspects of the rehabilitation technologies today in this session, such as seepage control masonry dams, repair of a spillway and its energy dissipator, appraisal of its spillway capacity, modified energy dissipator study case, and so forth. Over the past 20 years, the World Bank has provided roughly about $58 billion for more than 430 projects involving the dam in over 90 countries. Now that we have more than 200 dams related to projects under the preparation and the implementation for water supply, irrigation, hydropower generation, and flood control. For example, in Indonesia, where I am presently located, represented by this Indonesia National Costume Batik, we have a large dam operational improvement safety project covering structural, non-structural, and institutional aspects of the 130 large dams operated and maintained by our government counterpart, the Ministry of Public Works and Housing. With a budget of $250 million. As we all know, in India, we are financing the dam rehabilitation and improvement project 1 and 2 with the total financing of near than $600 million. In a similar manner, we have the National Dam Safety Project also in Vietnam and in Sri Lanka as well. I have been fortunate enough to be involved in all these 4 large-scale projects for the rehabilitation in the 4 countries mentioned. And in all this project, one of our major challenges that we are facing is the selection and the execution of the rehabilitation technologies to enhance the dam safety and how to ensure the long-term operational and maintenance of dams and reservoirs. We, the World Bank, together with the client countries and other institutes, such as Icold, should promote and facilitate the access to knowledge and rehabilitation technologies available throughout the world for dams and reservoirs development and management. For this reason, I consider today's session on rehabilitation technology to enhance the dam safety a very important issues that we should continue to explore and share knowledges. I hope this session will be instrumental in rehabilitating and upgrading the existing dams in your countries and to ensure the sustainable operation. I look forward to hearing from those in the session and also to move forward this important agenda. Without spending more time on my introduction, let us start the final session on this rehabilitation technology to enhance the dam safety. Thank you. All right, let's start now. Each presentation will have 15 minutes. I'll let you know when your time is up. And if the time permits, let us have the questions and answers session to the presentation, if possible, at the end of the overall sessions. Okay. Therefore, may I request that all the presentators to stay on after your presentation. I have one more request that when you are not making any presentation or speaking out, please mute your microphone in order for us to be able to concentrate on the ongoing presentation. Okay. With any, let us start with the first presentation, which will be the seepage control in masonry dams with modern technology using innovative techniques, and execution methodologies. This is a case study of one of my favorite dams in southern India, the Bhavani Sagar Dam in Tamil Nadu by Engineer Suresh Balaji Rangarajan. Engineer Suresh, are you with us? Would you please start your presentation, please?
Let us start. Good morning
Yes,
to everyone.
please.
First of all, I would like to introduce myself. I am Suresh Balaji from Tamil Nadu state of India. I completed my post-graduation in structural engineering and I have been working as an assistant engineer in Water Resource Department of Government of Tamil Nadu state for the past 10 years. First, I would like to appreciate the organization team of Icold who have been waited for a year and conducting this event at right time amid the pandemic situation. And my sincere thanks to the technical committee of Icold members who have selected my content, and it's an honor to be here with you. And I extend my thanks to the supporting members from Icold, DRIP, and to the Ministry of Jal Shakti, Government of India. Here we will go for the presentation. My presentation speech under the sub-theme of Rehabilitation Technologies to Dam Safety, which is all about seepage control in masonry dams with modern technology using innovative techniques and execution methodologies. A case study of the Bhavani Sagar Dam, Tamil Nadu in India. Start up with the introduction. In India, we consider the dams of the hydraulic temples which would safeguard and serve the peoples in all needs by drinking, irrigation, infrastructure development, hydropower, etc., all from the time immemorial. In dams, seepage is the important criteria that we should consider irrespective of its dam type, material used, and construction methodologies. Seepage is nothing but it's a continuous movement of water from upstream face of the dam towards its downstream side. Technically speaking, no dam can be totally impervious. So we, the dam engineers, need to ensure that the seepage to the dam should be well within its acceptable limits. In the present modern era, We have a latest technologies, advanced in instrumentation, modern techniques, etc. And we should all try to accommodate and replace all those things to incorporate for a newly construction as well as maintenance of existing dams. Now the case study we are going to see is the Bhawanisar Dam, which was situated in Tamil Nadu state of India. The history of this dam project is all about, this is the first major irrigation project executed in India after its independence during the period 1948 to 1955. The total cost of the project was 1,034 lakhs, and this dam is of masonry cum earthen portion. The height of this dam is 62.18 meter, and this is the largest earthen dam of Tamil Nadu state, having a length of 8,780 meter, that inclusive of masonry dam length of 464 meter. The storage capacity of the dam is 929 million cubic meter, and the dam having a spillway discharging capacity of 4,078 cumax. The command area benefited by this dam is all about 1,60,000 hectares. Now coming part to the rehabilitation. Due to our long year usage of continuous of dams, this rehabilitation and improvement works in all segments of the dam components have been taken for an amount of rupees 1971 lakhs under trip, which was funded by the World Bank, and the same has been monitored by the CPMU, Central Water Commission, Government of India. And I am one of the engineers who directly involved and executed this work completely during the period 2015 to 17. So the rehabilitation works undertaken such as chutes, parapet walls, dam roads, renewal and repairs to the hydromechanical components, upgradation of electrical instrumentations, dam instrumentations, etc. And the main parameter is on seepage control, which is directly linked to the upstream phase treatment work to the masonry portion. So coming back to the technology, the modern technology we have adopted in the upstream phase treatment by using polyionide ceramic cementitious mortar utilizing crystalline technology, or we can use any other equivalent cementitious materials too. This upstream phase treatment technology is merely new to the Indian dams, and which was one of the innovative techniques to control the seepage flows in masonry dams as compared to the results of geomembrane methods as well as to the results of graniting methods. This technology comprising of 4 treatments: surface preparation, cavity filling, injection grouting, application of pointing mortar. The first step of treatment is the surface preparation. In India, on olden days, the construction of dam take place on the masonry portion by using lime mixed mortar, and due to the presence of water stagnation over a continuous period of years, this water pressure seeps into the mortars and thereby seepages may occur accordingly. So to prevent the seepage of water, the surface preparation will be done by, you have seen the first picture, we are racking the old damaged mortar joints to a depth of 50 mm using the hand drain machines with a diamond wheel cutter. So once after racking the joints, then second step is the cleaning the joints with the air blower machines, as well as using the high pressure water jet machine with the variable bar pressure of 30 to 250 bars. Like that wise, we can racking all the joints in the masonry portion on upstream side. The second step of treatment is cavity filling. So this shall be done by filling the cavities in the racked area using controlled shrinkage cementitious microconcrete. Microconcrete is nothing but it's a combination of cement along with high graded fine aggregates having size less than 10 mm along with fillers, adhesives, etc. So using this micro cementitious concrete with the water cement ratio of 0.16, this shall be applied in the racked area using pressurized gun equipment. And this micro concrete cavity filling shall provide a compressive strength of 40 Newton per mm square at 7 days minimum and 50 Newton per mm square at 28 days. And the material should not have any chlorine admixtures, and this material should have a controlled expansion characteristics at about 1 to 4%. So once after filling the surface preparation, we have go for the cavity filling. Then finishing this cavity filling, the third step of treatment is the injection grouting. This shall be done by the following ways. Initially, horizontally, we are drilling the holes to a depth of 300 mm with a dia of 25 mm in a triangular pattern at an inclined position. Approximately, we have taken the 4 to 5 points will be fixed in the 1 square meter area. This type of injection grouting is the innovative technique to fill all the internal cavities which was not visioned on the upstream side of the dam. So this is the first step of drilling horizontal. Then once after drilling horizontally, we have to make a fixing of PVC nozzles of 16 mm dia using this rapid setting cement. So after fixing, a water permeability test will be carried out by injecting water into the drilled hole with a low pressure pump up to a bar of 2 bars for a timing of 5 minutes. If the injected water travels smoothly, then the water will come from the adjacent holes. If the injected water not travels in the sense means we can increase the pressure bar more by 3 to 5 bars, then the water will easily get traveled. So while including the water into the drill hole, the timings will be recorded for the water permeability test. So once after finishing this test, we can go for a cement grouting test in a phased manner. The first phase of cement grouting in the ratio of 1:1 shall be applied using low pressure pump as per the timings recorded in the water permeability test. And after 1 hour, we have to go for a cement grouting in the ratio of 1:2 shall be applied. Like that wise, we can fill all the internal cavities on the upstream side of dam to avoid seepage in future too. And this grouting material should contain the following constitutions: OPC 43 grade cement with water cement ratio of 0.4, then adding a polymer rubber based latex along with non-shrink grout admixtures. And this grouting material shall contain a compressive strength of 35 Newton per mm square in 28 days tested in 10 centimeter cube. This injection grouting is very new to the Indian dams to fill all the internal cavities, as we are not seen in the upstream phase also. So the final treatment is the application of pointing motor. So once after finishing the injection grouting test, then make a cut of the sealed PVC nozzles and then clean the surface. Then make an application of prime coat with epoxy bonding agent. And then after application of raised pointing with 5 centimeter thick polymer modified cementitious high graded repair mortar system. And this mortar system itself is a self-curing compound, and this material shall comply with the minimum compressive strength of 45 Newton per mm square and 70 Newton per mm square in 7 and 28 days as on 5 centimeter cube. And these are all the 4 different type of innovative technologies and execution methodologies that we have adopted in our dam, and this yields a good results too. Finally, I would like to conclude with the results of the tabular column shown that the variation of seepage levels with the pre and post project, and adopting this embedded modern technologies using innovative techniques and execution methodologies has proved its successfulness in seepage control to a tune of 30 to 71% reduction of seepage in the pre and post project level. So during the execution of this work, we faced a lot of challenges as the water was completely present in the upstream side, and we are overcoming those issues day by day in a slower progress. And finally, we completed this project over a period of 2 years with a very satisfactory note. So that's all about my presentation, and I'm very happy and thankful to share my views in the dam field on this live event, and your feedbacks are most welcome. I'm also looking forward on the live event to get various ideas, some knowledges which will be shared by the dam expertise all over the world. Thank you for this opportunity. Thank you so much.
Engineer Suresh, thank you very much for very good example of the seepage control in masonry dams, which in many other countries that I have worked, it is well needed. I have some time finishing the 15 minutes. Are there any burning questions now to Suresh? Or can we move on to another very interesting discussion? Okay. Please ensure that when you have a question, send the chat to the coordinator, and then they will be forwarded through the chat system to these people who has access to the WebEx. Suresh, once again, thank you very much. And let me continue with another very interesting case from Maneri Dam. This is the repair of spillway, and then its energy dissipator severely damaged by the rolling boulders during the large flood case. This presentation will be made by Mr. Vinod Verma. Vinod, over to you. Are you there? There you are.
Our paper is on Maneri Dam, repair of spillway and its energy dissipator, severely damaged by rolling boulders during floods. So first of all, some project features of Maneri Dam. This is a 39-meter high dam, 127-meter long. The spillway has 4 radial gates of the size 13 by 14.55 meters. It passes a discharge of 5,000 cumecs, and it had a slotted roller bucket. The intake is here. As you see, this has 3 bays of 9 meters width, plus a all-weather channel on the left side. Then the sedimentation chamber over here, it has 8 hoppers, and the hopper size is this 15.7 by 515 by 5.75 meters. The head race tunnel which takes off from here is about 8.6 kilometer long and 4.75 meter circular, concrete lined. Then the third shaft is restricted orifice type, 69 meters high, 11 meters diameter. It has 2 expansion chambers, upper and lower. And the surface powerhouse has an installed capacity of 3 into 30 megawatts with a design discharge of 71.40 cumecs and a head of 140, design head of 147.5 meters. The tail race channel is 120 meters long. There were severe floods in Uttarakhand in the years 2012 and 13, which resulted in severe damages to this dam. So a brief description of the details of damages. In the spillway base, the 1 and 2, which are on the right side, the about 6 to 8 meters of 13-meter long sill beam of the stop lock gates and radial gates had got washed away. And a cavity of about 2 meter deep formed in between the stop lock and radial gates. And of course, there was at the same time there was erosion along the spillway glacis, about 3 meters in width with varying depths. The left side base 3 and 4 damages were slightly less. Between stop lock gates and radial gates, the eroded depths were of this order, 0.25 to 0.7 meters, and the spillway glacis also eroded to almost the same depths. The slotted roller bucket at the bottom was got totally damaged. In fact, there is no bucket to be seen now. Then at the same time, deep scour holes and cavities got formed in the bucket area, about 3 numbers, all supposed to be interconnected. And the spillway training walls, as you can see, were severely damaged also. The probable causes of damages is this, that the dam is already silted up to the crest, and big rolling boulders they come along with the flow and they roll down the spillway, causing tremendous damages. At the same time, the topography is also quite adverse. The dam is on a bend. There is a, as you can see, there is a bend on the upstream, there is a bend on the downstream, and then the river flows something like this. So the flow concentration in the different bays of the spillway are different. Flow is non-uniform, and more discharge flows through the right side. Then this hillock which is there, this is an obstruction to this flow, and because of this obstruction, there are return flows and adverse flow conditions. So these are the possible causes of damages. And before the trip, UJVNL carried out certain repairs, and they carried out repairs in the right side base. First of all, they tackled the area from between the sill beam of stop lock groove to the sill beam of radial gates. That is the area they tackled. And for that, they had to take a shutdown of some 36 days. And after this work was completed, they took up the work on the glacis of these bays. And that was done in powerhouse running conditions. A little bit of details of how these works were carried out. Repair works from sill beam of stop lock gates to 2 meters downstream of radial gate sill. This was taken up first. For this, a bund was prepared in front of the bays 1, 2, and 3, and the flow was allowed to take place through the extreme left bay number 4. First of all, the damaged concrete was removed. Then this dismantling of concrete also had to be carried out in some places to get a minimum thickness of 250 mm for new concrete. Then the double bars and reinforcements were placed, and over that the high strength concrete M80 was placed after application of bonding coat. After the placement of concrete, this a 20 mm thick MS plate was fixed over the concrete, and contact grouting of between the steel plate and concrete surface was done through holes cut in the steel plates. Then coming to the glacis portion, you see these are the, we can see the steel plates here. And this was also done in the almost the similar fashion, these repair works, except for the fact that instead of M80, they used M60 concrete. So then during the drip, we took up works mostly in bays 3 and 4, and these were the works which were taken up under drip. First was the realignment and reconstruction of the downstream training walls. As you can see, the training walls were converging. So these converging training walls were dismantled and they were made straight like this to improve the flow conditions. Then the repairs in the spillway glacis of bays 3 and 4, this was taken up under the drip. In the repairs of bay 3 were carried out with M90 concrete using steel fibers, minimum thickness 500 mm. I think probably in India, this is the first time that repairs have been carried out with such a rich concrete like M90. Then bay 4, with M90 concrete repairs were done, but without steel fibers. So in one bay, steel fibers were used, in the other one, they were not used. And for doing this, they made shear keys and anchor bars were placed. Bonding agents were used. Concreting was done from bottom to top. The concrete mix design and supervision of works was carried out by NCCBM Vallabhgarh. Then coming to the deep cavities, you see here below in the bucket area. So there were 3 such very deep scour holes, and they were supposed to be all interconnected. So for treatment of these cavities, what was first done was dewatering and cleaning. of the scour holes, followed by chipping of the concrete surface, and then they placed dowel bars, and these cavities were filled up with M20 concrete with non-shrink admixtures in 1 meter lifts. Then the top of concrete, finally, they placed a mesh 20 mm dia, 150 mm center to center both ways, and then that will be finally covered with high strength concrete as may be required for the energy dissipation. And the area around these cavities was in that area, consolidation grouting was carried out to close the interconnections. Then these were the works which have been completed under the DRIP. Now certain works are still proposed and yet to be carried out. One is the repair of the downstream face of the piers. So as you can see that the downstream face of the piers has also badly eroded. The reinforcements are exposed. So this is proposed to be repaired by steel cladding, 20 mm thick plates fixed with anchor bolts. And the space between the steel plate and the downstream face of piers will be also contact grouted. Coming to the energy dissipation, it has been seen that the slotted roller bucket has got totally damaged, and it's no more in existence in the project. So as we all know that slotted roller bucket is, especially the teeth are very prone to damages, and more so because of the rolling boulders here. So we do not propose to provide a slotted roller bucket anymore, and instead it has been proposed to go for a stilling basin, and that too without appurtenances, no chute blocks, no baffle blocks. The spillway was originally designed for 5,000 cubics, but the revised flood is 8,368 cubics, and it has been checked that the dam is likely to be, the dam will get overtopped with this flood. So this is another issue, and this is being looked into separately under DRIP 2 by planning additional spillway on the right bank, probably a side channel spillway or a tunnel spillway. The energy dissipation stilling basin, which is now planned here, has been designed for 5,000 cubic, which is about 60% of this 8,000 cubics. However, the maximum observed flood is only about 1457 cubics, which occurred in 2013. A 100 meter long stilling basin is planned, and the top 750 mm thickness would be in M90. Hydraulic model studies are presently under progress under IRI, Bahadrabad. So you can see this is how it will look like. This is the spillway section, and we propose to give a slope of 3 in 1 here, so that we don't do any excavation below the existing spillway structure. When we try to keep our excavations away from the main structure, and then this is the 100 meter stilling basin. So model studies are going on. In plan, it will look like this. There'll be the rock slopes here will have to be cut, and they would be treated by shotcrete and anchors, normal treatments, and this is what is planned, and model studies are underway. Coming to the conclusions, we have adopted different methodologies for repair of all the bays. In the first 2 bays before the DRIP, they had used steel plates. Now M90 concrete has been used with and without steel fibers. This M90 concrete has withstood 2 monsoon seasons successfully. And the construction of Stilling Basin, which is planned, is expected to help in improvement of the downstream flow conditions. However, long-term monitoring of the performance to study the efficacy of different kinds of repairs which are carried out will be required. Thank you.
Thank you very much for a very good example of dam rehabilitation improvement program of India. This is a case from northern state of Uttarakhand. Our electricity enterprise called UJVNN, Uttarakhand Jal Nigam Vidyut. Minari was one of our concerned dam, 5,000 cubic meter of discharge. Good case study on example of rehabilitation works, various concreting works with various mixtures, with fibers and other mixtures. While I'm getting some of the questions already, due to consideration of the time, please stay on, and I'd like to continue to the third presentation, but always great to see you guys from UJVNN. Let me move on to the third presentation of the appraisal of the spillway capacity and the storage augmentation for dam safety using the piano key weir, and fuse plug for climate change effect by Engineer Gopal Singhal and Dr. Nayan Sharma. Engineer Gopal, Dr. Nayan Sharma, the floor is yours. Are you there?
Yeah.
Great.
Yeah. Good afternoon. The topic is appraisal of spillway capacity and storage augmentation for dam safety using piano key weir and fuse plug in the backdrop of climate change. Here I'm Professor Nayan Sharma and my colleagues Dr. Gopal Das Singhal and Mr. Subhas Mukala. They have also contributed to this paper. Well, in the current context, especially in the backdrop of climate change, the urgency of dam safety cannot be emphasized more. Even India has 5,264 large dams, third largest in the world. And even the recent occurrences of several cloudburst events, as well as the very recent, on 7 February, the cloudburst in Uttarakhand, is a great reminder to us to take the matter very seriously. Now, again, the problem is we have so much, more than 5,000 dams, but bulk of dams are all hydel dams or irrigation dams, and most of them really do not have flood cushion. I'll briefly come across. In this background, there are serious flood in 2019 in Karnataka. Then in Maharashtra, again, 2019. Kerala floods are very severe in 2019, 18 and 19. And Uttarakhand, and even Northeast also, which is really under spell of so many flood stages. Next. Well, we are looking at a visual where Uttarakhand floods of 2013, which really devastated, and some more than 10,000 people really lost their lives. And Kerala floods has become almost a regular feature. Then this happened just on 7th of February, where 2 dams, one is the Rishi Ganga Hydel project, and downstream is the Tapoban Vishnugarh hydroelectric project. They have been really smashed. And we're looking at this figure of Tapoban hydroelectric project on Dhauliganga River. Well, there are many instances. One of the very important is the Bangkok Dam in China, where 230,000 people perished, and it is unbelievable. There was a massive rains of 1,000 mm, and spillway capacity was totally inadequate. It was only 1,742, and a flood probably was much more than that. And there was a huge breach of 400 meters. Well, again in 1979, Machu 2 Dam in Gujarat state of India was breached very badly. And again, the cause was inadequate spillway capacity, which was hardly 6,182 against the incoming flood of 13,139, which was more than 200%. And again, here some 4,000 or 5,000 people lost their lives. There are some other dams. I'm focusing on India, which are under distress, like Matatila Dam, built in 1964 on Betwa River. The spillway capacity is 15,857, whereas the upstream dam built in 1984, 50-kilometer upstream, has been given a spillway capacity of 34,000 cubic. And this dam in 1983 was under distress. Fortunately, in spite of having a bigger flood, the excess flood got accommodated in downstream depression areas, as we can see from this photograph. Like Tehri Dam was a classic example where a big devastation was averted. In 2013, and again, the other floods also, 12, the Tehri Dam could absorb a huge amount of flow. Sudden cloudburst flood came, and all the inhabited downstream areas, especially the cities like Rishikesh, Haridwar, Deprayag, were saved. Now, let's try to understand what is the root cause. I think the best example I have chosen is Idukki Dam in Kerala state and Idamalaya Dam in, again, same basin, Periyar Basin. These two are basically hydel dam, Idukki, mainly hydel, and there is Idamalaya, which is mainly an irrigation dam. And there is one more upstream, Mulapariya Dam, that's also primarily irrigation. These dams have not been provided with flood cushion, and that are the reason why it cannot accommodate the excess flow that comes during extreme precipitation events. So I believe this visual brings what I'm saying in a very succinct way. Like most of the reservoir, like in case of Idukki and Idamalaya, which are in the same basin, in 2018, they were almost full, more than 92%, 97%. A flood, heavy precipitation occurred. So where to store it? It has to go downstream, and it really created huge devastation. And that kind of thing still happens because they totally do not have any flood control storage space. This is carrying forward of the same basin, and where we can see that these two dams and other dams, also Mulapariya downstream areas, they really do not have flood cushion. And even the storage of the flood carrying capacity of the Periyar River, for instance, really is just enough. So if more discharge comes, then it always spills the banks. Now, in this backdrop, let's try to understand what can be the solution of these all existing standing dams. Well, in this context, I'm really fortunate that I could work for some time with the EPFL in Lausanne, and like Dr. Lamperier, who is a pioneer in piano keyware. He was kind enough to give to IIT Roorkee some funding, not only funding, but also technical know-how and inspiration to go ahead with studies on piano keyware. And in this context, I will highlight that piano keyware is a very innovative and highly cost-effective, because I have my own experience in one hydel project in Himachal Pradesh, Power Corporation Limited on Pabbar River. The cost per generation was very high per megawatt. So it was almost shelved. But when we transform this conventional dam or barrage into a piano keyware with few bays on both sides with gates, the cost came down drastically. And as a result, the Asian Development Bank, who were reluctant to, or rather they were rightly hesitating to finance because of high cost per megawatt, they agreed to go for and this project, 110 megawatt. And finally, I'm glad to share with you that a major hydel project in India, that is Saurakuddu hydroelectric project, is now built with piano keyware, and it is now practically generating power. And in Europe also, in so many cases like Bullers, Saint Mark, Latroit, Gloriets. Similarly, in Vietnam, Van Phong barrage, and obviously I spoke about Saurakuddu. And one advantage with these that it can hydraulically much more efficient than conventional Ogi spillway, because it can pass 2 to 5 times. And in recently, there is a big advancement going on where arc-shaped trapezoidal piano keyware is being considered for research. It's going on rather in Iran and some other places, which can pass more than 5 times of a Ogi spillway. Well, this is a visual showing the physical model studies which we did in IIT Roorkee in 2010 on piano keyware. This one shows that this is in the piano keyware shown here, and this is in running. And this is the Saurakuddu project, which is completed. This is now complete, and it's in generation mode. And on the right side, you can see in the France, a 60-year-old dam has been converted into piano keyware by Dr. Lemperier's guidance. So there is one more advancement again by Hydrocorp that is based in Paris, that is using fuse plug. So fuse plugs are emergency measures and protects the main dam from failure. It gets in extreme flood completely washed away, but it doesn't allow the dam to get breached and protects it. And there can be concrete fuse plug, and there are also earthen kind of fuse plug as used in Australia, like Copperton Dam, and in US, Douglas Dam, and there even in Africa, this Wedbila Dam in Burkina Faso. So these are very good examples where the fuse plug technique, which is very simple, and it is designed in such a way that once water level goes some height above the crest, then the whole fuse plug tilts, and it ultimately gets washed away. So it safeguards the dam from breach. Well, this again is a photograph I have taken from Hydrocorp. And here we can see that there can be a combination of piano keyware as well as fuse plug. And the advantage of together is that piano keyware will be able to pass 2 to 5 times more discharge than a conventional spillway and be ungated. And at the same time, fuse plug will be able to help in case of emergency to pass more discharge, as well as it can create more storage. That is the beauty. and that more storage can be used for irrigation, for flood cushion. And in this case, we are thinking for flood cushion, and only in exceedingly high discharge, it will get washed away. So this, again, Dr. Lemperier's great contribution, and I am one of his proteges, I can proudly claim to be. Well, with this background, we try to carry out some analysis, very preliminary, in Shivnara University for Matatila Dam. And in Matatila, upstream, there is another dam called Rajghat. Matatila, which was built, constructed in 64, Rajghat is another 30, 40 years later, 50 kilometers upstream. So the upstream, as I told you already, has a higher discharge spillway capacity compared to this Matatila, which is just upstream of Jhansi city. Now this we can strengthen as per our study that if we go for piano key where the current spillway capacity can be increased from 15,000 to 20,000 cumac, and it can prevent any bank spillage. And that will again be considered two kind of PKW height. One is 7 meter height, or other is 10 meter. In case of 7 meter, 8 bays we can handle. If we go for 10 meter, number of bays can be reduced. And the beauty is we can still maintain H by P ratio, head over crest by height of the crest ratio 0.8. So that means, as done in France, all the old dams, all in France, all these dams are more than 50-year-old, and they have been installed with piano cuvée. So these can be done same way in Indian dams as well. And with fuse plug, we just tried a hypothetical study, and we found that it taking up the same discharging capacity of the upstream Rajghat Dam, that is 34,000 cumac, and we consider a residence time of 18 hours, and then we can still safeguard the dam, because downstream of the Matatila Dam, it can handle, the banks can handle a flow of 20,000 cumac, and with a fuse plug height of 3.75 meter. Well, similarly, we try to work out this just hypothetical study for Idukki, which is under great throes of every year heavy flooding. And in that case, we found that if we take the revised flood inflow of Central Water Commission, that is 9,402, and have a 12-hour residence time, then we can still manage we can prevent, we can avoid any bank spillage, because we'll be releasing only 5,000 cumac, which is well within the bank full capacity of Periyar River. And we need only a fuse plug height of 2.8 meter, 8.9 meter. But if zero spillage, if we don't want to spill anything, then we can manage with 4.5. We would later consider 2.89 with some spillage. Similarly, for Ida Malaya Dam, a revised flood spillways, as per CWC, 6,547, as against a spill of capacity of 3,000 cumac. 12-hour residence time is possible, and fuse plug height is 3.54 meter, and that was a great solution we can think of. But this is, let me point out, is just a preliminary hypothetical study, but it brings out great prospects, and it can really be a complete revolutionize the idea that existing dams, as done in France by Dr. Lemperrier and his team in Hydrocorp, existing dams can be safeguarded against flooding of downstream as well as their own safety by going for piano cuvée, as we have done in Himachal recently for Saurakuddu project, as well as using fuse plug, we can also further enhance the safety.
Dr. Can you wrap up, please?
Okay, I will now complete now. These are some of the initiations we have started. So my summary is that the existing dams needs to be provided with flood storage capacity, and that is possible. And the huge disaster on 7th February in Dholiganga River is a wake-up call for all of us. Thank you for your kind attention.
Thank you. Thank you, Dr. Sharma. It's great that dam rehabilitation project is also continuing the discussion, cooperation, coordination with academics. Great presentation from the IIT Rookie. Thank you, Dr. Sharma. Thank you, Dr. Gopal also. On the real interesting technology of the piano key weir and the fuse plug application to increase the spillway capacity as well as the reservoir capacity. Several questions I've received already, but let me see if the time would permit. But I really thank you for this this presentation. But let me move on to the next presentation, which is restoration and rehabilitation of spillway with modified energy dissipator. This is a case study from engineer Amit Kulhale. Engineer Amit, are you there?
Yes, sir. I am here.
Wonderful. The floor is yours. Please go ahead.
I have submitted the recorded presentation. I think Mr. Yogesh from the virtual MNC can help me in this out. Central Water and Power Research Station, Pune, India. My paper title is Restoration and Rehabilitation of Spillway with Modified Energy Dissipator, which is basically a case study. In the present paper, the model studies conducted at Sidul Paris for Indra Sagar project, Madhya Pradesh, has been described. This picture shows the aerial view of the project site. Indra Sagar project is situated on the river Narmada in Khandwa district of Madhya Pradesh. Indra Sagar is a multi-purpose project with an installed capacity of power generation of 1000 megawatt and provides irrigation benefits to about 1.23 lakh hectare. Indra Sagar is a 600 meter long and 92 meter high gravity dam with the curved dam axis having a radius of 850 meter. Main and auxiliary spillway comprises 12 and 8 spans respectively of size 20 meter by 17 meter, and it is designed to dispose of a PMF of 83,400 cubic. The project is in operation since 2004. This picture shows the layout of the project. This is the main spillway and this is the auxiliary spillway. A surface powerhouse is there with a power generation capacity of 1000 megawatt with 8 units of turbine. A 530 meter long headrace channel has been provided to divert the water towards the powerhouse from the reservoir, which is followed by the tail pool and about 850 meter long tail race channel. A downstream protection wall in the downstream of this auxiliary spillway has been provided to prevent the water flow towards this tail pool. As per the original design, the energy dissipator was in the form of slotted roller bucket with different bucket inverts level for both main and auxiliary spillway. We know that the energy dissipator are designed with the help of existing design manuals to give satisfactory results for a given design condition. And if the operating condition differ from the design conditions, it may give unsatisfactory results and consequent damages to the appurtenant structure under the transient and unsymmetrical flow conditions. This picture shows the damages to the ski jump bucket of the main spillway. It was observed by the project authority that during every monsoon, the bucket area of main spillway gets damaged and there is a recurring need to restore the damaged area. During the site protection inspection of the design and project engineers, it was observed that the spillway glacis and slotted roller bucket of main spillway have been damaged badly. The spillway was operated continuously for a considerable time during the year 2013 flood with high discharge of the order of 20,000 to 35,000 cubic. It was concluded based on the theoretical calculation and site observation The damages to the energy dissipator are due to hydraulic as well as the structural reasons. Deficient tailwaters during the initial period of the operation of leading to the ski action and generation of high hydrodynamic pressures during the roller formation due to high incoming velocity of the order of 35 meters per second. And negative pressures on the teeth were few the hydraulic parameters leading to the damages to the bucket. Then it was proposed jointly by CWC and CWPRS to provide ski jump bucket in place of slotted roller bucket, considering the prevailing site conditions, hydraulic and structural and economical aspects. The ski jump bucket with a bucket radius of 50 meter, invert elevation about 199.75 meter, and lip level raised by 10 meter at elevation 210 was designed by CWC in consultation with the CWPR. Hydraulic model studies were conducted on a 1:60 scale 2D sectional model for assessing the performance of proposed energy dissipator and finalizing the design of main spillway. Studies were conducted in a 1 meter wide flume at CWPRS Pune. This photo shows the flow condition for 100% ungated and 50% gated operation of the main spillway. And it was observed that the clear ski action for discharge up to 50%, that is about 18,000 cubic for gated and ungated operation of the spillway. And submerged ski action was observed for higher discharges. The throw distances were found to be varying between 52 meter to 72 meter for ungated and gated operation of the spillway for various discharges. Thus, it was concluded that the performance of spillway and ski jump bucket was found to be satisfactory. It was also shown that the flow was cascading over the bucket while passing the lower discharges. Therefore, a 15 meter wide concrete apron may be provided downstream of the ski jump bucket with the end key firmly anchored to the fresh rock to prevent the undermining of the spillway toe due to cascading flow. Then, as per the recommendation of CWPRS, CWC, and the dam safety panel, it was decided to conduct the hydraulic model studies on 3D comprehensive model for assessing the performance of ski jump bucket, flow condition emerging at the junction of the outlet of the channel of main and auxiliary spillway, and in the vicinity of tail rest channel of the powerhouse. This slide shown the photos of 1:130 scale geometrically similar 3D comprehensive model of main and auxiliary spillway constructed in a closed hangar at CWPRS as per the recommendation based on the studies conducted of the for the main spillway on 2D section model. The model incorporates the main spillway, auxiliary spillway, 8 units of powerhouse and tail rest channel, and a river reach up to 1.3 kilometer in the upstream side and about 2 kilometer in the downstream side of the dam axis was reproduced with smooth cement plaster. And also a high level bridge which is called HLB situated at about 600 meter downstream of the dam axis is also reproduced. Then hydraulic model studies were conducted for assessing the discharging capacity of the main spillway as well as the auxiliary spillway and combined operation of the spillway. These two plots shown the discharging capacity curves. For first one is the only for the main spillway and the second one is for the combined operation of the main and auxiliary spillway. It was observed that a discharge of 32,800 cubic could be passed at FRL elevation, which is 262.13 meter, and for 12 spans fully open for the main spillway. And it was seen that a discharge of 36,600 cubic could be passed at NWL elevation of 263.35 meter with all 12 span fully open of the main spillway. It was also observed that the discharge of 55,700 cubic could be passed at FRL elevation with all 20 spans of main and auxiliary spillway, and also a discharge can be passed about 62,500 cubic with at MWL elevation for all 20 spans fully open. Studies were conducted for various combination of main and auxiliary spillway. And this video shows the ungated operation of main and gated operation of the auxiliary spillway at FRL elevation until the water overflows the downstream protection wall towards the tail rest channel. Downstream protection wall has been provided to prevent the flow of water to the tail pool of the TRC downstream of the powerhouse. It was seen that a discharge of 37,000 could be passed with ungated operation of the main spillway and gated operation of the auxiliary spillway, which is partially and equally open by keeping the opening about 1.58 meter from the crest elevation. And it shows the auxiliary spillway can only pass the discharge of 4,700 cubic when the water level touches the top elevation of the downstream protection wall. And performance of spillway of the bucket of main spillway was satisfactory as clear ski action was forming. No roller action was seen in the bucket of the auxiliary spillway. Hydraulic jump was seen forming in the bucket and flow was cascading over the apron. And hence the performance of slotted roller bucket was not satisfactory as no roller action was seen. Finally, the flow was seen entering the main river of the main spillway, falling over the 60-meter wide cut provided in front of the divide wall between the main and auxiliary spillway. Now we will start the video. This is the main spillway flow with the ski jump bucket. We can see here the stagnation. This is the reservoir portion. And these auxiliary gates are partially open, equally partially open, with opening of 1.58 meter. We have calibrated this opening to prevent the water flow towards the tail rest channel. And from the auxiliary spillway, the water comes through this 60-meter wide cut to the main river channel. And we can see the flow is concentrated along the right bank. And along the left bank, a mild return flow have been seen here. After the conducting model studies, the modified design of the energy distributor as a skiing bucket of the main spillway as suggested by schedule PRS is adopted and implemented by the project authority, and construction was completed in the year of 2000. After the conducting model studies, modified design of the energy distributor as a skiing bucket for main spillway as suggested by schedule PRS is adopted for implementation by the project authority, and construction was completed in the year of 2018. The performance of a spillway and ski jump bucket was found to be satisfactory. It was also seen that the flow was cascading over the bucket lip while passing the lower discharges. Therefore, a 15-meter concrete void have been suggested for the construction. After the construction of the energy distributor of the main spillway was first operated during the month of August 2019. CWPRS officers along with the design engineer and project engineers witnessed the performance of the newly constructed energy distribution arrangement in the prototype. During the model studies conducted in the 2D sectional model at CWPRS, it was observed that the flow over the ski jump bucket was cascading till the gate opening 3 meter for equal partially open of all spans, while raising the gate gradually with the reservoir level up to elevation of 261.4 meter. And the model based result and observation were compared with the prototype measurement and operation to evaluate the accuracy of model behavior. In this connection, the same gate operation with gradual raising of the gate at an interval of 0.5 meter till 3 meter gate opening were tested in the prototype. It was seen from the figure The flow was cascading over the ski jump bucket in the model, also in the prototype, for the gate operation of 2.5 meter of the main spillway. Now this figure shows the partial gate operation of the main spillway at RWL elevation 261.4 meter, with all gates partial open with the gate opening of 3 meter each on the model as well as in the prototype. It can also be seen the ski jump bucket was formed by the ski jump bucket in the model, also in the prototype, when the main spillway was operated gradually with the gate opening of 3 meter with all 12 spans partially open, with the RWL elevation about 260.75 meter in the prototype. This video shows the transformation of cascading flow to the ski action while increasing the discharge from the spillway gates by increasing the gate opening of gradually for all spans of the main spillway. Use the prototype flow control. While CWPRS team has visited the project site during the August 20, 2019. Presently, gate opening is 2.5 meter, and we can see the cascading flow in the bucket. And while it gradually increases the gate opening of 3 meter, the cascading flow converted to this ski action. Now, based on the model studies conducted on 3D comprehensive model with various combination of spillway, it was suggested to remove the debris laying in front of the main spillway at site and to review the design of the bridge piers and consider the strengthening of the high level bridge piers if required to sustain the high velocity flow coming from the main spillway after the modification of the energy dissipator for roller to ski jump bucket. And it was also suggested to provide a plunge pool to reduce the downstream velocities near the bridge and to avoid the uncontrolled erosion of the riverbed and banks. And as a slotted roller bucket of the auxiliary spillway is not performing satisfactory for any of the operating condition, there is a necessity to provide a tail channel in front of the auxiliary spillway so as to guide the flow towards the main river channel for the discharges higher than the 4,700 cubic. Performance of slotted roller bucket is extremely sensitive to the tail water levels and primary cause of unsatisfactory performance of the same and consequent damage. Therefore, the slotted roller bucket should be designed carefully and comprehensive model study should be conducted before adopting the design for execution on the prototype to avoid recurring damages of the energy dissipator and to ensure the satisfactory performance of all possible scenarios. CWPRS has been associated in evolving new and efficient design by conducting model studies for several spillways during the last few decades and has witnessed a number of new developments in the design. Hydraulic model studies conducted at CWPRS Pune, which played an important role in modifying the overall performance of energy dissipation arrangement of main spillway, and the prototype investigation fully interpreted the model results, thereby showing the model prototype conformity. Thank you all. Thank you.
Amit, thank you.
You may ask.
Very much for this. Very interesting case from Pune from our Central Water Research Center in Pune on the Indira Sagar Dam for Madhya Pradesh. I'm so glad to see that the research institutions are also supporting the dam safety sectors in India and hope that will be the same in other countries as well. Amit, please continue to stay with us. Should the time permit, I'd like to accept some of the questions. Otherwise, questions are welcome, and then we will be sending you for your future bilateral discussions among yourselves.
Okay, sir.
I'd like to, yeah, okay, Amit, thank you very much for your presentation.
Thank you, sir.
I'd like to continue and to have our final presentation of this session. It is a case study from Mussel Dam, a multinational dam foundation rehabilitation effort that on a large scale. This is from Viraj Mariala. Viraj, are you there?
Just a clarification, Mr. Malyala was our presentation coordinator and submitted the paper, but this is David Sawicki with AECOM, and there is a recording there, and I'm actually the paper author here.
Sure.
And I'll go on for the end.
Wonderful, David. Thank you very much. Floor is yours. Go ahead, please, David.
Hello, my name is David Sawicki. I'm a vice president with AECOM, and I will be presenting today on the multinational effort to rehabilitate the foundation for Mosul Dam. I appreciate everyone in attendance, and I want to acknowledge the Corps of Engineers and the Ministry of Water Resources for working with us on this project or allowing us to support them. AECOM worked for the Corps of Engineers as part of the Mosul Dam Task Force, which was there to help stabilize and do an emergency grouting of the foundation underneath Mosul Dam. The top right photo in this slide will show you the dam from an aerial shot. It's a little over 2.2 kilometers long in the main dam. Overall, the dam is 3.4 kilometers long, but that includes a fuse plug spillway and saddle dam you don't see in this image. The dam is located just north of the city of Mosul. It is the largest dam in Iraq, and it's constructed across the Tigris River Valley in an area of geology that is less than ideal for dam building, but for a number of other reasons was critical to be built in this portion of the country. The dam is critical from a flood control, irrigation, water supply, and hydropower standpoint for the country of Iraq. And the watershed for the dam extends well up into Turkey and northeastern Syria. It holds a little over 11 billion gallons, excuse me, a little over 11 billion cubic meters of water. The dam itself is a well-constructed earthen embankment dam, but it was constructed, as I said, on a deep deposit of geology that includes gypsum, anhydrite, limestones, and other calcareous marls and rock units that are all susceptible to one degree or another to karst dissolution. The gypsum and anhydrite units being most particularly in critical nature. The designers recognized this and realized they needed a cutoff and an ability to maintain that cutoff over time. And so they built the dam with a grouting gallery at the bottom center of the dam axis. So in the cross section you see in the top right, you'll see the red circle surrounding or circling the grouting gallery. The three details below that indicate or illustrate the cross section of that gallery in different portions of the dam. And then down the bottom left-hand side of the screen, you'll see a profile looking downstream of the dam from a little over, well, the gallery runs 2.2 kilometers from one side to the other side. And the dark line at the top of that profile represents the top of the dam. The gallery profile, the red line, shows the construction of the gallery on top of the bedrock across the Tigris River Valley. And so in some cases, it's up to 80 plus meters below the top of the dam. The risks posed by the dam were captured in a number of probable failure modes prior to arriving on the dam site, with what information could be gleaned ahead of arriving on site, where most of that information was in a library at the dam site. So we didn't have access to that before we arrived. And you can see the number of probable failure modes and where they plot on an FN chart. The most striking aspect of this FN chart is the consequences associated with a failure, where if the dam were to fail catastrophically, on the order of 500,000 people were likely to lose their lives. And you can see that all those failure modes are plotting in regions where well to the right of the traditional line for acceptable risk. So it was an emergency grouting team that went in to prevent the dam from deteriorating, or the foundation from deteriorating, which could have compromised the dam. There were two main phases of work, although those were somewhat more tied to contracts and maybe a little less tied to the actual work to be done. And in each phase, there was a major grout line from one end of the dam to the other that was completed. The emergency one on the first was a lot of learning done and a lot of construction of infrastructure was being completed at the same time. We went in with the intention of grouting 50 meters beneath the gallery floor. However, as we were going in and drilling through the previously drilled grout holes, we found many holes that were open and were not filled with grout. So ultimately, we chose to deepen those grout holes to the full depth of what had been drilled in the past, typically between 70 and 100 meters. And then there were a number that did go as deep as 150 meters beneath the gallery floor. And each hole was pressure grouted in stages from the bottom to the top. Typically, we're using the upstage method of grouting. Where necessary and where the formations wouldn't allow or stay open, we use the downstage methods. In phase two, another major element of the project was the training of and integration of the Ministry of Water Resources staff into the processes the contractor was operating, and using the new techniques, automated systems, and the new equipment. Some of the operational challenges we experienced in executing this project, the infrastructure that was there at the dam was all from 1985 by and large. There was not a lot of very current equipment, and Trevi brought all of that in from Italy, outside the country, so that was a challenge. There was obviously a security situation in northern Iraq in 2016 when we arrived, which was just prior to the start of the offensive to retake the city of Mosul from ISIS. That was going on, and during the time that we were there, the dam itself, the security provided at the dam switched from Kurdistan or Kurdish forces to the regular government of Iraq army, which made for some interesting times. Getting materials and tools, we basically discovered you bought extras, you brought them in and you staged them and waited until you needed them. That was a constant challenge. The contractor also had to build a camp for 1,000 people for us to live, eat, and stay together. And that was a challenge, but it also meant that we were all together in one place. And as I mentioned, there was limited technical or historical information before we arrived on site. So we had to glean and gather and learn all that once we got on site. The upgrade challenges, the contractor built 3 brand new grout mixing plants to provide grout to any operation wherever we were grouting. They then pumped that in pipelines into the gallery from outside, where it was then used for direct or converted to other mixes. All of the water lines, electrical and fiber optic cables were new. There were 18 new drill rigs, and we rehabilitated 6 of the existing drill rigs on site. Customizing equipment for special needs in the limited space of the gallery was another challenge. In addition to upgrading the electrical, also the ventilation and all of the lighting and the dewatering of the gallery was all upgraded. The batching and grouting units in the gallery that were used in the gallery or on the crest of the dam, there were 32 brand new units brought in throughout the entire life of the project. And there were new office buildings and new repair shops also built to service all of this new equipment. And we mentioned the 1,000-person camp. Management challenges. From this task force standpoint, our staff was there, and as well as was the contractor, we were working 24 hours a day, 6 days a week Contractor was actually working on the 7th day, but that was generally used for maintenance and layout of planning for new production. Working with reachback staff in the United States or in Europe, we were dealing with time zone changes that were upwards of 8 to even 12 hours, depending on which part of the country we were reaching back to. And we were under a deadline to aggressively get this project completed. So that was another pressure. We had workers coming from all over Europe and Asia, as well as the Middle East. So we were anywhere from 5 to 10 languages were being spoken in different parts of the site at any given time. That made for some communication challenges, naturally. And just working in another country where you dealt with holidays that presented delays in Europe, and potentially at sometimes, and then you had the Middle East holidays, including Ramadan, each year would create other challenges. So what worked? One thing that worked very well was we were all living together, and that meant that we were all talking together, and we had plenty of problems and challenges, but because we were all right there working together around the clock, we solved problems quickly and found solutions, and we were able to roll those solutions out and communicate them to staff and get people trained to use the new processes as they came up. That meant that where we needed to adjust drilling or grouting for a complex geology at the site that varied not only with depth, but also as you moved across from one end of the dam to the other, meant that we had a whole series of processes that were critical to be applied in different locations. Certainly the configuration and moving in tight gallery space was still a challenge, and health and safety in Iraq was not always what we would expect it to be certainly in the United States. There were certainly challenges there at different points. The photographs you see here on this slide, two are looking down the gallery length, and you see the infrastructure strapped or attached to the walls or in cable trays. That's how the materials were brought in, as well as wastewater getting pumped out. And I won't read the rest of the accomplishments here, but the contractor did install over 170 kilometers of new cables at the dam, as well as 4.5 kilometers of new pipelines. So I think very, very significant work. The bottom right photograph is one of 3 main mixing plants with their associated silos of materials to produce the base grout mix. The grout mixing plants were supplying, of course, the drill rigs and the grouting units in the gallery, and the main plants could produce batches to the amount of 1.5 cubic meters of mix in each batch. And then the batching and grouting units in the gallery would tap off of those lines and produce 100-liter grouting batches that were then pumped into the holes. In addition, to keep communications going, over 2.5 kilometers of new fiber optic and internet lines were installed to connect with the control room, where all of the grouting was monitored, captured, recorded, and then instructions were sent out for what was to be happening at each hole as it was happening, as it was being grouted. So a great deal of oversight and capture of information, all automated to allow you to go back and look at it afterwards. I mentioned the complexity of working across the dam, and we developed the Mosul Dam Playbook, as we affectionately called it, which is a complete set of instructions of what to do in different portions of the gallery or on the crest of the dam where we were drilling and grouting, and how, when you ran into different conditions, what you were to do. And it was critical to have it translated and have it communicated to all the teams so that they knew how to operate in different places. So other accomplishments, again, as I pointed out, the phase 1 and phase 2, the dates of those are listed here. Those were more tied to contracts than they were necessarily to specific elements. But overall, I think some of the superlatives in this project was that we drilled and grouted almost 5,400 holes on the project. Of those, 4,200 and almost 4,250 were in the gallery. we injected almost 41,000 cubic meters of grout, and that meant that the number of meters of actually holes drilled was 667 kilometers of length of holes. The highest take in any one hole was 422 cubic meters, for just some other additional gee whiz facts. So accomplishments, the training and integration of the Ministry of Water Resources staff. This was a critical element of the phase 2, where we were training the ministry workers to be able to take over the work, whether it was related to drilling or grouting, management, the control room operation, whether it was dam safety, rig safety, actually even the mechanical repair and maintenance of the equipment, whether it was keeping up with the instrumentation, GIS, health and safety, or QA/QC procedures. All of these things were integrated with the Ministry of Water Resources workers so that they would leave, so that when we in the task force left, they were left with all of the skills and hands-on training to carry them forward. And we have strong confidence that that has been happening. We have heard good things. With that, I'm very pleased to say thank you and very proud to have led the AECOM team.
David, thank you very much. Wait, am I muted? Wonderful presentation of Mosul Dam rehabilitation effort by David, AECOM, together with Iraq's Ministry of Water Resources, supported by U.S. Army Corps of Engineers, in a very difficult working condition. I was working in Afghanistan for 3.5 years, rehabilitated the hydropower plant. So what I can sort of imagine what you guys went through, but the volume of the grouting works as well as the capacity training you have conducted, I want to congratulate you and your team and the Ministry of Water Resources in Iraq. David, a real thanks for sharing your experiences and technologies that you have shown. It's already 15 minutes past our deadline time, and sorry, I have to jump on to another meeting in 15 minutes. So instead of taking the questions and answers at the moment, please send them to the Secretariat for those and for the bilateral questions and answers to happen. Okay, I just want to summarize. Just took a note while I was chairing today's session. The first presentation on the seepage control in masonry dam with modern technology, using innovative techniques and execution method, a case study of the Bhavani Sagar Dam from Tamil Nadu by Suresh. This was an example of the injection grouting using the pointing mortars, or the seepage problem faced every day here in Indonesia also, and the technologies that much needed elsewhere where the seepage issues where they face. In Maneri Dam, on the second presentation, repair of spillway and energy dissipators severely damaged by the rolling boulders during the flood case study by Vinod Verma of the UJBLN Uttarakhand Jal Nigam. Complete damage case of 5,000 cubic meter discharge, which revised to 8,600 cubic meter per second. I'm glad to see the good examples of the rehabilitation work in this regard from Bank's Dam Rehabilitation Improvement Project, which I was a team leading until a couple of years ago. These are the examples of the various concreting works with various mixtures. M90, I'm not sure how strong, that must be a very strong compressive strength you have, with fiber and non-shrink admixtures used elsewhere. I thank you, Vinod, for sharing this experiences also. On the third presentation, appraisal of spillway capacity and storage augmentation for the dam, using the piano key weir and fuse plug for the climate change effect, by Dr. Nayan Sharma, together with Dr. Gopal Singhal, at the IIT Roorkee, SMU University. And thank you. And glad to see the continuous academic support to the dam safety program of India. Many in India, they mentioned that the dams are irrigation dams without flood cushions, with the example of Idukki and Idumalaya in Kerala state. There were examples of dam failure throughout the world was shared. Also, example of disaster prevention was presented, Tiri, Mataria dams, and quite interesting to hear that piano key weirs as well as the fuse plugs, how innovative and cost-effective technology these are. Examples shown from France, Vietnam, in Van Phung Dam, and in India, Swarakudu Dam with hydraulic modeling. Ongoing research and development of both technologies have also been shared. Thank you very much, Dr. Nayan Sharma. On the restoration and the rehabilitation of the spillway with modified energy dissipator, a case study by Amit Kurkale. Glad to see the works, strong research work from Pune in India, that Indira Sagar Dam in Madhya Pradesh was a case example. Main spillway damage bucket photo was quite striking. Damage mainly due to the hydraulic and structural reasons which they detected. Examples were shared from the two-dimensional and three-dimensional hydraulic model details, including the video of the hydraulic models itself. And the very fascinating example from the Mosul Dam, Iraq, thank you, David, the multinational dam foundation rehabilitation effort of injecting grouting of 5,400 holes for more than 40,000 cubic meter in grouting quantity. I mean, just looking at the concrete producer itself, that was striking to begin with. Yet you have also trained thousands of Iraqi engineers successfully for the technology transfer. I really want to congratulate you with all that conducted. First phase 2 years, second phase year and a half, if I remember correctly, in a fragile environment. I thank you, David, very much for sharing your efforts in this endeavor.
Thank you.
Thank you very much. And thank you, everybody. This session on the rehabilitation technology to enhancing dam safety will continue tomorrow morning. And I'm sure that listeners, participants of this session alone or throughout the day, you must have had a lot of examples that you have seen. And Icold together will continue to share the knowledges that you may require, that you may want to implement in the field. I'm sorry that I have spent more than the time that we have allocated to us, but I'd like to thank on behalf of the International Committee on Large Dams as a session chair on the Symposium on Sustainable Development of Dams and River Basins. Everybody, thank you very much for listening, and please stay safe in this special conditions, and keep up with the good work in the dam rehabilitation of the world. Thank you very much, everybody, today, and good evening to you all. Thank you, and bye-bye.
Sir, thank you very much.
Thank you very much.